Yeah. Mm. Thank you very much.
Yeah. Okay. Uh,
Share the screen.
you want to sit here?
You see the front of box.
Yeah.
Yes, sir.
It's working?
Yes, sir. Thank you.
Okay.
So you can see, I stand there and.
No, I'll sit there so that.
Oh, okay, okay, yes. Also, did you present the screen to Zoom? Like, did you share the screen?
Yeah. Oh, I'm not. Um, no, you're right. Yeah. So you guys can see the screen now. Can you?
Yes, sir.
Hello?
Yes.
Can you see the pointer? Oh, no, no, no,
Try
pointer is over here. See, I see. Pointer is from here. Okay, no problem. That's it.
Okay, you can't see the pointer. I guess that's okay.
That's okay. I'll explain everything mostly.
At least you could move the slides on.
Yeah, I can do that.
Okay, I encourage people, thank you for putting up with all the things and thank you for listening. I encourage more people to attend because that's like people have spent invested a lot of time and then you will have to having an audience is very important to listen to you. So that's why I encourage everything else. To give show support for your students, and also along the way you can learn. That's even more important. So even though you may not have read the paper, try to understand and ask questions. Feel free to ask questions. If I will, as the moderator, decide whether to defer the questions till later or not. So some of the questions that you ask may be best answered right at that point. So don't feel shy of asking questions if you don't understand something. Okay, thank you. Okay, go ahead, John.
Hello, I'm Aditya, and today I will be presenting the paper towards formally say, formally approximate minimal explanation for neural networks by Pikers and Solverson. So if you have any questions at this point or at some point, just stop me and ask questions. So I'll be like I'll try to answer them as soon as possible. Okay. So this picture depicts night time, right? And the below picture is a zoo. So this, if you ask why, we will find an answer. So these statements serve as an explanation for the classification instance. But if we train a DNA to classify this instance, if highly accurate, the DNA will classify as night. But if we ask why, we will find an answer from the DNA for anything else. DNAs can provide a verbal explanation for the classification instance. DNAs are now being used in numerous domains. Unfortunately, DNAs are black boxes, can be interpreted. This is often still concern in safety critical systems and also prone to adversarial attacks. Can we say that the moon being in the sky is enough to explain the classification? Explainable AI or XAI construct models for explaining and interpreting the distance of DNAs. Pixel values are input to the DNAs. So can a DNA say that the image is classified as 9 and the subset of pixels is white? And note that the subset of pixels might not be as nice as moon, or it will be written by some algorithm and might be very low level and maybe pretty random human being or human. But still can the DNA do that? So this paper depicts a similar approach, that is, we can provide a subset of features as an explanation to justify the instance. So how to formalize from justify? We will go through all of this. So any questions you can ask now, okay? So I'll just go ahead. So now the brief overview of the paper. So we'll first formalize the explainability. Then we'll see an algorithm to compute probably correct approximate minimum explanation. Then we will try to optimize the algorithm, and then we will see how to make explanation more compact and more human readable using bundles. And then we will go for experimental result and comparison, and then we will discuss in future talks. So a DNA verification query is a tuple P and Q, or A is a DNA that maps an input vector X to an output vector or output class Y. P is a predicate on X called post precondition, and Q is a predicate on Y called post condition. So a DNA verifier checks whether there exists an input X naught such that precondition and Q post condition holds. That case determine if there exists an input satisfying a condition, and answer case verify there exists no such inputs. Just note that DNA verification problem is known to be NP complete, and we will use this information later. A classification problem is a tuple FDKN, where F is 1 to N, denotes the feature and also called the feature space. D is basically the domain of all the features, but D1 plus D2 plus to Dn, and you can call it domain space. So K is basically a set of classes or the possible labels, or we can also call it label space. And the script F is basically the input space. It's D1 plus D2 plus Dn. We will take an input from this space. So a neural network is basically a non-constant classification function which maps an input from A to a possible level K. Possible level is K.
Yeah, so in this return, so normally we talk about neural networks, you just have the inputs, and you know the DNN is a function that maps the flattened input. So here specifically there are these feature set IDs that are introduced, and the value set itself is organized structured as per the feature.
Exactly.
So that is kind of some additional structuring that is introduced to be able to talk about explain the fashion, correct?
So we'll just in the next few slides we'll just get the difference between F and script F. So just remember that F is for now, F is a feature space, whereas script F is the input or value space. So we'll take so we can consider this as a variable and a variable variable. But it will be clear in the next few slides. So a classification instance is a pair B comma C, where B belongs to the input space or value space, C belongs to the label space, and C is the output of B on A. Okay. So in other words, B mapped by the neural network N to class C. So now we will give an informal overview of the explanation. Okay. For a given classification instance, B comma C, why was B mapped to C? We don't know the answer, right? So is there a set of features with determinacy in instance? That is, if we fix the values to those features with such inputs always belong to class C. So if we set the sky guard and draw a moon, it will always be a night time, we know. But those pixels serve as an explanation because it will always be night time whether there is a river or a tree in the remaining part of the picture. In other words, even if the values to the features that are not in the explanation change arbitrarily, the classification remains the same. So this is the informal overview. Any doubt there?
Yeah, in other words, those things that are not in the explanation, their values are insignificant.
Yeah, exactly.
That is how the explanation is defined, correct?
Yeah, exactly. So this is an example. So we'll get the difference between feature space and input space here also. So this is the original event, and the right side you can see the explanation here. So here the feature space is all the pixels, that is 784 pixels. Okay. So each domain Di is assume two possible colors, they can take two possible colors, black and blue. So the script name will be black comma blue to the power 784. Okay. So explanation will be a subset that is enough for the class to be shown. So you can see the right side that there is subset of pixels and it looks like soup. So the neural network, so the algorithm returned this as explanation, and so this means that even if we change the remaining pixels to make it blue or black, the output was always assumed. Okay. So even if we change the remaining pixel, still assumed. So is that clear to you? Okay. So now the formal definition of explanation. So given an input V with a classification C, an explanation E is a subset of feature space. If fixing the values to those features in E will imply that the output is fixed to the class C, whatever values the remaining features may take. Okay. So note that by definition, the set of all features serves as a trivial explanation. Okay. And also note that there might be multiple explanations for a classification instance. And we'll see an example in the next slide.
So which would be better? I mean, formally. So the smaller the explanation, the better it would be. So that is the kind of.
Yeah. So later we'll see that like the smaller the explanation, the better the understandability or more compact it is. Like obviously the whole speech space doesn't serve as a good explanation, right? Okay. So consider the following DNA with 3 input nodes and 2 output nodes. So here the feature space is the set of nodes V11, V12 and V12, and each of the node can take values from the set 0, 1. So the value space will be 0, 1 to the power 3. So value space and input space are there, and you can see the difference between feature space and the value space. Okay. So feature space basically the nodes, and the value space will basically the values the features can take. Okay. And the right side, the top output node classifies C1, bottom output node classifies C. The node with the higher value will be classified as the output. Okay. So in this case, the 15 is higher than -4. So the output class is C1 or 1, we can say. Okay. Now we claim that in this picture, the set V11, V12 is an explanation for the instance V1, C1. Okay. So V1 and C1, V1 is basically 1, 1, 1, and C1 is basically 1. Okay. To verify this, let's assign all possible values to V1 tree and see if the class changes. So in this simple example, V1 tree can only be 0 or 1. So in the left side, we are assigning 1 to V1 tree and we are getting output classes 1. And in the right side, we are assigning 0 to V1 tree and we are getting 1 as the output. So we can say that V11, V12 is an explanation, integer explanation. Okay. So we will now try to verify explanation as an answer trial. So this is the recall that this is the definition for the explanation. Because the definition of explanation. So this can be encoded as a verification query P, N, Q, where the precondition P is basically E equal to B. The values to the features in the explanation will always be same. A is the neural network function, and the postcondition Q is the class is not equal to C. So if this query is unset, so is definitely an explanation. Okay. In the previous example, so x1 will be equal to 1 and x2 will be equal to 1 and c1 will equal to be 2. So this will be the answer query. So if this returns answer, then we will say this is an explanation.
Yeah, if you really want to use, if you can sit there, you can actually point the cursor at those things.
Okay. Okay, I think in the next phase I don't need it, so I'll just go.
Fine.
So yeah, do you have any problem like do you have any trouble understanding the points or then like trying to like point? Or is it clear?
Yeah, I mean, I guess Anitra is asking if he has a pointer, but you can't see it. You know, if you want, you can sit there and then give me the pointer. So there's no one in the audience.
Yeah, anyways.
Yeah, anyway. Huh?
Yeah. So I'll just
And now you could use that
Yeah,
will be visible there.
Yeah, okay. Yeah, makes sense. So yeah, so the previous example, the easiest example from the previous slide can be encoded as unset. So we are setting x1 to 1 and x2 to 1, and then we are saying that nx not equal to c1. So if this return unset, so then that v11, v12 will be an explanation. Okay, so it should return unset because we have already seen this is an explanation.
Yeah, any questions there? So far it is just given an explanation, you know, just check if this query is unset, this check if check if it is an explanation or not. This is very much like correct Anitra, that you would check any property of a neural network. You know, it's the same kind of one set query.
Yes.
Yeah.
So do you have any questions? Please ask. Okay, I'll try to answer them as soon as possible. So now we are interested in
Am I audible?
standard because of its better understandability.
Hello. Am I
Yeah,
audible?
You have a question?
Yeah. So I just wanted to understand, can you explain what these sets are in terms of the boot example that you had shared in the beginning of your slides?
Yeah, I'll just go back to that slide. Yeah. This one, right?
Yeah. So what is the explanation in terms of subset of features in this picture? If you can
What
maybe
are some of the possible explanations in terms of the pixels which are the features?
So in this picture, yeah, we are like in the right side, we can say that the pixels that are marked blue or black is the subset of pixels that are explanation. Okay, in this picture.
okay, great. Yeah.
That
Like
is one. What is another one?
there is a whole picture can be an explanation. So that's
also, that is kind of a trivial explanation which is not that useful. Okay.
Yeah.
And exactly those pixels that you show as blue, that's what you meant.
Yeah, exactly.
That is one explanation. What can be another possible explanation, which is
so any superset of this explanation should also be an explanation. So I think that makes sense.
Yeah.
But like this is probably the minimum or minimal explanation written by the algorithm the authors had run. So any superset will be an explanation for this. We have already said that there might be some multiple explanations for this. Okay. So yeah, is this clear, Diganta?
Yeah. This
what might not be an explanation here?
Subset
So-
might not be an explanation. Yeah, like I think it's minimal. So if we remove,
Give an example of what might not be an explanation. I mean, of course, that you don't know.
yeah, like
Okay, but how about if everything is
yeah, then it's not to be an
blue,
explanation.
and
Oh.
lighting, everything is blue, or everything is every pixel is.
So we can do that because like like we can do that, right? Because
That's right.
yeah, because classification instance is fixed. Yeah.
Yeah, because the
We can-
values are important. It's the subset of
Subset of features. They should have same value. Yeah. So now I'll just go back to the point where
So is that clear to the audience as to what the explanation is? So,
Yeah, yeah, yeah.
So yeah, this one. So now it's so we have now we are interested in smaller explanation because of its better understandability. A subset E is said to be a minimal explanation if E is an explanation, and if we remove a single feature from it, it won't be an explanation. The first part in the formula, captures the explanation check, and the second part verifies if there exists no smaller subset for that. Okay. A minimum explanation is minimal explanation of the smallest size. Okay. So now we'll try to verify v11, v12 is indeed a minimal explanation. Okay. So verify this. We first remove v11 from E such that v12 is the only element in explanation, and then when we assign 0 to v11, even if v12 is the same, the output class was different. The same thing happened when we remove v12 from the explanation. So in both the cases, we can see the classification instance or the classification output class was changed. So we can say that v12 alone or v11 alone cannot be an explanation. So v12 and v11 is indeed a minimal explanation. Okay. Now, similarly, we can verify that v13 is a minimum explanation. To verify, we fix the value of v13 to 1 and try all possible values for v11 and v1. So we have already seen the case where v1 and v12 equal to 1 and 1, and that case classification instance was 1. So in this case, when we are assigning 0 and 0, the output class is 1. Similarly, when we are assigning 1 and 0 and 1, still the classification instance was 1. So the classification output was 1. So if v1 is indeed the minimum explanation. So how can I know it's minimum? Because like this is smallest cardinality size, right? We can zero size feature space, zero size an explanation must have the size greater than 0. So v13 is indeed the minimum explanation. Okay.
So once again, if you go back to the shoe example,
Okay. Yeah.
could there be a smaller explanation than what you have shown being space?
Yeah, there might be smaller. Yes, it can. But like
As long as it kind of preserves the.
yeah, it might be of completely different. So we don't even know about that. It might be of completely different.
Yeah, but what I'm thinking is, if you pick a subset of these blue portions,
Mhm.
such that the shape is still maintained as a shoe, you
Mhm.
might still
Yeah.
probably give. There could be. No?
Could be, yeah. So I hope this is the minimal explanation. I hope and if that's the case, then it says that we can remove any pixel from it. But that doesn't say that there exists no minimum explanation. There might be a completely different set minimum explanation than this. Okay. So this should be clear. For minimal explanation, we won't be able to remove a single feature from it. So please ask if you have any questions. Okay. So yeah. So now can anybody say what will be a trivial algorithm to find a minimum explanation? Any idea? So I'll just tell it. So if you want to try, you can like, okay. So if you want to try, you can. Okay. So I'll just tell it. So what we can do is like we can get all possible subset of explanations, all possible subset of feature space, and then try each of them to be an explanation or not. So then we'll find a minimum size explanation to be the minimum explanation, right? So this will be very trivial explanation, but a very trivial algorithm. But the time complexity will be exponential. Like we have to go through all possible subsets of the feature space, and that will itself take 2 to the power n time. Okay, so that this is not a very good solution. But what about minimal explanations? Can we get a minimal explanation faster? So any idea about that? Like anybody want to try? What about can we find a minimal explanation faster? Like not trying all possible subsets? Okay, this is also not very hard. I'll just explain it.
Maybe find an explanation and just go on incrementing it in some way till we can no longer. Just a naive idea.
Is this Vipro?
I think he has answered
Yes,
right.
yes.
Yeah, can you repeat?
Am I audible?
Yeah.
Yeah. So, no. Okay, go on. Maybe you're explaining something.
Okay. Probably you have told something
I
correctly.
thought you made a comment.
Okay.
Did you? Hello?
Yes, sir.
Can you repeat your comment?
Yeah. So I said maybe come up with some explanation that is not minimal and like go
Oh.
on expanding it till like we can no longer expand that.
Yeah, like what will be such a trivial candidate? Like we can take a whole set, right? That's what
Yes.
that's done. Like we are taking the whole set as the candidate minimal explanation. Then we are trying to remove as many features as possible to get a minimal explanation. Okay. So in this slide, we'll see a naive algorithm for this. First of all, we define a set of features that are already verified not to be in a part of the minimal explanation. Okay. First, we are sorting the features by ascending relevance using a heuristic model. So the point is the least relevant feature has the least chance of being in the minimal explanation. So we are first sorting the features in the ascending relevance. Now we go through each feature. The explanation at this moment is the free set removed from the feature space. Okay. So we first remove the if from the explanation, and if the remaining explanation is unset, then the explanation after removing f is still an explanation, right? So remove the feature f to add it to the free set and decrease the upper bound by 1. So upper bound denotes the size of the explanation. Okay, is it clear? So you're removing f from the explanation and trying to see that if it's still an explanation. If it's still an explanation, then we don't need f, right? So we are adding f to the free set and reducing the minimal explanation size by 1. That's what we are doing here. Okay, is it fine? Okay, I'll just go ahead. This seems to be a better algorithm than the previous one because we are not evaluating all possible or not evaluating all possible subsets of the feature space, but first of all, this gives an over approximation of the minimum explanation. This will not be a minimum, right? This might be minimum, might not be, but this will be minimal. Okay. Still, linear number of answered queries needed in the worst case. But the problem is, answered query can be prohibitively expensive as the free set grows.
I have a question.
Yeah.
You're right. This is not guaranteed to give a minimum explanation when it terminates. But you can get lucky. I mean, is there?
Yeah.
When is it that it can give a minimum explanation?
Like if okay. So if our sorting heuristic is so good that like it gives one priority to all the features in the minimum explanation, then if we remove everything like in the order, then we will actually get the minimum explanation.
So if you somehow can predict exactly those features that are in a minimum explanation, and you remove those things in that order, then it can give a minimum
explanation.
But you can never tell.
Yeah, we can never tell. Yeah, exactly.
That's correct. Yeah. Okay, good.
So
now people understood. So this is just more efficient, as Anitra said, than enumerating all possible subsets.
Yeah, exactly.
But the trade-off is that you will not guarantee
minimum explanation. Yeah, exactly. So the answer query can be prohibitively expensive as the free set grows. So as the free set grows, the search space also grows, and for the answer query, it needs to go through all the search space to return answer. So the answer query will be very much slower as the algorithm process. Okay. And we don't even know how far are we from the minimum explanation. We'll get a minimum explanation, a minimal explanation for sure, but we don't know how large it is compared to the minimum explanation. Okay, so that's the problem. So what's coming next? So both of these naive algorithms are not efficient. Linear number of queries still bad for zillion features. Okay, as we have said. Moreover, we don't even know how far we are from the minimum explanation in the case of ladder algorithm. Okay. Can you get a lower bound or under approximation for the minimum explanation size to get an idea how far we are from? Also, are there some features which will always be in the explanation? Both the answers are yes, thanks to the dual concept of contrastive example, which will help us to calculate a lower bound of the minimum explanation as well as speed up the algorithms we have already seen. Okay. So, first try to motivate the contrastive example.
Yeah, so you are going to be introducing a new dual concept which can help you.
Solve two problems.
Okay, so yes, yeah, so that that you will leverage
Yeah, exactly.
to get to.
First, we'll try to get a lower bound for the minimum explanation size, and then we'll try to use the fact that is the use the variables in the contrastive examples to speed up our this algorithm we've already seen. Yeah. So we have all heard of one pixel error. So it's an error such that flipping a single pixel will cause a neural network to misclassify. So in the above picture, the original image was classified as 1 by a neural network. But after flipping a single pixel, the image was classified as 9 by the same neural network. Now, we'll formally introduce the concept of contrastive example, and we'll see how this is related to contrastive examples. Okay. Yeah. So a subset of a subset of features is a contrastive example.
Can you go back to the previous thing? So did people understand what the
one
one pixel attack was and why this is a dual concept? Hello?
Yes, yes.
Yes, sir.
Any question you can ask me, like I'll try to answer.
Fine, go ahead. Yeah. This is the formal stuff.
Yeah, in next year I'll try to formalize this. So a subset of features C is a contrastive example if altering one or more features of the C causes a misclassification of the given classification instance V, C. That is, for an instance V, C, if we fix the values to the features according to V that are not in the CXP and go through all possible valuations in the features in the CXP, we will find a misclassification that is C1 not equal to C. Okay, is it clear? Okay, so I'll just repeat it again. Yeah.
Please, please.
Yeah. For an instance V, C, if we fix the values to the features that are not in the CXP and go through all possible value assignments to the features in the CXP, we'll find at least one misclassification for the classification instance V1, V, C. Okay. So, yeah. So in the right side, we can see that all the assignments are same, but we are flipping a single pixel that is white here. Okay. So this is a CXP because if we go to all possible assignments of that pixel, and then we can find a misclassification, that is the neural network misclassified this as 9, while the original image was 1. Okay. So this single little pixel is a CXP. Okay. And in the left image, if we remember the actual image, so all of them was 111, and the classification instance, the classification output was 1, right? And now if we are changing the values of V12 and V1 to 0, 0, and that changed the output class to 2. Okay, so so V12 and V13, this is a set of this is a contrastive example because changing the values of these is causing the neural network to misclassify. Okay. This might be a little harder to grasp, but so if you have any doubt, so just ask me. Okay, then I'll just say a lot of things later in this slide only to make you understand better. Okay. So we can verify this as a query P in Q, the P says that fix all the values to the features not in C. N is the numerator function, and Q is said that the class is not C. Okay. Also note that every superset of a CXP is also a CXP. And smaller the CXP, more useful it is in the context of this paper. And note that the complement of an AXP is not a CXP. Please note that. So they are different. AXP says that this is important. So just listen to this carefully. So AXP says that if we fix the values to the features in it, then the classification will not change. And CXP says that if we fix the values to all the features not in C and assign all possible values to C and assign all possible values to the features in C, then we'll get at least one misclassification. So I'll repeat this once again because I have enough time. So AXP says that explanation says that if we fix the values to the features in it, then the classification will not ever change. And contrastive example says that if we fix the values to all the features not in C and assign all possible values to the features in C, then we will get at least one misclassification. Okay. Now,
Yeah, the last comment, yeah, so this is not as simple as, the red.
yeah, I explained this because of the difference between. Yeah, like if you have any doubt, so they are not complement. Okay, so I just already said they are not complement and I explained why. So if you have any doubt, please ask. I will repeat. Okay. So any doubt?
No, go ahead.
Yeah. So yeah, when I said that the complement of an AXP is not a CXP, so I meant that it not necessarily be an XP, but it's indeed true. Like the complement of an XP can never be an CXP because as we will see, some elements from CXP must be included in an AXP. Okay, so this is also true. The complement of an AXP cannot be an CXP. Okay. So is this clear to you? Why this is true?
Yeah.
That's okay. So now we'll mention some important lemmas. So every contrastive singleton is contained in all the explanations. So this is the relation between CXP and AXPs. Okay, every contrastive singleton is contained in all the explanations. So we'll try to prove this, and the proof might be a little bit of like hard, but I'll just try to explain everything. Okay, let N be a classification function, and V comma C is a classification instance. Without loss of generality, let E be the set 1 to I is an explanation. Okay. And let singleton J is a contrastive singleton. Okay. Assume towards contradiction that J is not contained in the explanation. That is J is greater than I. Okay. Now with respect to V, we'll find an input X which has same values for the features in explanation, but a different value for the feature J and a different output class. Okay. Then we'll prove that such E can be an explanation. The proof is in the next slide, but just go through it once. Okay, just like I will just wait for some time. Just go through it. Okay. Yeah. So I'm going to the next slide. So now let's try to find such X. Okay. We first fix the values for all the features F minus contrastive singleton according to V, and then go through all possible values Xj that J can take. Okay. As J is a contrastive singleton, we'll definitely find an input for which the output class is different from V's. Okay. But X and V agrees on all the values for the features in the explanation, and they should have same output class, which is a contradiction. Okay. Is this clear to everybody? Like J is a contrastive singleton, right? So we'll definitely find an input for which the output class is different from V's. But X and V will agree on all the values for the features in the explanation, and they should have the same output class, which is a contradiction. Okay. So this is just a logical explanation. So there exists x1 x to xj to xn belonging to the input space, such that xi is equal to vi. Like x and v agrees on all the explanation, all the features in the explanation, and j is not one of them. And then we'll find an output classification, that is not equal to C. So it can be an explanation, right? So this says that every contrastive expression is contained in all the explanation. Okay. So the second lemma is all explanations contain at least one element of every contrastive pair. So contrastive pair is basically the contrastive example of size 2. Okay. Yeah. So this proof follows the same argument. Assume there exists a contrastive pair C and an explanation E for V, C that are disjoint. Like C and E doesn't share any common elements. Okay. So we fix the values of the features not in C and go to all possible value assignments to the features in C. We must get an input instance with a output class not equal to C. Let's call it S because C is a contrastive pair, right? But X and V agrees on all the values in the features in E and so should have same output class. This is a contradiction and therefore it can be an explanation. Okay. So are these two proofs clear to everybody? Like next we will generalize the proofs. Okay. Just ask any questions if you want. Any questions? Okay. Okay, I'll just go ahead. So the above two lemmata can be
Just
generalized.
a question, not exactly
Yeah.
a question. So the proof you just presented is not like a real-time constructible, right?
Can you repeat? Like I missed the last word.
The proof that you said, this proof is not like constructible. Like we know that we can fix the values and so on and so forth. Like we cannot construct this proof because like any
Yeah,
point of
exactly.
instance
We
you cannot
can,
construct.
yeah, we can actually construct that, but like this lemma, we are assuming a contradiction, right? So this will never
Yes.
ideally exist in the real world.
Yes,
So,
yes, that's what I wanted to.
yeah, so we won't be able to find, but like in some hypothetical scenario, we will be able to construct such a case. Like if anybody claims this, then we will be able to construct something to prove him wrong, prove him or her wrong. Okay, that's the
Okay,
point.
thank you.
So the above two lemmata can be generalized. So all explanation contains at least one element of all contrastive examples of the arbitrary sizes. So this follows almost same argument. Okay. So we'll not prove this because this proof is like very long and like simple but very long. Okay. Yeah. So given a collection S of sets from a universe U. Okay. So this is related to something like hitting set concept. So if you are aware of hitting set, so it's something similar, right? So all explanation must hit at least one element from all the contrastive examples. So let's formalize the hitting set. So given a collection S of sets from a universe U, a set H is called a hitting set for S if for all set small s belongs to the set of sets, H should hit every of them. That is, intersection of H and small s should not be non-empty. Okay. So this is the definition of hitting set. So basically it says that H should hit at least one element from every possible set in the set of sets. Okay. A hitting set H is said to be minimal if no proper subset of H is also a hitting set, and it is called to be minimum if it has the smallest possible cardinality among all possible hitting sets. Okay. So now a minimal hitting set of all contrastive examples constitutes a minimal explanation. The minimum hitting set of all contrastive examples is exactly the minimum explanation. So this is also like pretty intuitive, but the proof is also very long. And so I have like not included the proof, but the proof is simple but pretty long. So, but this is pretty self-explanatory, right? Now, what can be an algorithm to find the minimum explanation? Can anybody want to say? Like we after using this also we can find an algorithm that will like give us a minimum explanation. So can anybody want to explain that, or anyone want to try?
For the examples, which one you do?
Okay, like we have already said concept of contrastive example, and
you should explain it.
Okay, yeah. Okay. Then we can pick an element from each of the contrastive example in order. Okay, first we can list down all the contrastive examples. Then we can pick an element from each of the contrastive example in order, and we will skip if already the contrastive example is hit. Okay. Now this converges to the minimal hitting set or minimal explanation. Okay. So unfortunately, a minimal hitting. Okay.
So the minimum.
Oh no, this is minimal hitting set. Okay. So minimal explanation. Okay, yeah, this is true. But we can also listen to all contrastive examples and get the minimum hitting set of it to find a minimum explanation, right? Okay. So unfortunately, minimum hitting set problem is known to be NP complete. Okay. So further, enumerating all the contrastive examples may in itself take exponential amount of time. So finally, DNN verification is itself an NP complete problem, which may slow down the XP and CXP queries. So this is not a very good algorithm. Like, yeah, we can actually reduce the all possible contrastive examples and then get the minimum hitting set of it to find a minimum explanation. But as you can see, eliminating all of them is exponential, and minimum hitting set problem is known to be NP complete. So it's not possible. Like, it's not like we can something do. Okay. So anyhow, yeah, like do enumerating all the CXP is expensive. We can actually keep the process of enumerating at any point, let's say up to size of 2, to get an under approximation of the minimum explanation. Okay. We can stop at any point. Like say we enumerated all the contrastive singletons and stop. And we can say that no, we have enumerated singleton pairs and we have stopped. Like this, we can stop at any point, and then this will be an under approximation of the minimum explanation. Okay. So apart from that,
So what can you explain in what way you call it is an under approximation?
so yeah.
Yeah.
So minimum hitting set of all the contrastive explanation will be the minimum explanation, right? But we are clipping, let's say till size 2, and then we are taking the minimum hitting set of it. So we have left some of the contrastive example of bigger size out, and this some of them might contribute to the minimum.
So all you're saying is that this is a superset of a minimum contrastive example, right?
So
Or
this subset.
it's an under approximation of the
Yeah.
minimum.
So
It does not have all of.
So if we keep some
It's a subset
of all the possible
of
CX.
a minimum explanation.
Exactly. So apart from that as we are calculating CXPs, we can use this information to further speed up the algorithm for calculating a minimal explanation. Okay. So let's say that we already know that F1 is a contrastive singleton. So F1 must be included in all the explanations, right? So this will enable us to add F1 in the minimal explanation without making any extra verification queries. Okay. So using these methods, the authors propose the novel approach to probably approximate a minimal explanation we will get. Okay. We will first explain a naive version of it, and then we will try to optimize the approach to speed up the algorithm. So, yeah. So this is a naive approach. So the approach runs 2 parallel threads, an upper bounding thread and a lower bounding thread. So we will just explain what are they. So TUB computes a minimal explanation by reducing the feature space, providing an upper bound or over approximation to the size minimum explanation size. Okay. And TLB constructs in contrastive sets to a compute a lower bound on the same, and the UB and the lower bound, UB and the LP together enable estimating the approximation ratio. So this is the algorithm we've already seen, right? So this is for the minimal explanation algorithm. So just go through it once. Like we are like removing one feature at a time from the explanation and try to see if this is still the explanation. And this is basically the upper bounding trait. Okay. So after this, we'll get a minimal explanation, which is an over approximation to the minimum explanation size. Okay.
Yeah, this is the same thing as you showed up here.
Yeah. So now this is the lower bounding trait. So what we are trying to do it here, like we're first evaluating all possible singletons. Okay. So we are removing one feature from it and try to see that if that feature is a singleton or not. So if it's a singleton, we are adding it to a singleton cell. Similarly, after this, the second loop tries to find all possible contrastive pairs. Okay. So after first loops, we have all the singletons and we have all the contrastive pairs. Is it fine with everybody?
Yeah, what is NVC here?
Yeah, so I'll explain that. So first loop is I hope it's clear to everybody. So first loop gives us singletons, contrastive singletons, and second loop gives us the contrastive pairs. So MVC is basically minimum vertex set, minimum vertex cover problem. So note that my finding the minimum hitting set of all contrastive pairs is a 2 MHS problem, which is basically a minimum vertex cover problem. Okay. So now the lower bound will be the for each of them we are increasing the lower bound by the 1 for each contrastive singleton, and then after enumerating all the contrastive pairs, we are adding the size of minimum vertex cover pairs to the LP. Okay.
Yeah, so what is this? You're using the contrastive example here.
Yeah.
Just the first two levels, singleton and pairs, is hopefully efficient, reasonably
efficient. Yeah.
To come up with a measure
result.
the lower bound
Exactly.
of the size of the minimum expression.
Exactly. So I'll just explain it next
Yeah,
lecture.
that's okay.
Yeah. So this is the so we can constant LP by the following inequality. So LP is basically the size of singletons plus size of the minimum vertex cover pairs, which is less than equal to the K images problem for all the K CXPs, right? So K is arbitrary size CXPs. So this is the basically the MHs of all the CXPs, which is basically the size of the explanation, minimum explanation, right? So you can see that LB is always less than equal to the minimum explanation size. So LB serves as an under approximation for the minimum explanation. So is this clear? Is this equation clear?
Yeah, go ahead.
Yeah. So unfortunately, the MVC problem is also NP complete. However, the problem has a linear two approximation greedy algorithm, which can be used in finding lower bound in cases of large feature spaces. Okay, so you can actually use a linear two approximation greedy algorithm to get a MVC of size at most 2 of the actual minimum vertex cover. Okay. So towards the we'll try to optimize the algorithms. So the upper bounding thread forms the backbone of our approach, but suffers from limited scalability. Okay, as TUV progresses and more features are freed, the growing search space significantly slows down the verifier. To address this, the authors have proposed 3 methods. The first method remove those that definitely belong to any explanation and hence need to be checked for inclusion in the free. Okay. Sorry. First method removes those that definitely belong to any explanation and hence need not to be checked for inclusion in the free. So here it will be not. Okay. So we'll use the information from the lower bound. We'll see it later. Okay. The second method uses binary search to discover the minimal explanation in fewer parts, basically in log n parts. And we won't discuss third method. So it is a heuristic to remove those features from the search space that are very likely to be an explanation, and it's called local singleton search. So we'll skip this. I will explain this why we are skipping this. Okay.
Yeah, but in simple terms, what you're using the fact that singletons, some, members of a contract, for example, have to be there
Exactly.
in the thing to, figure out, what features you can actually remove.
Yeah. So
That way,
yeah.
upper TUV algorithm will be more efficient.
Exactly. So when you say remove those,
That's all I'm trying to say.
yeah, like okay. So any doubts you can ask me. Okay. Any doubt? So is this clear? Like this is not like this will be very clear in the next slide only. But if you have any doubt, just ask. Okay. Okay, I'll just go ahead. So now we'll try to optimize the algorithm TUV using the information from TLB. So now remaining features is a set of features whose participation in the minimal explanation is not yet checked. Okay. Free is the set of features which are verified not to be in the minimal explanation. Now we already have the contrastive pairs after running TLB. So we'll find all the contrastive pairs which okay. Now what we can do is like use a heuristic model to sort F by ascending relevance. And for each F in the remaining features, we can actually try to remove F from the explanation and check if still removing even after removing F is still an explanation or not. And if it's still an explanation, then we are adding F to the free set, and we are decreasing the size of upper bound by 1. Okay. So note that remaining features we are in the remaining features already first removing the singletons from F. Okay. So that's a huge optimization. We are not even considering those features in the contrastive singletons to be checked. Okay.
Because there you know that.
They're
cannot
definitely,
be there.
yeah.
Whereas the contact request, you don't know which one you have to remove, and that's why you will have to try, correct? Yeah.
Exactly. Now, one more thing in line 8, note that we are doing something. So now we already have the contrastive pairs also. We'll find all the contrastive pairs which include F, and for all the CXPs, we'll remove the other features from the remaining set. As we know, both of them can be removed from the explanation because both of the contrastive explanation cannot be removed from the explanation, right? So if F comma G is a CXP pair and we are removing F from the explanation, G must be in the minimal explanation. So what we are doing is like we are removing F from the remaining features, and if we are removing from the remaining features, then we will automatically add it to the explanation. Okay. So is this clear to everybody? Yeah, I'll just wait for something. So the line 8, note that we are deleting all the features in a pair with F because we know that F comma G, if F comma G is in contrastive pair, so G must be included in the explanation because the contrastive pair must not be removed from the explanation. Okay. So we are removing them from the remaining features because if we remove them from the remaining features, then if we then that feature will already be in an explanation. So this is a little harder, but yeah, like try. Yeah, like if you have any doubt, I will just wait and like explain. Right? Yeah, this is a little hard, but I'll just wait for like 20 seconds or like that. So yeah, if you have any doubt, just ask me. So yeah, we use the fact that contrastive singletons must be a part of any minimal explanation, and also use the fact that same goes for the one of the elements for every contrastive pair. We can remove all the both elements of the contrastive pair from the explanation. That's we are removing them from the remaining features. Okay. So is this clear, or should I repeat what's there?
No, that's okay.
Yeah. So just ask me if you have any questions. So I'll just after the meeting also like you can ask me. So yeah. Now we'll talk about binary search. Yeah. So in a binary search technique, we'll again first sort the features. So in this case, sorting is pretty important, okay? Because we'll see. But in this case, the sorting is more important than the previous algorithm. Okay. So yeah. So ideally, features in minimum explanation should actually get the higher relevance. Okay. So it should be at the last end of right end of the if array, okay, after sorting. So first we remove the first of the features and query that if the second of along is the explanation or not. Okay, so in this case, what we are doing is meet is basically L minus R by 2.
Now, detail.
Okay.
What I do, there is a main assumption of line 1.
Hmm.
There is you're assuming that the features are sorted in some relevance order, correct?
Yeah.
You have to repeat that.
Okay, I'll just repeat it. Yeah, I won't just explain this algorithm, but I will just say it in my words so that you can better understand it. Okay. So in the binary search again, we'll again first sort of features in absolute relevance. In this case, it's more important. Oh, so they have used line for them, but they have
So that is some
heuristic model.
that is already
Exactly.
outside of that.
Exactly.
Given that, now you could put an order in which you could
Yeah.
remove the features.
Exactly.
So hopefully,
Hmm.
and then you could, use
Yeah.
that for binary search.
Yeah, exactly. Yeah. So ideally, features in a minimum explanation should get the higher relevance, and will be most likely in the later half of the feature space. Okay, after sorting. So what our hope is like all the unnecessary features that are not in the minimal explanation will be clubbed together in the first half of the feature space after sorting. So what we are doing is like we are removing the first half of the feature and query that if the second half alone is the explanation or not. Okay. So if the answer is yes, we completely remove the first half from the explanation. And that's not a problem, right? Because we already know second half is the explanation. So we can actually remove the first half from all the explanations. They are not needed. Okay. And then we can call the same procedure on the second half of the feature space. Okay. So we know the all the minimal explanation will include all second half only. So we don't need the first half. Okay. And but if the answer is no, like we will add the second half as a part of explanation because we know the answer is no. That means that the second half of the explanation will always be part of the explanation. And we are adding it to the explanation, and then we are trying to make a half on the first half, And then what we are doing is like first half of the explanation and the whole second half, first and the second half of the first half of the explanation and the whole second half will be enough for the explanation. Okay. So if that's the answer is yes, then we can what we can do is like we can remove the first half of the first half of the explanation. Okay, so this is a recursive call. So the main fact is like at any point you have a feature space sorted according to relevance, and we can remove the first half of the feature space from the explanation. Okay, that's the main point. So if we can do that, then then we can actually recursively call the algorithm on the feature space again and again. Okay. So is this clear, or should I say it again? So this is a picture.
It relies on the fact that these are the relevance order is.
Yeah, exactly. That,
Otherwise, there's no guarantee.
Yeah, like
that it's the thing. So, I mean, the relevance order means if something in that order is not in the minimum, something that is of greater, lesser relevance will not be in the minimum set either. Okay?
exactly.
That is the, under that assumption, you are able to, do this thing. And this is better than searching over all subsets.
Yeah.
Right, so and it's also better than removing one at a time.
Because you are removing half of them first. Okay. And this is like if this is like something that we can get it the answer in logarithm time. Okay. So this is a problem like we can face actually. Like even if a single important feature is in the first half, then the algorithm will fail. Okay. So like in this, what I can think of is like we can use something like max set, like this kind of thing, which is a little like even which is a little what I can say, like which is not that hard. Okay, like if we use max set, then even if one of them is in the first half of the day, then also max set will return something based on like it's true or right. Okay, so this is the case. So I'll not just say
Don't get into.
max. Yeah. Okay. Yeah. Okay. Because I'll not. Yeah. It will anyway explain what max set problem is. But yeah, is this clear to everybody? Like why we can remove the first half? Yeah, so even if we remove after removing the first half, then we are checking the second half is enough for the explanation. Okay, so if it's enough for the explanation, we don't need the first half at all, and we can do the binaries of the second half. And if it's not, the answer is we need the first half, then the answer will be, the question will be how much of the first half we will need. Then we'll try to binaries on the first half only. Okay, and the second half, all of the second half will be in the explanation. So that's the main point. Okay. Okay. Also, we can also use the information from TLB to remove the features in CXP singleton that will further speed up the process. Okay. So in the first line, we can actually remove the contrastive singleton from the feature space, right? Because we know they will always be in the contrastive. They will always be in the all the explanation. That doesn't matter. Okay. So we can actually remove them from the F in a very first. Okay. Is this clear?
Yes, more.
Yeah, okay. So is it clear to you, sir? Yeah, okay. Now I will just keep this because the assumption they are taking is not very easy to explain and not very likely to happen. So I'll just keep this. So they're like, yeah, I'll just keep this. Now we come to bundles. Okay. So the bundle is introduced mainly to tackle the challenge of low level explanation for certain users. 34. Okay. Yeah. Intuitive bundles are a partitioning of the features in disjoint sets. Explanation in terms of bundles are often easier to comprehend, and also it curtails the search space traversed by the verifier, like it makes the search smaller by bundling up the features. Okay, and hence speeds the process further. A bundle is a subset B of F. The set of all bundles B is forms a partitioning of F. That is, F is a disjoint union of all the bundles. Now, yeah.
Intuitively. So earlier features were at the pixel level.
Yeah.
Okay?
Yeah.
And now you are lifting that thing to regions of pixels.
Yeah.
Okay? and then that's what the bundle is. So the idea here is
Hmm.
to lift the level of features to
Feature.
a higher level.
Exactly,
So that
exactly.
you don't need to, your explanation will be in terms of bundles.
Bundles, and moreover, you can see.
That's all.
Okay, like
That, then the essence.
yeah, so it will also speed up the algorithm. So yeah, that's the point. Okay, so yeah. So a bundle explanation EB for a classification instance is a subset of bundles such that if we fix the values for all the features in a bundle explanation to V, then the classification instance will not change. This is very similar concept. Now we are not getting the pixels as the explanation, rather we are getting bundles. But the remaining everything is same. Okay.
Or the bundles, the set of bundles have to be a partition of the
Yeah.
one, or
No,
it be overlaps.
no, it's a partition.
Partition. Yeah.
So this is the
You
meaning.
did mention.
Yeah.
Sorry.
Yeah.
So it has to be a partitioning, and that's why then you can have that.
Exactly. Exactly. Yeah.
So, yeah.
So also the theorem is the union of features in a bundle explanation is also an explanation. That's pretty trivial, right? Because we can like fixing these pixels will not change the output classification instance. So this is pretty trivial. And we can also develop similar notions like minimum bundle explanations and contrastive bundle examples. And algorithm, and then algorithm methods can be extended to the case of bundles to perhaps get more comprehensible explanations. Okay.
Yeah. So does this also, this gives certainly more comprehensible explanation, and that I can understand.
Yeah.
But does it also will be more efficient?
Yeah. So that's I wanted to explain here. So you can see there like just note the first bundle here. So consider this is 784 pixel wala image like 28 cross 28. But let's say that we are 4 cross 4 pixel are considered as one bundle. Now for the previous expansion algorithm, we have to go through all 784 pixels as a feature set. Now, if we are clubbing them into 4 cross 4 pixels as a bundle, then it will reduce to like I'm not sure like 427. So for only 14 bundles. So it will speed up the process by a lot of time. Okay.
But it may miss some explanations.
Yeah, it may miss in the sense that like the external side indeed will be higher in terms of pixels. Okay.
Because the next year that you said was only implication.
Yeah, exactly. That's also the exactly. So implementation. So every bundle explanation will must be the explanation, not the previous. So we might miss the minimum explanation as the minimum bundle explanation by the literature. Yeah. So now we are almost at the end. Like we have 15 minutes left. So I'll just define.
At this point, are there any high-level questions?
Yeah,
before it's time to pause before he goes to the experiments from the audience.
So I won't take you along for the experimenting. So if you have any questions, please ask. Please ask.
Hello? Yeah, okay, you can go ahead. Yeah.
So yeah, okay. After this also you can ask, no problem.
Yeah.
So I'll just first explain the experimental setup. So they implemented a Python framework using the Marabou DNN verifier, which supports proofs, abstraction, and optimization. Feature element, these points. So we have using some feature elements for sorting, right? So they have used line method for this, and the MVC was used. MVC used the two approximation linear greedy algorithm. Okay, so we have seen that the MVC problem is NP complete. So for zillion of features it don't work. So they used two approximate linear greedy algorithms. Okay. So experiments ran on x86 GNU Linux with one Intel Xeon Gold 6130 core, and the timeout limit was 1 hour. Okay. So benchmark included DNN trained on MNIST with 96.6% accuracy and Fashion MNIST with 87.6% accuracy with a 784 cross 30 cross 10 cross 10 software architecture. Okay. So they note that the selected classification instances, but the network had low confidence. The top two classes doesn't have very different score. That is, the top two output scores are very close. Like the top score was like 0.57, the second score was 0.54. Like it's like they are the neural network is not very sure which one will be the output class. Okay. So such low confidence input is such low confidence inputs yield more meaningful and larger explanation. Therefore will help us for thorough experimentation. Okay. So please note that this point. Okay. So this is for sole purpose of making the experiences larger and more meaningful. Okay, so that's why they have selected instances like this. And now I'll explain the experimental results. Okay, so this is 37 slides. So in these two pictures, the y-axis denotes the feature portion size or ratio. That so the 0.4 in the y-axis denotes the 40% of the all the features. Okay, I'll repeat it again. In these two pictures, the y-axis denotes in these two pictures, pictures in the next slide too. The y-axis denotes the feature portion size or the ratio. So the 0.4 on the y-axis means total 40% features of all the features. Okay.
Feature, what features? Space.
Yeah, this is called, I'll explain that. This is called feature space portion.
Space portion.
Like, yeah, like 0.4 means 40% of total feature space. Okay. Okay. No, now, okay, so wait.
Well, that gives an idea of how big the explanation.
Exactly how big the explanation, how many explanation, how many features are in the explanation. Okay.
That's what,
Yeah.
the size of the explanation.
Yeah, okay. There are two different concepts. I'll explain. Okay. So first picture says that average portion of features verified to participate in the explanation. Okay. So y-axis will denote that the number of features, percentage of features of total feature space that are already verified to be in the explanation. Okay. So y-axis denotes the number of features, the ratio of features that are already verified to be in the explanation. Okay, so the higher value will denote that we have verified more features to be in the explanation, and a low value will denote that we couldn't verify a lot of features to be in the explanation. Okay, so first this is the first graph. So is this clear to everybody, or should I explain it again?
It's okay, but what does it say?
Yeah, I'll just explain that. But yeah. So now, this violet color, this violet line is the previous, the performance of the previous state of the art model by Ignat. Okay. So as we are reaching the timeout limit, 3600 seconds. So we are saying that only 40% of the line is at 0.5 or 0.4, right? So you can say that only 50% of the features are verified to be in the explanation. Okay. But the algorithm proposed by the authors, like use all the algorithms we have already seen, and we can see that they have already in a 1 hour timeout, they have already verified 90% of the explanation to be in the explanation or not. Okay, is this clear? So 90%, they have gone to 90% of the explanation, 90% of the features, and they have verified. Sorry, wait, sir.
No, go ahead.
Yeah. So we can see that after 1 hour timeout, close to 1 hour timeout, the algorithm proposed by the authors have already verified 90% of the features to be in the explanation or not. Okay, but the previous state of the art model only verified 50% of the total features. Okay, to be in the explanation or not. And moreover, like we can see that this is the like naive algorithm proposed by the author, and this green line uses the binary search, then red line uses the information from TLB, and the blue line uses all of them. Okay, something like that. Okay, you get it?
So I'm a bit confused by this lot A. Just to understand this carefully, so in the algorithms that you showed, it's not. I mean, in the first few algorithms, you were starting with the whole feature set as your explanation, and then slowly reducing it. So as time would progress, the size of the explanation would reduce.
Yeah.
Here, the
So
size seems to be growing. That only corresponds to the one of those load bounding algorithms, right? So, what does it mean to say that
sir, okay,
these
I
many
get your
features were
question.
here?
I'll just
Yeah,
explain. Okay, so think
yeah,
of the upper bound and lower bound. Okay, the lower bound thread. So what upper bound thread is doing is like we are going to upper bound thread, and we are taking each of the features, and then we are verifying that if it's in the explanation or not, right? Is that true?
yeah.
Yeah. So as the time goes, so we will be verifying more and more features to be in the explanation or not, right? Is that correct?
Oh, so so we're deciding for each of these features whether they'll be in the explanation or not. It's not
Yeah,
about
exactly. So
the
this is not the
size of
yeah.
the.
This is not the features in the explanation. These are the features verified
Correct,
they are already in explanation or not, right? Okay, is it clear?
correct.
So
So
90%,
how many features have we decided one way or another about?
yeah, sir. Please continue.
No, no. So this is the number of features we've been able to decide one way or another about. Like, as in, so when you're saying that around at 1500 seconds, something like 85% of the features or 90% of the features are under my graph, what it's saying is that my algorithm has, by this point, for 90% of the features in the input space, it has been able to decide whether those features
Whether they
need to
are
be in the explanation or not.
exactly, exactly. This doesn't say
Okay.
90% of them in the explanation. Okay, this doesn't say that. The next picture says that.
Yeah,
We'll,
but
but
it has looked at all the 90% and decided, so for some of them these need to
exactly,
be, and from some of them these don't need to be. Whereas the
exactly.
rest
That's
of the 10% it's not sure about yet.
it's still not, it was not able to verify.
Correct, correct.
Yeah, like if we have give more time, it might be able to verify, but at this point, it wasn't able to verify. Okay, so is this clear to you?
Yeah, it's clear to me, but I don't know the significance of that.
Yeah, like
It's
it's
a particular, you're moving one at a time. Therefore, how far it is to finding, I guess it's a measure of how far it is to convergence. Okay.
and
I think
no,
I think
not really. Like
Well,
this is shows that how efficient are their algorithms. Like if we remember that.
you don't have time, so you have to go to the next.
Okay, okay. So I'll explain it later. Okay, so if anybody. So yeah. So next, the next graph it says that. So it says that like it says the average explanation size after close the timeout. So after the timeout, we say that the previous model returned 82.5% of the features to be in the explanation. Okay. The previous model was like Ignati, previous set of sorry. This one above all the lines, this is the violet line. This is the performance of the previous. This is the performance of the previous set of the art model by Ignati. Okay, this says that like 87.5% of the total features were in the explanation, minimal explanation, close to the 1 hour time. Okay, and this improved to 82.5% at like almost 5% improvement by Waters model, which says that like after the closed 1 hour timeout, the expansion size is 82.5% of total feature space. Okay, so 82.5% of the all the explanations are in the feature space. Of the 82.5% of all the feature space is in the explanation. Okay.
So the authors method were able to get smaller explanation.
Yeah, exactly. 82.5%. Previously, it was 87.5% by instead of dark model.
2.5% of the cases, the benchmarks they were able to get.
I mean, IST data set, I think
Yeah.
they have mentioned. Okay. So now next is pretty easy to explain. So this is the so as we have so the upper line is the upper bound thread TUB, and the lower line is the lower bound thread or TUB. So upper bound, as you can see, is that the upper bound thread is almost getting to 80% of total explanation size. That means that the minimal explanation, as we are end up getting to the close to the minimal explanation, we already verified 80% of them to be in the explanation. Okay. And the lower, as we are proceeding to a lower bound thread, we are constantly getting the CXPs, the contrastive singletons and contrastive pairs, and we can see of them like 50% of them, like this is close to 5.5. So 50% of them are verified to be in all the explanations. So this is the lower bound. Okay, is this clear? So this is the T upper bound and this is the T lower bound. They both of them are reaching UB and LB, right? So this is the value of UB, this is the value of LB. Is it clear?
That is clear, but what does this mean?
So yeah, as time is progressing, okay, so size of the value of UB will decrease, right? And time is increasing, the value of lower bound will increase, right?
Yeah, but there are two things it means, okay? Most of it, I mean, as time goes by, I mean, there is a limit to which how far it can get.
Yeah.
So most of it is done in the beginning, after that it tapers.
They almost because the query exponential like takes more. So yeah, so this is the upper trade is the value of UB and the lower trade is value of LB, and we can see that they are getting closer. Okay, as time progresses. Any question? Yeah.
They are getting closer, yes, but after a point, they're not getting.
Yeah, exactly.
Both of them are there. It's not like they're just, it's a point of information, that's all. So,
Yeah.
if you get any gain, it'll be in the, right in the beginning, the more time.
Yeah, exactly. So yeah,
Smaller
exactly.
and smaller.
So the more we go, because the expensive is the more expensive, so it will slow down the quantities. Okay. So this is the for MNIST. So you can see that this 80% was the value of UB and the 50% was the value of LB almost, right? So the average approximate ratio was 1.6 for MNIST. This is very accurate. We can see this is almost 80% and this is almost 50%. So 80 by 50 is almost 1.6, right? So this is the 1.6 for MNIST. Okay. To get that. So we are returning the minimum, the approximate ratio. So which is 1.6. Okay. And for fashion MNIST, they haven't included in the actual paper, but this was the ratio was 1.19. So at any point we can actually click and to get an approximation ratio. So we are going to 1 hour. Okay. That's the point. We can actually click here to get some like 1.2 as the approximate ratio. We can here stop at 1.8, but after 1 hour, it was the value was 1.6. That was timeout. So they stopped there. Okay.
So regarding the approximation ratio, a smaller number is better, right, for us?
Better.
Yeah, exactly. Then we know how close we are. Like the close we are from the minimum, the better we are, right?
So 1.19 is better.
Yeah. So yeah, exactly.
Whereas 1.6 means the minimum expiration was 1.5 times the actual minimum.
Exactly.
Why was it for fashion?
Yeah, so I have a reason. So if you note this point, so they selected classification instances where the network had low confidence. Okay, so these and the fashion MNIST has only 87.6% accuracy, and this should happen more in the case of fashion MNIST.
And does it mean to say network had low confidence?
Oh, so I explained that. So the, low confidence means that the top two output scores are close. Like when the first output scores was like 57% and then the second one was 54%. So the value was close and the DNN was not too sure that if the value is 1 only. Like they only moved 3% more sure, right? If the value is 100% or 0%, the DNN is always be sure it's definitely 1.
So the prediction of classification of that network was low, iffy. Okay?
Exactly.
It was not classifying that instance with a high probability. And that's why it was able to find better, get closer to I guess the explanation itself would be muddled.
Exactly, the expansion will be muddled up, but the problem is CXP will also be muddled up. But as we are calculating only CXP as singleton and paired, so CXP's burst will be more higher than explanation. So that is what I think essentially reducing the values of approximation ratio. Right, so we can verify less CXPs and pairs than singleton. So that was the size was very low, is very high.
But I think that if you're testing this thing on network with low confidence, I wouldn't put too much value in that thing, isn't it?
Yeah, that's why they said that low confidence input yields more meaningful larger experiences. They haven't defined why, but they say that it will be the case. Yeah.
So you have
Such
low confidence inputs yield
more meaningful and larger explanation. Aiding thought experimentation. That's the whole point. Like if we get all like smaller experiments like this, in here will be very smaller. Like the experiment will always run first. So to be fair, they use this. Yeah.
The larger explanation. That's fine. It explains that the ratio is.
Yeah, exactly. And now it's almost done. Yeah, almost done. So the first one is the original element. The explanation was like the original algorithm returned this explanation, and the bundle explanation algorithm returned this one. So we can see that this is very more likely to be a SU, like if we can see. If we see this also a SU, but towards the human eye, like this is more like a SU. And this is only for shoe, but bundle are more prone to return something that's better for human understandability. Okay. And we can also read a number of pixels in little larger than this one, but still more human readable or human interpretable. Okay? And some of the feature works. So this is the main bottleneck. So currently the algorithm finds an explanation for each input points, but can it do the same for a class of inputs? That is, given a class of inputs, what features will always be in each explanation for each input. Okay.
Hi, maybe sorry to interrupt you, but I had one question.
Yeah.
Will we have time after you talk about the future work, or shall I maybe ask right
Yeah,
now?
if you want to ask me at this point, it's very
Yeah, because you're almost to the end. I mean, you would, yeah, just finish up and then.
and then yeah. You can ask me, Digant. No problem. I will always be available on the WhatsApp or something like that. Yeah.
Yeah.
Currently, the algorithm finds an explanation for each input points, but can I do the same for a class of inputs? I given a class of inputs, what feature will always be an explanation. Okay. Similar problem can be that like the like converse question. Given a set of features and their assignments, which class of inputs will definitely be explained. Okay. Now, can you get some approximate algorithms that can find the explanation of size k to the minimal explanation in polynomial linear time, not in exponential time? Okay. So, like,
So what does which class inputs will definitely be explained means for which you can find the minimum explanation? Or what,
No,
what,
like-
what do you mean definitely?
yeah, like let's say we have given some pixels and some value assignment to it. Then can an algorithm return that if these pixels are taking these values, can the output will always output classification be a true like this? So we are fixing the pixels and the value assignment to them, and then we are asking an algorithm, given these assignments, will the output classification always be a true or will always be a nighttime like this? This is the converse of the first question.
Okay.
Yeah. Okay. Is this clear? Like yeah. Now the authors use line to sort the input features by relevance. We have already seen the heuristic model. This was line. So in another paper we have read through like a bit. Like you will propose an algorithm to approximate FFA or formal feature attribute in an anytime fashion. So what? Okay. So.
No, FFA you don't need to explain.
Okay.
I think Abhinav Sabra will be presenting that is tomorrow at the end,
So-
another form of
Yeah.
explanation, which will be something like FFA.
Yeah.
So
I haven't explained it. So yeah, in a very sort of way, like FMS says that the number of
yeah, in a simple way, I mean, you can say
yeah,
it counts the number of times a particular
feature will be
is
explained.
in all explanations.
Exactly. Number of explanations the feature will be is basically the FFA. The higher the FFA, the more important it is to
Yeah,
basically.
that's another way of that's so okay, isn't that you had a question?
Yeah, like you can
I
ask.
think
Yeah.
before that, does the rest of the class have any questions? Even feel free. I mean, even no question is dumb or clever. Okay? So you can ask any question that you want. Yeah.
Yeah, you can ask question. After meeting this, after this meeting also you can ask. Divan, you can ask.
Yeah, you can ask them offline also. Yeah, go
Yeah.
ahead, Digant.
So, can you go back to the slide where you're showing the shoe and the explanation in the experimental slides? So, my question is, see, the one after, this one. See, so all of this started because we were thinking about safety and safety critical domains and all of these things, right? So, what does an
Yeah.
explanation like this tell us about safety? I mean, see, all that this explanation tells us from what I understand is that if you were to fix the blue pixels to the particular values that they're in the image, and vary any pixel outside of that set to, or any pixel outside of the set to any value, you'll still have a shoe. Does that mean that if I can set the background to pure blue, so that the
Yeah.
shoe kind of blends in with the background, the network still thinks that that will be a shoe?
Yeah, like this also very much depends on the neural network itself. Okay, so neural networks might be a very low accurate model for this, but what you are saying is right. So if this doesn't make sense, right? So if we make everything blue in the background, then it should not be a shoe, right?
It should not be a shoe, but according to the explanation, it will still be a shoe, right?
So this is the okay. So I am not saying this. Yeah. So this is the property of a neural network. Okay. So
Yeah.
is this coming? Hello, hello. Okay. So this is a
I
very
can
much
hear you, I can hear
a neural network. So neural network said that. So what neural net did that it fixed the values to it fixed the colors of these pixels and went through all possible assignments of all the other pixels, and then it said that it definitely has an explanation. So it's completely dependent on the.
So let me understand Digantha's question. Okay, to see if, for the rest of the audience. So, Digantha, you're saying B is an explanation here in this. Now, in
Yeah,
that,
B is an
you
explanation.
change all the white portions to blue. I mean,
Right.
technically, because you're keeping
I don't know what sound coming from.
just let's put it down here.
Okay.
Okay. Then, how can it still be an explanation, right? Because it is.
Yeah, because so
No,
if
no,
it is the
I think it's my
if
pocket,
this
so I
is
think I'll just remove it. Yeah, yeah, okay. Yeah, I think this is fine.
yeah,
Yeah.
so what I'm saying is that if this is indeed an explanation, then it is in fact saying that if I change all my white pixels to blue, then this particular network will think that that image is also a shoe. So then
Exactly.
the question is, what is this explanation telling the user? Is it really telling that the network is behaving like we would expect, or is it telling that there's something counterintuitive and about the network in the sense that it's doing something which we don't want the network to do, or something that we don't expect the network to do?
Yeah, I somehow feel that this, they've just given it as a contract, I mean, just as an illustration. I feel that there must be some boundary, okay, where which are also relevant. Okay, see, what is not clear here when they show in the B is that there might be some set of pixels which are in the Y, which may also be part of the explanation, okay? So they must continue to be white, is what I'm saying. So that is what. So
Yeah.
what you observed was, oh, we kind of interpret, oh, all the blue dots that are part in the shoe are the only ones in features in the explanation. I feel that there is also some pixels which are currently shown to be white, which are very close and they form the boundary. They are part of the feature. They are features in the explanation as well. And their value is white and they have to be white. Okay. That's why, when you said, oh, if I make everything in the background which is shown as white to be blue, will it continue to be an explanation? Okay, I don't think so. And that is not because, here in this explanation, what is not clear is what should be kept as white. I mean, what features are necessarily should be kept as white. Okay, and those features will be which will determine the shape to be a shoe. Okay, if that is the case, then indeed this is a reasonable explanation, isn't it?
Yeah,
Okay.
yeah. So, Digant, I just want to say one more thing. Like whatever said, can you hear me, Digant?
Yeah, I can hear you.
Yeah, so one thing is like in test set we typically have 5,000 to 10,000 data sets, right? In test set at most, but the all possible assignments will like 256 to the power some 784, right? So the point is like there might be some many nonsense inputs that should never be in a test set or something like that. If we make the background whole as blue, this input is completely nonsense, right? It doesn't make sense. But neural network is bound to tell something about it, right? It's bound to tell. So that's the point. Like even if the MNIST is Fashion 87.6% accurate, but it's on the test set, right? But all the input, if we include all the nonsense input, so it won't be able to explain. So what we can actually say that, like what we can actually say that even if we like make those background blue, it will be a nonsense input, but still like the neural network says that it was a it was a shoes only. It was shoe only.
That's where I disagree.
Yeah, like the background.
Because maybe if it does, then Diganta's thesis is correct. Then it is nonsensical. What I'm saying is it is not even clear here.
Yeah, the other thing is
I'm saying they might be in this explanation some features
might be in the border.
And the border.
Yeah.
Right. So some of the things that are marked white might be something that they're demanding should always be white in every image or something like that, right?
Yeah, and there must be some portion, or maybe.
But I don't think that that is the case here because the original image does not have any white pixels. I mean, ultimately, if they're marking something as white and the original image doesn't have any white pixels, that can only mean that it's not part of the explanation, right? Because
Oh,
whatever, I mean, is a part of the explanation, the value of that pixel should match whatever the original image has according to
Exactly. White means we can
So
ignore.
what is the thing? So let's suppose I had a thesis, okay, then what I'm saying is not true. Then how would you explain that if everything is made into a blue, it is still called an explanation?
Yeah, so it's not that is what I'm trying to get at. I don't
That's how it is interpreted.
know if that is
Yeah, exactly. Because this is that we will that input is also doesn't make sense. We will never train the neural network on that input. So neural network behavior might be complex for such type of inputs. So like
correct. But then the whole point of this formal analysis is
yeah,
to
like
really
that.
work out what
That's the whole
happens in
point.
such corner cases, right?
Yeah. That makes sense.
And yeah, and then just by looking at this, it's not very clear what is going on in this corner case. Like I mean,
Yeah, and that's
somebody
also
gives you
that's
the
the reason I
explanation
feel
in
like
yeah.
this precise kind of answers for explanation is not useful.
Maybe-
It has to be some statistical
Yeah, exactly.
kind of a thing, which
Yeah.
Abhinav Sabra will be
Yeah.
Correct. Yeah.
much later.
Or maybe there needs to be something, he needs to talk about the background somehow, which I think is
Also
possible.
with
And I
one.
think we have to stop
Okay,
here
okay.
because
Okay.
it's-
I'll just
Yeah,
talk to you.
sure.
Okay, thanks, let's thank, Aritra, so for his nice talk. And Deepu,
Very nice job.
yeah, you can share, I will make you a co-host and you can share.
Yeah. So was it fine?
Sure.
Oh, it was very good. Yeah. Yeah. Deepro, you.
Like almost 1 hour, 25 minutes.
Yeah, but we started at 10 minutes late, so that's okay. I'll make it up. I think the lunchtime will be reduced a little bit. Deepro, you can share your screen.
Sure. Just a minute.
Yeah. Deepro will also be talking about explainability, slightly different notion and
Is my screen visible?
yeah,
Is it visible now?
yes, it is.
Thank you. Should I start,
You
sir?
can go ahead.
Okay, sure. Good morning, everyone. Thank you for coming here. So my name is Deepro. I'll also be talking about interpretations or explanations, explainability in ML models, but in a different way that Aritra did. We'll see what that means. So I'll be talking on synthesizing parrot-optimal interpretations for black box ML models. These are a lot of big words. We'll slowly decipher what these mean. Okay. Before we go into that, we would like to understand from where these motivation comes to like synthesize any kind of explanation. So what we have is a neural network called TaxiNet uh, that processes camera images to estimate something called cross-track error, which is basically distance of airplane from runway center line. And the airplane then uses the decision made by this neural network based on some image inputs to classify as like if it should raise some alert or like if the runway is clear and so on and so forth. Now, the question that really bothers us is since like we do not know the internals, we have the TaxiNet neural network as a black box model. We do not have any idea about how it functions, the internal working. So we have we do not know how reliable the output or the decision is. The monitoring module might consider factors like say weather, which is basically a function of the number of clouds, time of the day, and the positioning of the airplane to determine the reliability, which is basically raising an alarm or giving clearance. Now there is one monitoring module that requires an interpretable model to understand the decision-making logic of taxonomy.
Yeah,
By
Deepak,
yes, sir.
can everybody hear Deepak well? Your voice is a little bit double, at least here. Can you move back from the microphone a little bit to?
Uh, is it better?
Forward. Yeah, move.
Hmm. Just a minute. Is it any better?
Yeah, it's better. It's better.
Okay. Okay. Maybe I'll raise my voice a bit as well. So yeah. So the monitoring module, which basically wants to take some decisions on based on what the neural network has classified. It's confused if the neural network is really reliable. So it requires an interpretable model to understand the decision-making logic of taxonet. Now, what is an interpretable model? In plain English, it is a human understandable explanation for when taxonet's output is deemed reliable. We will see what an explanation means. What do we mean by these terms like human understandable? These are not formal terms. I have not formalized till now. So basically, this is the motivation. I have a neural network that is given to me as a black box, and I want to understand how reliable it is. Okay. So now we come to the question, what is an explanation? So a neural network whose functioning we are not aware of can be approximated using much simpler structures with maybe more deterministic output, say decision trees, decision diagrams, linear models, etc. They provide a more structured way to represent the very complex decision-making process. And it is very important that we have these kind of deterministic stuff in our hand because they break down the neural network's decisions into a series of very human understandable logical steps. And so we get an insight into the computation paths that bring us from input to output. Here, for the time being, we will restrict our explanations to mean something called bounded multi-valued acyclic decision diagrams. We will see what kind of structures these represent, but for the time being, we will understand explanations to a neural network as bounded multi-valued acyclic decision diagrams or just decision diagrams. Also, we need to keep in mind that we do not have infinite computation power. So the maximum number of decision nodes in any diagram is upper bounded by some constant, say k. Cool. Now getting a bit formal, please ask questions from now on. It's going to get a bit mathematically dense. Please ask questions if something is not clear. Okay, now getting a bit formal. Since the underlying model is treated as a black box, we can only access things like inputs, which is basically a set of features, a subset of the feature space. Maybe we have n features, so the input is basically like a collection of vectors from the feature space, each with a fixed domain di. Am I still audible? Yeah.
Yeah,
Okay.
yeah, you're audible.
Okay.
Yes,
Okay.
sorry.
Yes. Just
You
that
are
I.
little trouble. Please go ahead.
Okay. 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 And I also have some output class O. So for each feature fi, I define a set of partition functions that partition the domain of each feature into several classes. Now, what do I mean by partitioning inputs into classes, and how do these help us in what are like defining the decision diagrams? So basically, an overview of this is given an input, I need to have a function that will tell me which partition it belongs to so that I can decide the branching of the decision diagram that I'm going to construct. So each B basically partitions the domain into finitely many sets. And a multivalued decision predicate we can construct from that B and F, which will basically tell me given any input value iota that will for the feature Fi, that will determine, that will check the partition to which the value belongs. So this is the multivalued predicate that I can define on every value of branching function and feature input, right? So that's what I have formally written here. Given an input iota for the feature fi, the predicate determines the partition to which the value belongs. Cool. And by stylized P, I denote the set of all predicates. Just one notational convention. I'll be using stylized stuff for generally indicating structures, maybe some decision structure, some set, so on and so forth.
Can you use pointer, mouse pointer, like, yeah, like all the
Could you be a bit more audible? I am not
Yeah.
hearing properly.
You could take I think you should use that, or you go, yeah, you should use that. Okay, only then they'll hear you. Yeah, he was saying if you could use your cursor, okay, to point
Yes,
to
yes.
where you, yeah.
Sure,
that's
sure,
what-
sure, sure. Sure. Okay. Yeah. So I was talking about how this predicate depends on the feature input and also the branching function to decide which branch the feature would be into or which partition the feature would get into. And the full set of predicates, the stylized P, indicates the set of all predicates I can construct in this way using some branching functions and the feature space.
You have an example, no?
Sorry?
Do you have an example that you will be showing?
Yes.
Yeah.
Yes, I have an example, but before that, I want to formally define what's a multi-valued decision diagram, and then I'll promptly move to the example.
Okay.
So, as I've said, a multi-valued decision diagram is a DAG over finite set of nodes V, and each internal node V is a predicate, each leaf node is a output, and for an internal node labeled by the feature Fi, here, I choose a branching function from the set of all branching functions and decide its outgoing edges based on the branchings. Maybe an example would help us understand this better. So I would promptly go to the next slide where we have an example for this. We were talking about the taxinet neural network, which I have shown here as a diagram. So we have taxinet as a black box model. And when we have an input image, some pre-processing is done to convert it into a vector of these three things, these three features, P, C, and T, which is basically position of the airplane, weather, which is denoted by the number of clouds, and time of the day. So the input feature are like three things, P, C, and T. And the system outputs one of the two possibilities, to alert or not to alert. And assume, I haven't included the description of stylized P, the set of all predicates here, because that's like too heavy. Assume we have defined like set of all predicates, POS, TIM, and clouds, corresponding to P, T, C, and respectively. Then the rightmost diagram is a legal decision diagram, that is an interpretation. So what does that mean? If the position, if the pos predicate takes an input between 0.5 and 2.5 meter, it will go to the time predicate node. If it's less than 0.5 meter, it would just directly decide it's no alert. And for greater than equal to 2.5 meter, it will raise an alert. Now, in the safe range of 0.25 and 2.5 meter, the time zone will decide where to go, either to alert or no alert based on its own partitioning function. So here the predicates are POS time. The leaves are marked with output nodes, output labels, no alert and alert. And the edges are decided according to the branching function that I have chosen from any suitable class of branching functions. Hope this idea of an interpretation is clear. Any questions?
Yeah.
Might be different from recently, like recently is same thing or like is it something?
Yeah, I'll talk about that, how it's different from your approach in the next slide. So, okay. So other legal I'm answering your question. I'm not avoiding it. Just give me a minute. So other legal interpretations can be this. Explanation 1 and explanation 2 are different from what I have just shown, but they are also possible explanations. I am not really considering the accuracy of their prediction or how complicated they are for the timing. Just I'm saying they can be explanations. Sorry.
So
Sorry.
was your, no, I don't know if, was your question if it is, if this, his definition of decision tree is different from other people who have done it, or was your question about whether there can be several different explanations?
My question was like, we have seen decision tree in ML, traditional ML models, right? It's a traditional, I was asking how is it different like, from that? Like in decision.
Well, in the interest of time, what I'm saying is, I think it is about the same. I mean, decision trees, here, there's a specific kind of thing where he's using multi-valued. Okay, it's actually those predicates are multi-valued in the sense, you know, we can have one of several branching, okay? So sometimes decision trees are strictly two-way branching.
Oh,
He's just kind of abusing or generalizing to make it,
Decision diagram.
multi-way, okay?
otherwise there's.
Otherwise, they're the same, yes, yeah.
Yes.
So the branching is multi-way here. He calls those predicates, but it's a little bit misleading, okay? Because you could say that that predicate, I mean, it's actually the predicate is evaluating whether the value of clouds in here input is in one of those partitions, okay? That's why he gets a multi-value. Sometimes decision trees are strictly two-way partition, but sometimes decision trees can be multi branching also. I mean, that is the only difference. Yeah. Go ahead.
Now coming to the question, how is it different from what Orithro just presented? So Orithro's presentation included explanation as a subset of features, right? While this approach that I highlight, it uses decision diagrams. So in that way, these two approaches are different, right? Now we ask this question. We have just seen these two explanations.
That's
Explanation
not
one.
the only way it's different, okay? Yeah, that is a very crucial way it's different. Explanation, in this case, is just a subset of input features, whereas here it's more complex. It's a
Yes,
printable
entire decision diagram.
model of the original DNN itself. Okay, that's and which is representable as a decision tree. Correct? Yeah.
Yes. Yes. So we have just seen these two decision diagrams as possible explanations. Now we ask a question, are all these explanations equally good? Or maybe we don't know what good means right now. I'm just asking, like, are these equally acceptable or am I equally happy with these two things? I can observe some points. See, explanation one has like less number of predicates. Explanation two definitely has more predicates, more nodes and branches. So it will be very difficult for me verbally to explain this to anyone or even understand that myself. So the human understandability factor comes into point. On the other hand, explanation one is way simpler to explain and understand, but it omits a lot of key features like position of the airplane, clouds. So it might be less likely to predict, it might be less likely to predict correctly. And that is like a very big compromise on the safety of the passengers. So the trade-off is there of correctness versus explainability. Now we come to the fact we haven't quantified formally what these terms mean, correctness and explainability till now. Now we are slowly quantifying formally these parameters. So given a decision diagram stylized epsilon, we have two associated parameters. The first is correctness, which means like correctness in a traditional ML sense. We still, like, it can have a lot of meanings like accuracy, precision, recall, F1, etc. We select delta C as a correctness measure to be accuracy. So what does accuracy mean? Say we have a set of samples IO. So basically input I on which the DNN we want to test the black box has been applied to yield output O. And we want to see our given interpretation model, how does it agree with the sample, with what probability it agrees with the sample. Basically, if I give any input from the sample to the explanation, if it will give me the same output or not. And that is, and so I define this to be the number of points in the sample where it agrees upon the total number of samples. So this is the correctness score. And we can always normalize that between 0 and 1.
Yeah, is that clear? So yeah, so to the audience, So the decision diagram E is what we call in the integrated model. That's also an explanation. That's the kind of notion of explanation that he has. This is the correctness measure for attributed to the that particular interpretable explanation. Okay, is that clear? Yeah. Oh,
Yes.
please go ahead.
Yes. Now I come to explainability, the second parameter, delta epsilon. The function. So by this is again a function that firstly that recursively builds the definition of a predicate. Recursively builds the explainability of an entire decision diagram by first starting with.
That you use understandability. I know that I said this with that, but understandability is one aspect. That's also what you're calling as explainability here, right? So
Yes,
you're using
yes.
Oh,
Yes.
just for clarification beyond example. Yeah, go ahead.
Yes. So firstly, the function explainability delta E should associate with each predicate a weight with some properties. It will reward favorable predicates by assigning them weight more than unfavorable ones. So what do I mean by favorable predicates? This is like a very user subjective thing. Maybe some user will think that, okay, the position of the airplane is more important than the number of clouds. Some people will prioritize time over, say, the position. So this depends on the user preferences. This reflects the user preferences and rewards predicates with uh, more preference than the lesser ones. And also this weight function should be consistent with rewarding predicates with less branching, and which means like this is a very crucial part of the intuition behind explainability. When I mean human understandability, that what we see decision diagram with more nodes, more branching, and like very long paths are very hard to explain because they are voluminous. So we want to reward decision diagrams that are smaller in size, and so we reward predicates with less branching, which will result in more explainable shorter paths. Lastly, for any given explanation E epsilon, we just sum up their weights, all the predicates present there, we just sum up their weights to give the function. One thing we can note here is, given any decision diagram, the labelings should they can or cannot be unique. Like we do not necessarily need to make all the labelings unique. Like one predicate can appear multiple times across the decision diagram. Our goal is to come up with a good interpretation which is correct and explainable.
Nico, you snuck in that thing. Show that example in a previous slide.
Sure.
And how is that relevant for the previous? Yeah. So, for example, on the right side, huh?
Yes.
There are two instances of pause with different branching. Is that what you meant?
Yes. Also
So
two
why did you
instances of
mention
time.
that in the context of that particular slide? So here, first pause has two different branching, okay? That you think of. So the weights can also be different. Is that what your point was?
Yes.
Okay.
Exactly.
Okay.
Yes. And the goal is to come up. Sorry?
I don't get the point that rewards favorable predicate means. Like, what does rewards?
Okay, and in the interest of time, I will kind of say, I think.
Is it Aritro? I actually do not hear him.
Okay, sorry. Yeah, I think I should make you explain it. Aritra was saying he didn't understand what reward means. Okay.
Yes.
I mean, weights and rewards are the same. You assign weights to certain predicates, which is like you're rewarding. By assigning more weights, you're rewarding those predicates, occurrence of those predicates. And the overall score for explainability is computed by adding all the things. Okay, that's how it is. Yeah, go ahead.
Yes. So before going to the goal, come up with a good interpretation of what good means, I will use an example to briefly illustrate what I just said. So yes, this might answer Aritra's query. So maybe so when I assign weights to the predicate, I have to be careful of what the user wants, like how the user sees. Maybe the user thinks that position is a very unimportant predicate as compared to say maybe time or clouds. So I assign 0.3 to 0.3 weight to pause, 0.6 to time, and 0.9 to clouds. So in a way, I'm like rewarding them with weights based on their preferences by the user. So given this decision diagram, the legal interpretation, the explainability score is just the sum of the predicates present, pause, and time, and so it gives me 0.90. Hope I've been able to clear Aritra's question. And now I define S to be the sample where I take 9 pairs of the format that P is less than 0.5, like position is less than 0.5. So it will come to this path, and only at one instance for P is 0.5, it will not come to no alert. It will go to alert. So we can see by the definition that the DNN disagrees with this sample only at the last pair. So the correctness score is 9 by 10, that is 0.9. For all other computation paths, it will go here agreeing with what DNN predicted. So this is the correctness score. This is the explainability score, and this is the correctness score for this sample, this set of samples and this decision diagram. Right.
Which, can you?
Okay, there is something
I
very,
think you should use that. Yeah.
there is something like branching score or not? Branching score, right?
Yeah, the
I did not
question-
hear you
We
again.
have something called branching score, okay?
Hmm.
So,
Yes. So there is a branching score in the sense that like I want to reward function, I want to reward predicates with more branching. That I haven't this is one of the ways of rewarding. I haven't explicitly shown the way of rewarding predicates with less branching in this example. We will see that when I encode it.
yeah, I think the weight itself has to encompass by, you could enforce it by giving, if more branching is not contributing towards explainability, you will give it less weight. That's how it is. Okay, because you're free to give less weight to those predicates which are, branching. That's how it is, yeah.
Okay. Should I proceed?
Go ahead, please.
Yes. So now answering the question, what constitutes a good interpretation? Please note that the pair delta C comma delta E induces a partial order on any set of decision diagrams given a set of samples. And it is very clear because like we know that given any pair of numbers, given a set of pair of numbers, we can induce a partial ordering on that. We call that partial ordering like precedes or precedence, and we say that epsilon 1 is epsilon 2 precedes epsilon 1 if both of the parameters of epsilon 2 are greater than equals to both of the parameters of epsilon 1. So correct, it is as correct as like epsilon 1 is as correct, at least at most as correct as epsilon 2, and it is as explainable as explanation 2. So, and it's an AND clause, so these two need to hold together. And that's how we can define a partial order.
Yeah, I think
Now-
everyone knows the partial order is equal, so I don't think you need to.
Yes.
debate on that,
So
okay?
basically,
So when you have a pair of elements, each of them is ordered. When you have a pair, of course, you have a partial order. Okay, go ahead.
yes. And since it's a partial order, it will always have a maximal element in a maximal chain. We call that maximal element Pareto optimal according to the precedence operator. And max x is a set of all maximal elements, all according to the precedence operator. That is a set of all Pareto optimal elements. And this is our notion of the word good. So Pareto optimality is good. This is what we want to say. Cool.
Yeah, this is important for you to understand. Maybe the example will make it understand. Okay, so it's
Yes.
if I were to, its side is okay. That good. Yeah.
Yes.
You can-
Yes. So this is a plotting of the taxonet model of the interpretations we have in hand in the correctness and explainability space. So please note that the blue points noted here are the Pareto optimal interpretations, and the red areas indicate we cannot have any Pareto optimal points in them, and all of them are maximal in the sense, all of these points are maximal in the sense that there is no other point in the region that like strictly dominated by them, where both of the parameters are more than them. So that's why we do not search for models, Pareto optimal models here. So this is a way to understand, and all of these three things are Pareto optimal models in the sense that they are not strictly dominated by any other model with respect to the precedence operator.
Yeah, in some sense, Pareto optimal points dominate the other non-optimal points.
Yes.
Okay, or all the green region, correct? So that is one way
Yes.
to view it. Okay, so yeah, so they kind of dominate that region. Yeah.
Yes. So now the problem definition comes to E be the set of all interpretations over inputs I and output O, and by all I mean it's bounded by some K, which is by definition finite. We have a set of samples where on applying the input to the DNN, I get the output. Delta C and delta E are correctness measures and explanatory measure respectively. The Pareto optimal synthesis interpretation synthesis problem is given these inputs, these four inputs, the multi-objective problem of finding the one interpretation belonging to the max E. So this is the Pareto optimal synthesis problem. I will keep coming back to this. If you have any questions, if you need to stare at for a moment, please let me know.
So the problem is to synthesize all or one of those Pareto optimal points.
For the timing, it's we need to understand how to synthesize just one.
One. Okay.
Yes, anyone. Yes.
Any questions there? Okay, please go ahead.
Yes, and the outline of the remaining work is like this. We will encode the Pareto optimal interpretation synthesis problem as a max hat formula. We will see what these things mean. Then we will try to obtain the set of almost.
Hopefully, you will explain what the max hat, what max hat is as well, correct?
Yes. I will explain everything, and obtain the set of. This is what we will see. Then obtain the set of all PO interpretations. Give some statistical guarantees on the sample size, because we cannot have it infinite, exponentially too large. We will see some experimental results and conclude with scope for future work and what we did basically. Okay. Now coming to the part that we want to encode the Pareto optimal synthesis problem instance as a max hat formula. Now, what exactly do we mean by a max hat formula? We know what a SAT formula is. Given a Boolean formula in CNF form, we want to find a satisfying assignment to it or report that none exists. A weighted max hat formula is the same in a CNF form, but with additional constraint of a weight function associated with each clause, such that I will end up maximizing the weight, the total weight of all clauses. This is the traditional weighted max set. So the objective is to find an interpretation and assignment of the variables such that the total sum of the weights of the clauses get maximized, in the sense that which clause is 1, like the clause that is evaluating to 1 will contribute a positive weight and the others will contribute zero weight. Here, we will be interested in using a particular variant of this problem. That is, there will be some hard clauses, as in some clauses will need to be satisfied. They should be 1, and some soft clauses in the sense that over them we need to maximize the sum of their weights, of which is positive, which is true, and the false will not contribute anything. Their weights will be not be contributing anything towards the sum. And please note that unlike SAT, all clauses in max set do not need to be satisfied. We just need to find a maximum weight satisfying assignment to the soft clauses. Okay. Now we try to.
No. We need to give a pause a little bit. For the audience, is MaxSat clear? So every clause in the hard set has to be satisfied. And some subset of the clauses from the soft has to be satisfied such that the sum of the base must be maximum.
Yes.
Correct?
Yes.
Okay.
This is the weighted max set problem. Yes. Now we get into the problem encoding. So given a problem instance E, S, delta C and delta E, we want to encode it as some formula where psi E, that basically represents the syntactic constraints of the input set E we have. This should be hard because we need to define the structure of legal decision diagrams. These need to be satisfied. Also, the semantic constraints, psi S, that encode the sample we have in our hand, they also need to be satisfied as a hard clause. And both of them need to be satisfied because these give a structure to the input decision diagrams we have, and they give the behavior with respect to the samples, which is the correct behavior. And then we have the correctness measure and explanatory measure encoded as soft clauses because we want to maximize these particular parameters. We do not need them as hard parameters. We want to maximize them. So like E and S are encoded as hard clauses and the parameters are encoded as soft clauses. Any questions from here?
I have a question. So the phi E and phi S are made hard, and they, which means that must be satisfied, because if they're not satisfied, why? Why are they made hard? Because they are, if they're not satisfied, I guess, X.
So if they're not satisfied, like why we wanted them to be hard is like if they're not satisfied, then we are not defining the structure of the input in the correct way.
The correct way.
So-
There is not even
Yes.
an excuse, I mean, a legal.
Yeah, it could be anything. Like
Yeah.
we want to bound it to be decision diagrams and give some semantic sense to it in sense of like a sample size that will like it will defy that. So it might not be an interpretation at all.
Not a legal interpretation model.
Yes.
At all.
Yes. Should I proceed?
Yeah, I think so. You don't have any no questions.
Yes.
Please.
Yes. Now okay. So here are 4 clauses. I will show how to encode them using one example of this encoding I have. So phi E is the conjunction of 1, 2, and 3 I have listed here. Before going into that, I want to introduce this lambda IP, which is true if and only if node I has label P. Otherwise, it's 0. And how do I ensure that? I ensure that by saying that they should like in this diagram, lambda I pause, lambda 1 pause and lambda 2 times should be true. And also exactly like every node I has exactly 1 label. I ensure that using this clause. So this is node assignment. The second point that defines a correct transition from one node to the other and using the branch C. So transition function, transition variable tau I Cj is true if and only if the transition on node I to J is possible using the branching C, and this is valid. And I encode this using with respect to this decision diagram in this format. So given at maybe the first clause here, the first formula here, like tau I, this part, tau 1, comma 0.5 to 2.5 to 2, that basically gives me this part. And I can reach, here 1 is pause and 2 is time. I can reach this from pause to time using this branch reported to be 0.5 and 2.5. Also, lastly, I want the branching consistency to be maintained, that in this diagram, I want only the branches that the branching functions are using to be possible, and others I have made them explicitly not. So this is a way of encoding the syntactic constraints for my problem. Any questions from here?
I mean, yeah, I guess the branching consistency is also encoding a little bit of semantic thing, okay, that indeed,
Yes. Yes,
yeah,
yes, yes.
take that branch, it has to be in that partition, okay? Is
Yes,
also
exactly.
which is a bit semantic, but nonetheless, I understand what you mean, yeah, yeah.
Yes,
Yeah.
yes, yes. Yes. Now I show how to encode the semantics, the sample size. So basically, what I want to do is I want to I want to ensure that on the sample space, like the samples given, the all the decision diagram should behave correctly, as in given the input from a sample, it would also give the same output as predicted by the decision diagram. Sorry, a DNN. So it's a conjunction of pi I is the conjunction of 1 and 2. And I introduce here a variable m, which is true, like if and only if the node corresponding to it exists on a valid computation path that computes output O on input I. So for that, we need to first ensure that all leaves have valid output labels as samples. And secondly, we need to encode valid computation for samples using the edges. So for all S, like for all samples, I need to ensure key like the leaves have valid outputs with like the leaves are 3 and 4. They have valid output labels on the specified inputs. And when that input is being transformed into the output via some computation path, I need to specify their edges, which I do using the second class of clauses. And the bigger formula is a conjunction of these two. So these are the hard constraints I have in mind for E and S. Now I want to encode the soft parameters that I want to maximize the explainability score and correctness score. First is to show how to encode explainability score. It's a soft clause represented as a conjunction of the following clauses. So there will be the predicate preferences where each lambda dash IP denotes if I has label P is a soft clause with a weight that will be consistent with the user preferences, as I have already spoken. This kind of encourages preferred predicates in the diagram. And I want them to be for all predicates that are reachable from the node. Okay. Next, I want the node usage to be minimized. So here note that UI here, unlike here UI, so UI here indicates if node I is reachable from root. Here I take the complement. So when I try to minimize, when I try to maximize this, what gets minimized is the number of nodes that are reachable from root. So in that way, I reward like lesser complicated decision diagrams. And here all UI complements have weight 1. Right. This is how I define psi delta E. Now, how to encode like the correctness measure? So the correctness measure again will maximize the number of samples matching at the root, and each MIS is represented as soft clause. I want this to be maximized. I want this particular clause to be maximized. So I assign weight I for weight 1 for each clause. I do not discriminate between the clauses. So by ensuring that each this parameter gets maximized, I ensure the number of these clauses get maximized, which means like number of samples matching at the root get maximized. Right. Now, the question is what happens after like I've encoded this. I will pass this maxat instance.
Yeah,
Sorry.
maybe this question is coming the people of, from people in the audience. Why should this encoding? Why should it be finite? I mean, why should you said an explanation, which is a decision tree.
Hmm.
The set of all possible decision tree is finite. Why?
Because it's bounded by
Because first,
a
my
size.
question is, why should this encoding be finite? Okay, in the sense,
Yes.
why can you encode it? This is a formula. So a formula
Yes.
has, a proposition formula has, if there are finite many variables, it is fine.
Hmm.
So then the question translates it to why should every possible decision tree that can be explanation for a given as you have defined, why should it be representable as a prepositional formula in terms of hard and soft? By means of finite number of variables. Why?
Yes. So the answer to this is since the number of predicates is bounded, the sample size is bounded, and most importantly, the size of the decision diagrams are bounded. I can only have finitely many choices. I have finitely many labelings of all decision trees over this, and the number of decision trees is also finite because it's bounded by a finite number. So that's why the bigger propositional formula that I construct out of them should also be finite, and I know how to define them.
You missed one important point. I think just having a finite number of predicates, which is finite, is not enough.
No.
The depth, they assume that the depth is also bounded.
Finite.
Huh? So
yes.
they assume that the depth of the solutions that they are in the search space is bounded. The depth of
yes.
the decision. So if we bound the depth of the decision tree, and if
yes.
The predicates are finite, and the partition of multi-way partitioning is also bounded for each predicate. All these three assumptions, okay? Just the number of predicates is finite alone is not enough.
Yes, because we can have repetitions.
Yeah, the two additional important. They assume that their search space, the decision tree depth is bounded by some constant, and the partitioning is always bounded. Okay.
Yes.
If the partitioning is constant, then we can take real values as we can take real values as a value of a predicate, right? Like time can be anything. Like you can partition something like, let's say 12 into 1
Yeah, the question here is, your question is whether the domain of these values can be real values.
If real values, then the number of decisions might not be.
Can you answer the question? So I think there is the.
I haven't heard the question properly.
The question is if the domain of, for example, their position or time, it's ranging over real values, why will it be finite? Okay, but there is an obvious answer to it. Okay.
I mean, yes. So the thing is, we can represent. Yeah, we can just as a small thing, we can represent real values only. We cannot infinitesimally have real values. No, we'll ultimately end up approximating them using some registers, and that space is limited. It's finite in the sense. So
no, that is not the answer. So the partitioning is finite. Okay, that's the predicate. If you get that, even like in the example that he showed, this was between 0.5, some real value 0.5, 0.2. Okay. So each partition is infinite, but the number of partition, if it is finite, then in the branching is finite. Now, Deepak, that's how we should have answered. Okay.
Okay. Sure.
Okay, go ahead. Yeah.
Okay. So now that we pass this instance to the MaxStat solver to get a PO solution to the original problem, now the question is, why should this happen? I will include a brief proof why every solution of the weighted MaxStat problem is basically also a solution to the PO interpretation synthesis problem. So that the proof follows that way. Let if E be the solution to the first problem, like the Pareto optimal synthesis problem, with measures C and E. Now that E maximizes both of these things, is the weighted sum of soft constraints, we know that, let's assume for contradiction that E is not Pareto optimal. Then there should exist some Pareto dominating E prime with measures C prime and E prime, where either some C is greater than C, C prime is greater than C, or E prime is greater than E. So even if one of these things to happen, then this sum of delta C E prime plus delta E E prime will be strictly more than the sum of the parameters for E, which contradicts the maximum weight assumption for E. So every weighted maxat problem, weighted maxat solution of the problem is also a solution to the PO interpretation synthesis problem. We prove that by contradiction. So we just pass it on to the MaxSat solver, get a result, and that is our solution, required solution. Any questions? Okay.
Go, close it. Yeah.
So is it external maximizing what? Like the sum of weighted sum of soft quantity?
Aritra, could you be a bit louder?
Yeah, he's asking the question about the second bullet in the proof. What do you mean by epsilon maximizes delta C plus delta E?
If we add addition, then like it's total.
So you take, sorry, what did you say?
Weighted sum of soft. Exactly what we are sending to the max set.
Yes, this is the weighted sum of sort constraints. No, that's what we're encoding here. So this is the weighted sum of sort constraints. So whatever I have encoded here, that should get maximized by the SAT solver. So the principle is I cannot have more than that.
Does this function not impose a total ordering already? Like if we are adding
No, not really. It does not impose a total ordering because I'm taking the sum. No.
No. Okay, yeah, so there's a confusion, okay? Vipro, see,
Yes.
MaxSat, okay, I think the confusion is coming from, he's not encoding the maximizing thing. That MaxSat does that, okay? Any solution that epsilon E, any solution E produced by MaxSat ensures that the delta C, the number of clauses in delta C, the sum weighted sum of the constraints in delta C plus delta E is maximized. Okay, that is
Yes.
ensured MaxSat itself.
Yes.
not too sure, but let's say 5,2 is an instance, and let's say 3,7 is an instance. So they both are optimal, right? Because they are like they both might be optimal.
So
But for both, yes, I agree. But if I have like all of them should sum to the same thing, no? Otherwise, something is getting dominated.
Okay, I will first ask the question again. Like let's say 5,2 and 3,7, both are like maximal kind of thing. Like we can input them, but like 5 plus 2 is 7, but 3 plus 7 is 10. So how can you max it return 3,7 but not 5,2? It can return any pair of right? Or something like the sum of weighted constant
If so, okay. So if what are the things you said? 5,2 and 7,3.
7, yeah, like this.
5,
So if 5,
5,2 or 3,7.
5,
so if 5,
7.
Like they are not incomparable. My point is that like they are not comparable. Like they are.
yes, they're not comparable.
So
So
like
if 5,2 is returned, yes.
so epsilon will return 7 plus 3 equal to 7, 3 because 7 plus 3 is 10, right?
Yes.
But 7,3 is parallel to optimal.
But 5, 2, 2, 5 is also 5, 2 is also parallel, right?
Oh, his
5,
question
2.
is not parallel to optimal.
It's not. But yeah, let's continue. But I'm not going to.
No, his question is 5,2 and 7,3 both are parallel to optimal?
5,
No.
2 and
If 5,2 is if 5,2 is Pareto-optimal, then 7,3 cannot be Pareto-optimal because both of the parameters are more.
No, he's saying 3,7. Can that be parallel to optimal?
Yes, that can be another Pareto-optimal solution.
Yeah, but the epsilon always return like 3,7 solution, right? Because
How do you say it will always return 3,7?
Maximizing delta C plus delta E and the weighted sum of constraints.
Yes, in that sense it will return. Yeah. In that sense it will return 3,7. So what if maybe I'll answer this question in this way. Maybe 5,2 is not what we are seeking. We will see, like, okay, I understand your question. So what you are trying to say is what if the SAT solver returns 3,7 as the maximizer thing, and there is another Pareto optimal solution that is 5,2. That's what you are saying, right? Am I getting your question correct?
Yeah, that's a question.
Okay. Yes. So the thing is, yeah, that can happen. And that is why you will see how to synthesize more Pareto optimal solutions. In this specific context, if the Pareto optimal, if the max hat solver returns 3,7, and we know that it's Pareto optimal. Why is it Pareto optimal? I've proven that here. Why do, because that's just a maximizer thing, no? That's
Yeah,
not Pareto optimal in the sense of the formula.
Yeah, last question is if epsilon maximizes this thing, then there is no need of like pair optimal. Then we can actually impose
Yes,
the
there is some need. There is some need actually. That's what I'm going to come to. I'll come to that. Where is that need? Why do we need other Pareto optimal solutions? Yes. So, is your question answered properly? Maybe I can move to the next slide.
Yes, please.
Yes. So, as Orithro asked, like, since we already have a Pareto optimal solution, why do I need something more? I'm just coming to that and how to obtain those sets. So, see, coming back to this example again. So, please note that these three solutions, they have differing correctness and explainability values. Maybe I'm just saying that Orithro prefers this bigger model, like the more complicated one with less explainability and more correctness, more than me, and I'm contented with less correctness and more explainability. In that case, it's very user specific. No, the demand is user specific at how to like. So if I can not give like one Pareto optimal solution to everyone, that might not fit with their constraints, what they want to. So,
I didn't
so
think he will be like. Okay, I think
could
I'll
you?
just discuss it with after the meeting, so let's not wait for
Sure.
this.
Yeah, please. So, what I want to say is like exhibiting the complete Pareto frontier, i.e., the set of all Pareto optimal solutions, enable the user to select what kind of Pareto optimal solutions they want to, what parameters they consider important, what parameters they do not consider important. But the maxat approach just gives me one solution to it. So, how to convert, like, how to obtain the Pareto frontier from that solution I have in hand. So that is the problem, synthesizing Pareto optimal interpretations. Okay, so we cannot check, as the first bullet says, we cannot check all decision diagrams in E, as that takes exponential time. There are exponentially many decision diagrams with respect to predicates and the size. So it's not an option to check for all of them.
For a moment, let's go back. It's important thing that Rita is asking. If you're able to enumerate all possible maxat solutions, okay,
Yes.
wherein the I think the Pareto optimality condition is also encoded as part of the thing, right? That
Yes.
what Pareto optimal, the dominating factor, is I believe encoded in the way that the weights are assigned. Okay. And maybe that detail that we are missing, I think we have to consider this as separately. Okay, so the question is if it is if it is the cost that is as measured by the sum, weighted sum, is maximal, then indeed it is Pareto optimal, isn't it? Huh?
Yes.
That is the way the encoding happens. Okay. And I think that part is a little bit, the detail is missing, okay? Therefore, if you enumerate all possible maxat solutions, then you have all the Pareto optimal points.
That I think makes sense.
Yeah. Okay, go ahead, yeah.
Yes, sure.
And I think the missing piece here is this question that I wrote rightly asked. If the guaranteeing the sum of weighted sum is maximal is indeed Pareto optimal. That's what in the proof that you said. And I think there must be something in the encoding that guarantees that is what I came in, okay, which was not clear from the proof itself. And yeah, which you could take offline. Yeah. So.
I see.
Go ahead.
Okay. Yeah. So picking up from where I left. So I want to synthesize Pareto optimal interpretations that belong to this set of all, like the space of all solutions.
How you
So-
give a more efficient approach, which doesn't need to enumerate all possible
all the
maxes.
solutions.
Correct?
Yes.
Yeah.
Yes.
Please keep
So,
that so that everyone will understand. Yeah.
So given a Pareto optimal solution CE that is pointed by blue, I see that the space actually splits. If I draw like lines passing through it, the perpendicular lines passing through it, it splits the space into 4 regions. We will see what those regions mean. Take this region R1C highlighted by red. So by definition, no Pareto optimal, like this solution, like if there is a solution here, that will be strictly Pareto dominating CE. So like that will be like according to the precedence ordering, it will be more than CE. So I cannot let, like that is not possible by definition. So we will not look into here. This is the space we want to avoid. Also, by the definition of Pareto optimality, it is of no sense to look here because everything is strictly less than like takes like strictly less precedence as compared to this one, the blue point. So the ideal region that we want to look into are RCE3 and RCE4. That is this one, this vertical slab, and this slab, this horizontal slab. And we would iteratively look for them for more Pareto optimal solutions. Briefly, the idea is this. We first initialize, synthesize an interpretation E with parameter CE by encoding maxset formula and finding an assignment. So this step becomes our CE here. And we set the Pareto optimal set to be E, CE. Then we explode these two regions, CE, R3 and R4. Somebody has a higher correctness, somebody has less higher explainability, while the other one being compromised. And if the measure improves, I keep that PO solution and again split the space according to that particular solution into 4 regions and accordingly evaluate. Else, I just adjust the bounds and repeat this thing till a given number of times. So that it will terminate when no new non-dominated solutions are found based on whatever I have updated in PO. So this is the iterative algorithm that efficiently enables me to find a set of Pareto optimal solutions without iterating through all explanations. So this is a brief working of how that works, of how this algorithm takes place. So say I have CE here at this point, and I want to explore the first step. I want to explore the C, what I had reported as like the this region C3 R3. It was R3 reported. I want to explore this, and I find C prime comma E prime as this one, and after that when I explode this, I find C triple prime and E triple prime as this region. So iteratively, I keep on exploring such valid regions. After this step, the valid regions are C3, this one, this one, this one, and this one. And I keep on looking for Pareto optimal solutions in the valid regions only. And at every step, the size of the region, size of the space decreases. I just strike them off as the red spots. Right. So, any question from this?
When do you terminate this thing?
So there is some parameter set that determines what will be the minimum space requirement for me to explore. When I reach that minimum space, I just give that up.
Yeah, so which means that you may not find all the Pareto optimal points.
No, I might not
Yeah,
find
that is
all Pareto optimal.
approximate.
I might find almost all.
Hmm.
I might not find all Pareto optimal solutions. Okay. So now so what we have seen till now, summarizing a bit, that we can find one Pareto optimal solution using maxat encoding, and almost all Pareto optimal solutions in the given space with some like within some area of region. That is the approximation. Now, what assumptions we had so what input we had was E and S. S is the sample size as a sample set. Now one approach can be to like to ensure the correctness. One approach can be, what a very naive approach can be, to like give every like possible input output pair by running them on the DNN, and then the correctness will be like it will be 1. So, but that is not a very viable thing, because all IO pairs can also shoot to exponential size, set of all IO pairs. So we need to put an upper bound on the size of the sample size basically. And how do we guarantee this? We guarantee some statistical, in the statistical sense, in the probabilistic sense, we put some guarantee on the sample size. We do that. So, okay, as I said, exhaustive sampling is impractical for complex systems due to size constraints. So the question is, what bounds on sample size can we put so that that prevents overfitting with very high probability? And the answer comes from something called PAC, probably approximately correct learnability. So, which will guarantee me that with some probability and some which is a confidence, I want to find a solution within some error range with using a sample size m that is bound by a function m epsilon, that is a function of E and delta. This is PAC. We will look a bit more formally into what this means. So a class of interpretations is PAC learnable. I have a sample space with respect to, I have a sample space L, a loss function S, and a distribution D over S. If there exists one function that maps like epsilon and delta to natural numbers and an algorithm A. So when A runs on this M is like bounded in the lower by this ME thing, samples, it returns the interpretation A or some element in the A. I would not say this interpretation because I've just taken this as a, this is the interpretation. Satisfying this probability that it's away in the probability of the expected value of this loss function being away from some minimum value in the set by at most epsilon is bounded by 1 minus delta. So this is the guarantee PAC gives me, and the uniform convergence property from PAC tells me that every finite class of interpretations is PAC learnable. So this is the big theorem that we are going to use, as the paper has used. Any questions from this part? This is a bit math intense.
A lot of details here, okay, but can you, at the top level, say where is it used? I mean, how it is primarily used, I understand, to determine the number of samples, huh?
Yes,
So,
the number of sample size.
the sample size.
What is LD?
So
Sorry.
LD is hello.
Yeah, go, no, no. I thought I think I interrupted, sir.
No.
Perhaps maybe
I was just explaining LD is so given an it is an expectation. So when I pick up an with respect to any given probability distribution Z, I pick up from this class of distribution. So what is like the expected value of this E being chosen?
okay.
What is the expected loss that this might incur with respect to this probability distribution? LD is the expected loss.
Right, that makes sense. Yeah.
Okay, thank you. So now I want to put the statistical guarantee. So what we can immediately find is we can define the loss function to be 1 minus correctness, and that fits exactly into the PAC framework. So as we have said, this minimizes the expected loss. So by the theorem stated previously, the number of samples can be stated in terms of any epsilon comma delta comma epsilon and the size of the interpretation class. So it's bounded finitely by these functions. That is guaranteed by the PAC learnability framework. So this brings us to an end of our topic. That statistical guarantee can be given.
What is capital
Pardon?
E? What is capital E?
What is?
No.
Could you come again?
When we say delta, comma, epsilon, and size of capital E, it becomes below.
Yes, E is the this one. Yeah, E is the set that is given to us, like the set of like decision diagrams.
Set of what?
The set of all decision diagrams.
So it's a class of all possible decision
All
diagrams that
decision
you're
diagrams,
searching
huh?
on.
Yes.
Okay. Class of all decision diagrams
Yes.
of that particular size and branch.
Yes. 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 All right. So now we move to the experimental results, what we have in our hand. So firstly, like this demonstrates that um, we analyze this trade-off between correctness and explainability for decision diagram with 7 nodes. Like I bound K to be 7, and these plots show how increasing the predicate counts. First, I begin with 3 predicates, decision diagram on 3 predicates, decision diagram of 4 predicates, and on 6 predicates, affix the solution space. So, and we have taken epsilon and delta to be 0.05 and 0.05 respectively, and like same thing only. So here each point represents a Pareto optimal interpretation satisfying our constraints. And this is how like the red parts are the ones that we have chalked out to be like the wrong regions which will not contain any Pareto optimal solution. And so this is the set of blue points here are the Pareto frontiers. This is a Pareto frontier set or the set of all possible Pareto optimal solutions within some given range. So yes, this is one result. This is one demonstration of what we wanted to do of the algorithm we were taking.
And just synthetic examples, not from MNIST or anything. Huh?
Sorry?
Here they were just were using some synthetic examples of DNA.
So they were using the taxinet, as I've discussed earlier, the taxinet neural network they were using.
What? Which one?
I have discussed the taxinet neural network at the beginning. They were using that.
Oh, the taxinet. Oh, the taxinet. Yes. So everything was performed with, I got it. So for the taxinet, then they use, they performed this experiment for taxinet with those number of predicates. Yeah, okay, I got it.
Yes, 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 yes.
Okay, and?
Yes. And secondly, we have the computational efficiency part. So we run the experiments. The paper has run the experiments on different sizes that I've specified here, like what kind of sizes they have taken, the bounds they have taken, the input they have taken. And these are some statistics regarding that. The peak memory reaches 1.8 GB. The average iteration time is 14.3 seconds. And total PO interpretation found is 217. Like when we wanted to check, like that is what we found. Now, the runtime distribution tells us that it's very fast, like less than 20 seconds for 80% of inputs, moderate for 15%, like 20 to 60 seconds, and it took more than 1 minute for 5% inputs. And we also observed that the complexity depends, since we are differing the predicate counts a lot. What we can say is the complexity depends more on the solution space structure, how the solution space looks, rather than the number of predicates. So this is the observation they have. This is the experiments they have carried out.
Yeah, can you repeat that? So, I mean, it's not the number of predicates, but the size of the solution space. Is that what? Can you repeat what you said? Yeah.
So the time complexity of the algorithm, how we run it, that depends more on the solution space structure. Like we could not, so when we wanted to infer some relation with the predicate count, we could not do that. So they just make an observation that the time complexity will depend more on the solution space, of how the solution space is structured. What kind of possible interpretations can the solution space have, more than the number of predicates.
Yeah, but the number of predicates, I mean, increases the solution space also. The more number of predicates, the more also, no?
No, not necessarily, because we can have repeated predicates, no? So,
yeah.
I mean, the number, like the same complex structure I can also use with same predicates with at different node points.
Do that. But if you had more number of predicates, then a more number of decision
solutions. Yes, I could have more number of explanations. Yes, yeah, that is something I agree to. Yes. So now we have like I'll just briefly speak about what I have just discussed. We had a novel framework where we did Pareto optimal interpretations. That guarantee. So the good part of this exploration is that we do not need access to the internal working of the black box. We do not need training data. We do not need testing data, all the details. And we have decision diagrams which are very simple to understand as explanations. It gives us formal guarantees in the terms of that sample size is limited. We do not need to access the black box too many times. And the correctness explainability trade-off is like properly understandable. Also, we have like a scalable encoding in the sense that weighted maxat formula itself is like well defined. How do we convert instance of at optimal interpretation synthesis problem to a weighted maxat problem? And also we can make it efficient. We have made it efficient by avoiding brute force search. Okay, so this is like a conclusion of what we just saw, and we have a couple of future directions that. So what one thing we have restricted ourselves is to like we have only thought about finite classes, like the class of all interpretations is finite, is bound by some number. What if that is infinite, like maybe finite VC dimension cases, like or OMT extension, something like that. So what happens when we do that? We do not know. Also, when we extend that beyond static structures like say decision diagrams, linear models, and we take like dynamic structures, we take more probabilistic structures, what happens to that? We do not know that. And another thing is what happens if we, whatever algorithm we are like splitting up the regions into 4 spaces, how about we do that like on parallel computers, we parallelize our explanation. So maybe that will help us speed up the computation a bit. So these are future directions of work, and I think that's it. Any questions?
Yeah, I have a couple of questions.
Yes.
Wait, so I mean, one thing that I wanted to ask is where do these predicates come from? I mean, we are using in the examples we've shown some predicates and so on, but
Yes.
there's some magic numbers in those predicates, and it's not clear where they are coming from.
Sure. And maybe go back to the example itself.
Yeah.
Yeah. So this one you're talking about when I'm encoding that.
Correct, correct. So, I mean, this 0.5 and 2.5, all of these things are fixed, right?
Yes. So
I mean,
so position
even when you're searching
is
through the
POS.
specification diagrams,
Yes,
these are
yes,
all
yes.
fixed.
Yeah. So this position thing, this position predicate, its domain, like, it's an input, right? So its domain is fixed from like it can take any meter variable. So what I can do is like break up the partition the domain of position into classes, and that partition is shown using these numbers. So if you see this is an
Right,
exhaustive
right.
partition.
That I understand. It's a search partition, but how did you, I mean, realize that the class boundaries need to be these specific numbers, right? I mean,
Yes, so this
I
can
could
be
have
arbitrary.
instead,
Yes, you
yeah,
can
but what
you
in
could
the
have done
what
anything.
is there in the algorithm that decides this? Is it something that
There
the
is
algorithm decides, or
no, that the algorithm does
so
not decide. The
there is an
algorithm,
expectation that the user will do this in some sense?
yes, this part will be entered by the user.
I see.
Yeah.
Okay, sure, sure.
I think that's a very good question because, yeah, so that is given as an input. And how you come up with that the partition, basically the predicate is defined by how you partition the domain. And that's what coming with the predicate means, yes. Yeah. So that has to be done by domain knowledge, I guess.
Yes. So one thing I'll like to show here is, so we take these two positions. Uh, is this visible? I think
Yeah,
I
yeah,
cannot
yeah.
zoom in more. So see these two positions, their partitions are different. One has partition less than 0.5, greater than 3.5, and less than 2.5, and another has like greater than 2.5 and less than 2.5. So these are different partitions.
Yeah, but
Yeah,
I
but then
think
all of that is, I mean, the fact. Sorry, go on.
Yeah, but your question was, how do you come up with these things? Because the predicates.
So
see, the past-
here
past
it's
is-
assumed that the
past
user will use, yeah, the user will input like
The set of all
good,
possible
yeah,
partitions.
yeah, yeah.
So basically, the user tells that, okay, I mean, I'm happy with branching at the point 0.5,
Yes, yes,
2.5,
exactly,
3.5, and any combination
exactly.
thereof.
Yes, yes,
But
yes.
then the search space does not cannot, like, for example, insert a branch at 1 because that's something the user didn't mention.
Sorry, come again.
So I mean, for example, here if the user did not mention that 1 is a point at which you might want to break up another possible partitioning. If the user had not mentioned it, then the search procedure, when it's going through all possible decision trees, will not ever think of introducing a node that branches
Yes,
based
exactly,
on something like less
exactly.
than 1.
That will be
Yeah,
omitted.
yeah.
Actually,
Correct.
I mean, like if you look at it, like so, like it is a very, matlab, very rigorous expectation in the sense that there will be only 5 clouds. So if there are 6 clouds, like even in this diagram, the decision diagram does not know where to go.
Right, right, right. Exactly. Yeah. So another question that I had was, see, this tiny taxinet. From what I mean, I don't know if it's the same thing as tiny taxinet or not, but from what I'm aware of in terms of the data sets, this is an image to kind of how far are you drifting off the center line of the runway kind of a regression problem, right? So the input
Hmm.
space are images, and you
Yes,
mentioned they're doing some kind of pre-processing to come up with this PCT. There have two
yes,
questions. One is, of course,
sure.
what is the kind of pre-processing that they're doing,
Uh,
and yeah. So maybe firstly answer that. Yeah.
Sure, sure, sure. So they do not exactly mention what kind of pre-processing they do. They just mention that they get a set of images and convert it into a input feature space of these 3 things.
Correct.
So
Okay.
I would like to assume maybe some kind of I don't know. They do a couple of CV stuff like understanding the boundary and all those kind of things.
So you mean non-neural network based CVR, because otherwise it will
Yes,
not,
yes, yes.
because
Yeah,
otherwise
yeah,
you
yeah.
shift into
Non-network based.
explainability problem.
Yeah.
Uh, Right.
But
Yeah, I see. I don't know if that's a typical taxinet model, but sure. Yeah. So the other question, yeah.
Regarding this PCT question that you had, would it be the case that it's the other way around? I mean, usually you have in your domain, probably the thing is expressed in terms of PCT, and when you actually do the build the DNN, the PCT will be somehow encoded in the thing or no? Huh? Sometimes that also happens. No, there'll be some higher level inputs
Mhm.
which are then encoded, embedded in some vectorization, vector model. But is
Yes.
this still
Yeah,
probably
I don't know. In this case, I think, see, in this case,
not
when
the
you're
case?
training the DNN, from what I can at least tell, all that we have access to explicitly are a bunch of images and some marking or some labeling for each of these images as to how close we are to the central line and so on, right?
Hmm.
So this PCT is not there in the data set, which means that we cannot directly train the DNN to produce these PCT values or encode these PCT values
Yes.
explicitly in some of the internal layers, right? But it might be happening implicitly, as in, maybe the DNN is implicitly learning to analyze something like some values which are related to
More
these
worthy.
PCT
Yeah,
values,
yeah,
but
yeah,
then,
yeah, exactly.
yeah, but to extract that out of the DNN would be non-trivial, I think.
Yes. And that probably also contributes to the taxinet entirely being a black box model, na? Otherwise, like if I knew that, I could just extract that.
Yeah, of course. Yeah, yeah, yeah. I mean, if you're talking about extracting, you cannot think in terms of black box models, right?
Yes, yes, yes.
Um, so, and two more questions. So, one, the second
Sure.
question is, one question is that so this PCT, I mean, the input dimensions is very small, right? It's 3-dimensional, but the original image was
Hmm.
some much bigger input dimension, right? I
Yes,
mean,
yes,
do
yes.
you think that this approach is fundamentally limited to small input dimensional cases? Because I mean,
Okay.
if we have something like an image, like an actual image, and if I have a network that is just taking in a raw image, not some pre-processed thing,
So
is
one
there
thing
any
is
hope
that
of, yeah?
yes. Sorry. Please go on.
No, I'm just saying, is there any hope of adapting something like this in that
So
sort of a
yeah, I
situation?
had 2 things in my mind. I was thinking about this. One thing is for that, like so one very I would not say impractical, but a limitation of this approach is that the formula sizes themselves are very big. So the moment like PCT, like the predicates also shoot up, they will also like they will only increase in the length. No, so that will lead to the interactability further. And the second thing is like as I've discussed, we could parallelize stuff. I don't know to what extent we can parallelize things, but I think like one way of adapting this to bigger things would be like just to parallelize stuff.
Sure,
Maybe
but I mean, that is
the
the
regions.
computational complexity side of things. I'm
Yeah.
thinking more in terms of how complex or readable the explanations will be in the first place. Like, let's assume that we have all the computation in the world. Even
Yes.
even then, would this GT be readable at all?
Yeah,
Sorry,
I see the BCT, the number of predicates will definitely not only increase the size of the encoding, okay, because given a certain depth and a certain branching depth and so on, that's what determines the size of the encoding, okay, of this one, right? And then that also determines the size of the search space, okay, solution space, right? Both of them. So I think this is only scales for very small number of predicates.
Right, right. And I mean, yeah, I mean, basically it will scale for situations where a decision tree is a reasonably good model class in the first place.
Yes.
So, one final question I had
And just
was
for
that,
Uh,
one,
see,
someone
sorry,
I'm
so there's some noise from someone's end, I think. But
yes, yes,
anyway,
yes. I don't hear properly.
yeah. I'll try to. Yeah, sure.
they're
Um,
muted now. They're muted now.
yeah.
Okay. So,
Yeah.
yeah, why don't you ask a question? We start at 12:15, we are running for 10, 15 minutes late.
Okay.
Yeah,
So just one quick question. So I mean, see, when you talked about the pack guarantees, right? So
Yes,
LD was sort of the expected loss under
yes,
whatever distribution we're sampling it from. I mean,
yes.
one
This
question is,
one,
okay, what is the distribution whenever they're doing this learning? What is the underlying distribution that they are working with?
uniform.
Secondly, I mean, see, when they're actually looking in the Pareto optimality condition, when they're actually measuring quote unquote correctness, they are, measuring an empirical accuracy, right?
Yes,
Which will be an estimate of LD. It will not necessarily be the actual LD, right?
yes.
So, I mean, that estimate itself will have some loss within this pack framework, right? I mean, there'll be
Exactly.
some confidence interval with that estimate. So, I
Yes,
mean,
exactly.
if we are doing fewer number of samples, then there is this epsilon and delta coming from the pack framework in the first place, right? So, if we're doing fewer number of samples, then is any of these things being accounted for in the correctness, or are we just fixing some epsilon in the first place, and
We are fixing
we're
exactly.
happy,
Yeah, yeah,
and
we
then
are
we're happy
fixing
with
that
whatever,
exactly.
whatever some empirical estimate of LD that we're getting with
We
that.
are fixing these values as in the experiment also I've shown. We are just
Hmm.
fixing these things to be 0.05 and 0.05. That's it.
Right, sure.
And
But then
whatever,
the fact that this LD that we're going to estimate might be
yeah.
different from
So
the
yeah,
actual
that's
LD.
exactly
That is not
that's
that
an
is not
approximate.
really captured in the Pareto optimality condition anyway, right?
No, that is not in the Pareto optimality condition.
Okay, yeah, sure. So and what is the distribution D? What distribution are they
They
taking?
suggest taking uniform.
Right. Because I think, I mean, that will matter a lot, right? I mean, uniform distributions of images is I mean, yeah. Again, I'm thinking in terms of images, but it's like it's not a very good representation of the dataset distribution, for example, right?
by the way, what was the
Yeah,
size
that's
of
what I
the sample size that they, yeah, this is something orthogonal, okay? That I understand. This is itself, these distributions that are not taken account in the encoding. But the size of the sample set will definitely determine the size of the encoding also, right?
Yes,
Yeah.
yes.
So what was the size that they chose for their experiments?
Uh, so for this experiment,
Uh,
yeah. So they have a couple of the slides. I just give me a minute. they chose like so I remembered the size of the decision diagrams to be around 800 to 1000. I do not exactly remember the size of the decision diagrams. It was like an approximate thing, around
Yeah, I
800 to
don't-
1000 nodes.
Sure,
Yeah,
but
I-
how many
Samples.
samples are they
Oh,
considering?
acha,
Decision
how many
diagram might be
samples
small,
there?
but
Right,
yeah.
right. So for
Because
samples,
I mean,
I don't exactly recollect the number.
sure,
Okay, we can look it up.
Don't
Yeah,
exactly
because
recollect the number.
sure.
I think that's the only thing. I think the size of the samples is all that is figured in encoding, in the encoding of MaxSat.
Yeah.
Hmm.
And the
Because I mean,
quality-
if they are using a large number of samples, even if the decision diagram is finally very small, the encoding itself will be very, very big, right?
Yes.
Yeah.
Okay, I think we'll have to, any other questions from anybody? Huh? I think that question that Eritro asked about, the solution that, it's related to the theorem that you proved, that you showed, and this thing of whether enumerating all possible solutions, of course, if you enumerating all possible solutions, you can then, it will include all the Pareto optimal, obviously, okay? But that question will have to be.
My question was like, if we are adding things, like then why not like make the correctness clause and correctness and equal together, like.
Yeah.
Sorry, I can't hear the question. Can you
Me
please
neither.
repeat?
No, I want to, there is this question which I don't think we'll be able to answer here. Aristo's question was, if you just, MaxNet is only maximizing, it produces, the weighted sum, okay? It gives the weighted, all solutions for which the weighted sum is maximum, okay? That's how it does. MaxNet can also be asked to give solutions of a particular cost, okay? There is a feature like that. Now, the question of Aritros was, I'm only going to formulate the question, and then, which I don't think was completely, very satisfactorily answered, was if you use the sum of weighted sum, you optimize the weighted sum, that doesn't necessarily the solution will be a Pareto optimal solution. How are you ensuring that? Was your question, correct? Yeah?
Like,
Yeah, okay, so there is that issue of how exactly is the encoding also taken into account that the solution that MaxNet produces is guaranteed to be Pareto optimal, okay?
So I think that if you take a weighted sum, it will
Yeah.
be Pareto optimal. It's just that when you're choosing the coefficients of your weighted sum, you're implicitly making a choice about which Pareto optimal solution your MaxNet solver will produce.
like,
okay.
we are adding things, it will be always a Pareto optimal, but we are like removing other Pareto optimal solutions.
Yeah. And then there is, I mean,
Yes,
ultimately
that
there's
is
no other.
yeah. That is what I agree with. We are not technically removing other Pareto optimal solutions. What we are doing is we are choosing a Pareto optimal solution using the max hat drop procedure. Then we try to evaluate other kinds of Pareto optimal solutions too.
Correct. Yeah. So there's an iterative procedure, and you'll be covered a lot of it.
MaxSat, you could say it gives one, you can enumerate all possible. You can, so then you have all possible.
No, then we are adding plus delta C plus delta A, right? Right, so we are adding this. So if we are adding this, then we can club the MaxNet query to correctness plus experiment. We don't need to another different words like that.
No, that I don't agree with.
I'll probably
Yeah,
give some-
okay. So anyway, so I think partially it is answered. So, Deepro, and I think I want to understand what exactly your question is, since you don't understand that. Okay, so, good, thank you, and, the next, talk will be by, Pranika on, enhancement to the node merging abstraction, that you heard, in the class, okay? So, can. Yeah, you have to send it to me, yeah? You have to mail it to me and then. Thank you, Deepro. This is a good talk.
Thank you, sir. Thank you, everyone.
Thanks. Really nice talk.
I'll just go to the room and then join for.
Yeah, please. You sent it? Huh?
There's a pointer also if you want to use that.
Yeah, but that won't be visible, so you might as well. Either you can sit here and then.
Okay, so you're well like pictures. Like. I will probably leave it low. I'm not sure. Yeah, but okay, you can actually hold it and speak, but. And the mic's also off, so you need to turn it on, So this is off, this is mute, and this is on, okay, so I will turn it on.
On the screen over here, or can I sit and change the screen?
Well, if you sit here, you can use the cursor, okay? Otherwise, you'll
The
have
others
to,
won't be able to see.
yeah, the pointer, they'll not be able to see. So whichever way you want to choose, yeah? Yeah, please. Yeah, go ahead.
Okay. Hello, am I audible?
The people on the net, is she audible to you?
Yeah, yes, sir. She's audible.
Okay.
Yes.
Okay, so good afternoon. I'm Parnika and I will be talking about cigarette. Cigarette is an extension of cigar which we have learned in class. So I'll be starting right now. So for the introduction, we will be talking about DNNs. DNNs.
Is she audible?
Hello.
Hello? Is Pranika audible? Someone?
Yeah.
Yeah, she's audible, yes.
Okay, so I'll continue. So we will be talking about DNNs or deep neural networks. So these are networks composed of multiple layers of interconnected neurons or nodes, and each connecting edge is associated with a weight and bias. So these are used in real-world applications like speech recognition, autonomous driving, and other critical systems, such as airborne collision control, etc. So the reliability of these DNNs are a valid concern for security reasons. So there are some possible factors which undermine reliability. So the first one is generalization gaps. So we train the DNNs on data which can be biased. This can also cause overfitting of DNNs to that specific data. DNNs are also vulnerable to adversarial or backdoor attacks, which can make them behave in a way that is undesirable to us. So as a solution, something called formal methods exists, and they use mathematical techniques to formally model, define, and prove the desired behavior of the DNNs. So this provides guarantees about its correctness, given there are specific conditions. So moving on to neural network verification, NNV checks if a DNN satisfies a given property for all inputs in a region. So typically the negation of the DNN's desired behavior is taken as the property Q. So Q is the property that we want to verify. We take the negation of the desired behavior so that if we get a SAT, it means that a counterexample exists. And when we get unsat, it means that the property holds for all valid inputs. So what we are looking for is an unsat. SAT means that there's something, there is some input that allows the. Sorry?
Sorry, it was my mistake, sorry.
Yeah, I think we should avoid crosstalks. Was that a question or was it a crosstalk?
No, like it was a cause, like my mic got unmute. Sorry, extremely sorry for that. Yeah, I was going to room.
Okay. Can I continue?
Yeah, please.
Okay, so basically what we are looking for as an output for our NNV is an unsat. So there are some challenges in NNVs. So one is scalability and complexity. So when the DNNs sort of exponentially increase, there are more neurons and they get more computationally expensive. So we have come up, the people have come up with something called CIGAR, which is counter example guided abstraction refinement. So this is actually something we have learned in class, but I will give an overview of it just in case. In order to verify with reduced computational cost, CIGAR is going to use a simplified version or an over approximation called N prime of the original network N, and it's going to refine only when there is a spurious counterexample encountered. Throughout the presentation, I will refer to the counterexamples as X0. So this over approximation of the DNN is going to encompass all behaviors of the original network N and possibly more. So this is the flowchart of CIGAR just to make it clear. I'll just go through it once. So we start with the original network N, and we are going to use a certain function called abstract N, which is just basically node merging. And then we are going to get the abstract network, which is N prime. We are going to then feed N prime into a verifier. So in this case, the underlying verifier is Marabou. So this is going to give us two possible outputs. One is unsat, which is what we actually want, which means that the DNN is behaving as we desire. The other output is SAT and a counterexample X0. So this means that the counterexample is going to satisfy the property Q. Like Q is the negation, so this is not something that we prefer. And since it satisfies it in the abstract network, we are then going to check whether it's a spurious counterexample or a real one. So to do that, we are going to check the value of the counterexample on the network N. So if it does satisfy Q in the original network as well, then it means that it's a real counterexample for the network N as well. So this is something that we will have to do later. In case it is spurious, which means that it doesn't satisfy this. So it just appears to be a violation in the property that we desire. But in reality, it's not really a violation. It's like a false positive. So this means that X0 is spurious. We then go on to refine the network N prime, which this basically means that N prime has really loose constraints. It's not accurate enough to describe N. So these are the shortcomings of CIGAR. So when it comes to CIGAR, we are talking about node merging over here. So CIGAR NN's approach for verification has two main components, abstraction and refinement. Here, abstraction is basically merging neurons, and refinement is using the spurious counterexample to guide the refinement. And we just split the merged neurons. So the issues with abstraction is that it reduces the size and complexity, but at a certain cost. This abstraction brings in the increase of spurious counterexamples. So how does that happen? I will be explaining about that shortly. So as a result, there are too many refinement steps that have to take place, and this makes the verification slower than checking the original network directly. I will give an example of this soon enough. So in conclusion, the current abstractions are less precise, and they don't really exploit the flexibility in property encoding. So there is a method to sort of overcome the issues with cigarette, and one of them is property abstraction. So going beyond vanilla network abstraction, Cigarette improves on the standard cigar by abstracting both the network and the property. So we saw that in cigar NN, we are abstracting and refining the network. In Cigarette, we go one step ahead and do the same for the property as well. When I say property, I mean the property Q. So the key insight is to use a specific constant D to tighten the property Q conservatively. I will be talking about this this constant D very soon. So to compute this constant, we use the difference between the bounds of the network. I will be showing a simple example soon enough.
Yeah, at this point, I mean, I'm sure when you show the examples, it will be clear for people that, you don't recall that the node merging abstraction method, the property has a particular structure that is speed y less than or equal to c. There's a single
Great.
output and y less than or equal to c. So here, when Pranika says she's tightening the abstraction, she will explain it later that it will be doing something like y is less than or equal to c plus d and then d. So this same statement is very much is relevant to there is some parameter d that she uses to make it tighten it, what she calls as tightening, which she'll explain later. That will also reduce the spurious example. Okay.
Yes, so I will be explaining it with an example soon. So the benefits of this property abstraction is that, first of all, it reduces the spurious counterexamples. And this is actually what we're looking for. Since there are less spurious counterexamples, there will be fewer refinement steps. So this also gives another advantage which speeds up the computation. So it has been tested on several benchmarks like ACAS, XU, and MNIST, which I will also talk about. So just to summarize, cigar is network abstraction. Cigarette is an extension of cigar along with property abstraction. So this is the former's problem statement. This is actually everything that I've said just in a formalized version. We will be having a verification query of the form n, p, q. N is the original network that we have, and the output neuron is y. And p is a set of input constraints of the form x belongs to a, b. And q, as I said, is the negation of the desired property of the form y is greater than c.
Not actually, Q is the negation of the original property. The original property was of the kind y less than or equal to c. So the negation becomes y greater than c. Correct? Yeah.
Yes. So the form
The
y
original property that is applied was y less than or equal to c, and the negation was y greater than c. Okay.
Yes. So whenever I refer to q, I refer to something of the format y is greater than or greater than c. So this format usually encodes most of the widely used constraints. However, there are some things that it might not encode. For example, temporal or logical sequences, sequential constraints, or something like probabilistic constraints. There will be some transformations that have to be applied in case we want to encode it of this form. But going forward, we will use this, y is greater than c. So finally, the goal is to determine whether there is any input x from this set of input constraints P, such that the original network violates Q. So if yes, it means that a counterexample x0 is found. Otherwise, it just means that the property holds for all inputs, and this unsat is what we are looking for. So the traditional approach is cigar NN. The optimized approach is cigarette NN. So there are a few technical challenges that comes along with this verification. So DNNs with many neurons are very computationally expensive to verify. And spurious counterexamples also pose a threat. Abstracted network n prime, since it's an over approximation, it includes behaviors of n, and it may allow behaviors which are not present in the original network as well. So these are like undesirable behaviors. So this leads to unnecessary refinements and slower verification. And when it comes to tightening versus soundness, we need to ensure that the property, the abstracted property, Q prime, also remains an over approximation. And it must not rule out any real counterexamples to prefer the soundness. So another one is, while splitting the nodes again, we need to find out which abstract neurons are influencing or bringing up the spurious examples. So we have to identify neurons that significantly impact the output. And this is usually non-trivial. This is beyond the scope of the presentation and might require methods like gradient-based or bound-based analysis. So moving forward, I will be using this original network N to explain what is going on. So we have the input X, which goes into the input layer, which I'm denoting as the neuron N1, 1. And it has two outgoing edges, one with the value 10 and one with the value 1. And the hidden layer is composed of two neurons, N2, 1 and N2, 2. So N2, 2 has one outgoing edge with the weight 4 that leads to the output neuron, which is N3, 1. I will be referring to it as Y, just to sort of reduce confusion. And the first hidden layer neuron has an outgoing edge of 3. So this is a very simple network that can be used to explain the entire thing. So the verification query is of the form N, which is the original network. And the input constraint P is that this input should be within the range 20 to 21 with both numbers included. And the property Q that we're talking about over here, remember that it is of the form Y is greater than C. So over here we have N3, 1 is greater than 800. So C over here has the value 800.
That's the negation of the.
It is the negation of the desired property.
Yeah, that's the negation. Yes.
Yes, so this is the cigar algorithm that we have gone through in class as well. So this is just a formalized version of the algorithm. I can go through it if required.
No, I mean, when you go through quickly, okay?
Okay,
So
sure.
this is the same, when she refers to CGAR, she means CGAR in, that's the same node merging extraction. Yeah, so quickly summarize for people that just to.
Sure,
Yeah,
sure.
I think it will be useful.
Okay,
Please.
so cigar is an iterative algorithm that aims to converge towards a representation that is accurate enough for verification while also remaining computationally tractable. So first we begin with abstracting the original network N and obtaining N prime. And then we are going to verify the query with N prime. And if we get unsat, then we just return unsat since the property holds for all input values. Otherwise, we will get the output sat and we are going to extract the satisfying assignment X naught, which is the counter example. And then we are going to check if it's spurious. That is what this block of the code does. If it satisfies Q in the original network as well, then it is considered a real counter example, a valid one, and it is not spurious. So we just return sat and X naught. Otherwise, it means that X naught is spurious. So we're going to continue to refine X using the counter example. So again, it is guided by the given counter example. And then we obtain N prime. So again, we just we take N prime as N double prime, and then we go back to step 2. And eventually we get to an unsat or a sat. And that is the end of the algorithm. So this is an example of how the node merging works. So if you all remember, there were categories which are pos, neg, inc, and dec. So here it can be seen that these two, the nodes within the hidden layers, N2, 1 and N2, 2, both belong to the same category. So node merging can be done on these two. This is the abstraction part of cigar. And so after we merge the nodes, we get this node, which I'm going to call N2, 1 plus 2. So this is the abstract node that we have finally. And if you remember, when it comes to taking the weights, the incoming weights are, we take the maximum of the incoming weights, which is 10, as seen over here. And for the outgoing weights, we sum the values, the individual values, and we get 7. So this is N prime, which is the final abstracted network. Now, when it comes to the property Q, where Y is greater than 800, there is something that we notice. So for example, let's take the value 20, which is within the range that we have given in P. So if you notice for the value 20, in N prime, once we propagate 20 through this, so we get 200 into 7, which is 1400. In the in the abstract network, we see that the value 1400 is greater than 800. So what does that mean? It means that it is satisfying this property Q, and it's not something that we like. But we also have to check whether it's a spurious counter example or a real one. So we go ahead and perform this check on the original network. So after propagating the values through this, the calculation can be seen later on. So we get the value 680. And now 680 is lesser than 800. So it's not really violating the property Q. It is within the constraint. So there is something wrong over here, which means that 20 is spurious. It's not a real counterexample. It just appears to be a counterexample, but it's like a false positive, which means that this abstract network is far too abstract. It's not accurate enough to sort of represent n. So since since the value 20 is spurious, we're going to refine n prime. And how do we refine it? We just split the nodes which we have merged. And this was also the only node which has been merged. So we are going to go ahead and split this one. So once we split it, we get the original network n. We basically just get the original network n, and n double prime is the refined network. So if you can notice, n, the symbol isn't visible here, but n is equals to n double prime. So this is like an extra step. Instead of just verifying this network directly, we merged the nodes and then had to split it again, and we just ended up with the same network when it comes to cigar. And this just slows down the verification process. So cigarette has a solution to this. So this is just explaining the issue with cigar. In the example network n, there was only one abstraction refinement iteration needed, but ultimately the refined network, which was n double prime, as you can see, it was just equal to the original network n. So this was an extra step in the verification, which slows down the overall process. So this presence of such spurious counterexamples are due to the imprecision introduced by the abstraction of n. So the solution is that the abstracted network's behavior is over approximated, right? So to compensate for that, we can tighten the property. So this is where cigarette comes in. So cigarette's methodology. So cigarette's approach is to extend the standard cigar framework by introducing.
Let's see from your slide.
Yes, sir. It's because I shared it. If I had presented it on Canva itself, it would have been.
Yeah, just when you explain it, say what the readout.
Yeah, I will do that.
Yeah, there is an arrow missing, I guess, yeah?
Yeah, a few arrows are missing. Okay, sorry for this. So this extends the standard cigar framework by introducing property abstraction alongside network abstraction. So here the abstracted property and network, which are Q prime and N prime, are over approximations of the original N and Q. So the implementation is to build the abstracted network N prime. So we do this in the same way. We just merge the nodes. And now this is something new, tightening the property Q prime. And there is this soundness condition that comes in. So if N prime satisfies, so if N prime doesn't satisfy Q prime, which means unsat, it means that N doesn't satisfy Q also. So you can see like the parallels across N and Q. And so after this, we try to get a sat or unsat output. So if we get N prime satisfies Q prime, then that means that we have a certain counter example. So we extract X naught. Now we are going to do the check whether it's a spurious counter example or a real one. So if X naught in the network N, the original network N, satisfies Q prime, then it means that it is a valid and real counter example. So we just return sat and X naught. So the algorithm converges over here. Otherwise, it means that X naught is a spurious counterexample or a false positive. So the next step is to trigger the refining step. We are going to refine the network and the property. So this is the crux of cigarette. We are going to refine the network and the property. So basically, we get N prime becomes N double prime and Q prime becomes Q double prime after refinement. So this property refining and abstraction both use an approach that we call property tightening. So this is something I will be speaking about very soon. Property tightening is basically just adding a specific value D to the constraint. So this makes the constraint Q harder to satisfy. So it won't really allow many spurious counter examples through. So this is just the algorithm which is like formally defined.
Yeah, when you say harder, I think this is a bit misleading. Harder sometimes you use or harder to check in terms of complexity. What you really mean is it's stronger.
Yes,
okay?
it is stronger.
Stronger than the original problem.
Yes, because it's harder to satisfy.
There are fewer values that it gets.
Yes.
It is stronger. Okay, so there is fewer spurious counter example. Okay?
Yes. So this is the cigarette algorithm formalized. So for abstraction and refining, we have separate functions, which I will call query abstract and query refine. I will just go through the algorithm again. So this original query we take the original query over here, and then we abstract it to get n prime, p, and q prime. Then we are going to verify it. If we get unsat, then the algorithm terminates. It's good. Otherwise, we extract the counterexample x naught that we get from the sat output. And if it is a valid counterexample for NPQ, then we just return sat and x naught. Otherwise, we carry out the refining step. So that's done using the function query refine. So the crux of cigarette is using network abstraction, property abstraction, and guided refinement. So this guided refinement means that it is counterexample based. Again, this is also an iterative algorithm. So I will be explaining it better with the same network. So we have the same network N, and the abstraction is basically the same. We just merge these two nodes which belong to the same category, and we get this abstract node, which is N2, 1 plus 2. So the network abstraction is done. And once we get the abstracted network, we do something called property tightening. Now, this is the actual newly introduced aspect of cigarette.
Yeah, good.
So the original query V1 has N and this property P, which just states that the input should be within the range 20, 21, both numbers included. And the property Q in the original property Q is Y is greater than 800. So here 800 is the constant C. Now we are going to do something called bound computation. If you recall, I spoke of a certain constant called D. So to compute this D, we are going to use the network bounds. So the bounds we are going to use is, we want the lower bound of the abstract network. So the lower bound of the abstract network is 20. So we have n prime of 20. So the computation is done over here. So 7 into 10, 10 into 20, we get 1400. So this is the value of L n prime. And the next bound that we use is the upper bound on the original network. So like this is based on the input bounds. When I say L n prime and U n, these are the output bounds after propagation of the values. So after propagating n21, we get the value 714. Now computing D, the main formula for computing D is this: the maximum of 0, L n prime minus U n. So basically we want a non-negative minimal difference D. And over here, we are going to just plug in the values 1400 and 714. So we see that the value is positive. So we just take 686 as the value D. So now since we had Y is greater than C as the original property, Q prime is now going to be defined as Y is greater than C plus D. So this is where the D comes in to tighten the constraint.
Why is this? I have a question here. Why is this D that you computed here is sound?
This D is sound because it's still, how do I explain this? So it still is an over approximation. It's like an abstraction of the original Q. It just makes it harder to satisfy. Like it doesn't rule out the real counterexamples. In fact, it rules out the extra spurious counterexamples and makes our job easier.
Yeah. I mean, can you give a counterexample that was there earlier? That
Yes,
is
I
not
can.
there now?
I will give
You
that.
will do that.
I will
Okay.
do that.
So this is some D which keeps it sound as per your earlier
Exactly.
requirement. So it removes some counterexamples, but some spurious, but not
Yes.
any real.
Not any real counterexamples.
That's a good one. Yeah. The way
Okay.
exactly that is that you will.
Yeah. So D is computed this way. Actually, I believe that there are many other ways to compute D, but for this example, this bound computation is simple enough. It works out. So now overall, before we had Y is greater than 800. Now after tightening the property, we get Q prime as Y is greater than 1486. Now this is the new property, tightened property that we will be using. So this is just like an overview. Instead of from N P Q, we go to N prime P Q prime. This is just a process of abstraction. There was supposed to be an arrow here and here. So now let's call the new verification query as V2, where we have N prime, P, and Q prime, which is this new query, this new property, which is Y is greater than 1486. Now we are going to proceed with the verification. So if you remember, before we had the counterexample 20, this was considered spurious in cigar. So now let's try to check the same thing. In the abstracted network, it's the same abstracted network, which is N prime. So once we propagate it, we get the same value, which is 1400. Now here, if you look at it, 1400 is lesser than the value 1486. If you like, this is the new property, if you remember. So it doesn't really violate this property Q. It is within the range. It is lesser than 1486. And it is lesser than 1486 here as well. So this doesn't come to be a counterexample at all. Forget being spurious or real. So this sort of spurious counterexample is eliminated. So you just directly get unsat since there is really no value that sort of violates Q. All of the values lie below this constant, 1486.
Yeah, is there, I mean, let's pause here. Are there any questions here about the tightening of property and how it is helping improve the performance, I mean, over the original node merging abstraction? If there are any doubts that you have as to what this property means, you may ask now. Okay, there's no question, there are no questions, so you can go ahead.
Okay, assuming that there are no questions, I'll continue. So the analogy to this is like sort of having a filter. So increasing this value C by a constant D sort of filters out the counterexample, and it kind of narrows down the output space. So any output that you get is more likely to be valid as compared to using the previous value, which was just 800. So finally, now x naught is equals to 20 is not a counterexample at all. So it's not spurious or real. So finally, the verifier just returns unsat and it converges over there. So this also just says that the DNN n satisfies the desired property, which is what we are looking for. So this new query with the abstracted network and property has sort of, it is an actual solution to the problem that Cigar had. So now this is just an overview of the abstraction. So I increase the threshold C by a certain value D. This is just a formally put slide of everything that I have explained. So Q prime is equals to Y is greater than C plus D. And the constant D is a non-negative minimal difference. So why does this work? As we saw, the tighter constraints are harder to satisfy and the output space is narrowed down. So such spurious counterexamples are excluded. So now because of this, the verification efforts are focused on more likely genuine violations instead of just false positives. So this also leads to fewer unnecessary refinement and it speeds up the entire verification process. So this is just, we had two certain algorithms.
You're going to describe how exactly you will derive D.
Yes. If you remember in the original.
Yeah, yes, somebody has a question, yes.
This is Deepro. Sorry, you just mentioned that you wanted to increase the threshold by some D. So, how do you decide that D?
Yes, there can. Okay, so you're asking how we decide the threshold D, right?
Yes.
So there are many possible ways, but the ways that we are using.
This crosstalk, can somebody? Yeah, go ahead, yeah. So Deepro asked that question, so how do you determine D, okay? Yeah, what's the answer, yeah?
Okay, so for D, we are using certain bounds on the network. Over here, we compute the lower bound on the network N prime and the upper bound on the network N. And then we get two certain output bounds. Now this works because it doesn't, it's kind of like conservatively increasing C. So you don't increase it by too much. You just add refinement when needed. So whenever there is a spurious example, you restore some amount of precision. You don't want to make it, you don't want to turn it back into the original network and you want to find a perfect balance. So to do that, you increase C by some amount.
Yeah, I don't know if Deepro understood your answer. Okay, let's make sure. Deepro, did you understand?
Yes. That makes sense.
Okay.
Yeah, so see, yes, so the D, like she has already said, the D can be, she uses a bound propagation on N, the original network, and the node merge network. And based on the count, she gets an estimate on the value, right?
Yes, basically.
How, yeah. How it is, yeah.
Okay, so we don't want just some arbitrary value of D. We want the right value of D, and it has been found that using the output bounds of the network helps out. So that is the crux. The constant D is the core of the property tightening. So we use the lower output bound of the abstract network N prime and the upper bound of the network N. And D, the formula for D is this. D is equals to maximum of 0, comma L N prime minus UM. So we want it to be non-negative. So
Crosstalk. I think there is some background noise. If someone has not muted their speaker, can you mute them? Mute it, please. Go ahead.
okay, so continuing. So this is the overall formula for D. We want it to be non-negative so that it actually increases or just keeps the constant C the same. We don't want it to be decreasing. And finally, we compute the new Q prime as Y is greater than C plus D. So this plus D is what sort of tightens the property. So it makes it stronger. Now, the reason why spurious counterexamples exist is because the property wasn't strong enough. The constraints were too loose. So this is something that's going to help out in reducing the spurious examples. So this abstract N is the same node merging abstraction to obtain an over approximation of the network N prime. And now this tighten property is the function over here. It relies on the observation that there is some minimal non-negative difference D between the output bounds, and we decide to take this one as the constant to add to C. So this is like the overall just an expansion of the formula for D. So now when it comes to bound computation, here we have compute lower bound and upper bound. So how do we compute this? So these can use bound propagation techniques. Basically, bounds of the ith layer are linearly combined to estimate bounds of the I plus first layer. So this is like a simple example. We just propagate the input bounds, and these values just propagate through the next layer. And finally, to the output layer, you get certain bounds. I think this is actually something that we have learned in class. So this is just an example. So there are a few bound propagation methods that we have learned about as well. For example, symbolic bound tightening or SBT is found to outperform the other two methods which were tested, which were interval bound propagation or IBP and deep poly. So the statistics for this will be shown soon. So basically, to summarize, we use something like SBT to compute the lower and upper bounds, and we use the difference of these bounds as the value D. And to tighten the property, we add the value D to the constant C. So that is how we got the new query, which was Y is greater than 1486. So this is the refinement step. If you remember.
Use SET. Deep poly was discussed in class. What
Okay.
is symbolic bound tightening? Are you going to describe it or
No, actually, that is.
Okay. So they use some other method besides deep poly.
Yes, they actually.
Do a better,
yes.
more precise bound propagation. Yeah?
There was some experimentation done on some bound propagation methods, and they just found out that SBT is a certain bound propagation method. This was something that outperformed the other two methods, which were IBP and deep poly.
Some details of which are they described in the paper or
the
what is symbolic bound tightening? I know that you're not going to talk about that, but I'm just curious if for the benefit of the audience, is the paper have it or not?
No, it doesn't have the specifications, but there are some comparisons of the bound propagation. Those are there.
I meant the technical details. So it's
Okay, the technical details
similar
are-
propagation, they probably do actually propagate the actual constraints.
Yes.
As predicates and something like that, like using homologic and so on. So I imagine that's how
Yes,
it is.
yes.
So it's doing domain-based propagation like deep poly does.
Yes.
They use more precise predicate-based propagation, probably. Okay.
That is true, but any bound propagation should work.
Yes. Yeah.
For the simplicity, we just use the regular, just the input propagation.
Yeah, I do agree. So any bound propagation that is sound
Yes.
should work.
Okay, so moving on. This is the example of bound propagation. Now, if you recall, after the cigarettes abstraction, we didn't really need any refinement. But that was only for this case. It's not always necessary that refinement isn't needed when cigarette is there. So refinement is carried out only if the counterexample x0 is spurious. So let's say that even after abstraction in cigarette, we get the output sat. So if we get the output sat, it means that there is some satisfying assignment x0. So again, we have to do the spurious or non-spurious check. So if by chance x0 is spurious, we do the network refinement. So the network refinement is done in the same way. We just split the nodes. So again, like we have to sort of identify the abstract node where the spurious behavior is suspected to arise from. So let's say that we have merged 3 or 4 different nodes to get 2 abstract nodes. And out of these 2 abstract nodes, maybe one of them is responsible for the spurious behavior. So identifying that is a whole new topic. So once we identify that, we have to split it back into the original neurons. So what this does is it restores precision to the network.
But this step, the network refinement step,
Yes,
they use is exactly the same as.
it is exactly the same.
No difference.
There is no difference.
Okay.
Even when it comes to property refinement, we still use the same tightening property. So basically, maybe the property wasn't tight enough. Again, the property wasn't tight enough. So we recalculate a tighter property Q double prime. So based on the updated network bounds,
Correct.
we use the formula.
The refined network.
Yes. So here we computed D is equals to max of something. Here we're going to compute D is equals to the max of 0, comma, the bounds of the new network, the updated network bounds. So we have the abstract network and the refined network. So first we have, one thing that I have to clarify is that first we have to do network refinement and then move on to property refinement.
Okay.
So this is because property refinement uses the abstract network that comes out from this part.
Correct.
So moving on, we recompute a new constant D prime, and then we add it to C. So then this is the refined property Q double prime. And this refinement restores the necessary details only when there is some undesired behavior that is observed. So this is like a conservative way of doing something, of like doing the refinement. So we don't want it to be too approximate. We don't want it to be too abstract, but we don't want it to be too detailed either. We want to find the perfect balance so that it is computationally efficient as well. So this cigarette iteratively helps converge towards a precise query that avoids both false positives and unnecessary complexity. So we want to balance this fewer spurious examples and unnecessary complexity. So that is where the D and D prime comes in. So the refined query generation is the same thing, but formalized in an algorithm form over here. So we use something called query refine. So n double prime is just splitting the abstract nodes in n prime. And for q double prime, again, we use the tighten property function. And finally, we get this new query, and then we go back to the original step. We start verifying again. So we get an unsat or sat, and it just keeps going until it terminates with either a sat or an unsat. So this was cigarette solutions, as we saw. It applied both network and property abstraction. So this eliminated the spurious counterexample x0 is equals to 20, which arose in cigar. So this refined verification query ruled out this false positive. And the false positives are basically caused by loose approximations due to abstraction. So tightening the property just compensates for that loss of precision. So this process converged and returned unsat, confirming that the original network N satisfies our desired constraint, and it behaves as we want it to. So this improved on Cigar's technique. Now I said that the process converged. So how are we sure that cigarette converges? Here is some proof. So we start with abstraction, and there are only finitely many abstraction steps that you can take because there are finitely many neurons that you can merge. And when it comes to refinement, since we just split the nodes that were merged during abstraction, we can think of refinement as undoing abstraction. So this also means that refinement has finitely many steps. So eventually, no matter how many refinement steps you go through, at some point, it becomes the original network N, and Q prime becomes the original query Q. So we can actually see that in the first, in the cigars case, where N double prime just became equal to N after refinement. So at some point, you do get you do come back to the original network and property. Now, after you get this query, the next iteration will definitely return either unsat or SAT. In both of these cases, the algorithm will terminate. So unsat just means that the desired property holds, and the SAT will just return a true counterexample. So in both of these cases, there is a termination, which means that infinite loops cannot occur. So this basically concludes that cigarette definitely does converge at some point. So now let's move on to how the paper implemented cigarette and evaluated it. So when it comes to
Here's the time to pause. Anybody have any questions about the algorithm, cigarette, regarding how it does property refinement, property refinement at each step? Yeah, any questions? Okay, more.
okay. So moving on to how cigarette is implemented. So the paper came up with something called cigarette NN, which is a proof of concept tool that implements the algorithm cigarette. So now the underlying verifier to get a SAT or unsat output is Marabou. We have studied about this in class. It is a sound and complete DNN verifier, which uses a simplex solver, and it has some abstract interpretation with enhancements. So some examples are like proof production. So it can formally prove the correctness and give guarantees, and splitting heuristics, and it supports various activation functions like ReLU, tanh, sigmoid, etc. So actually any other underlying verifier can be used, but this paper in specific has used Marabou. I thought I should clarify that. And when it comes to abstraction and refinement operations, it implements the query abstract and query define algorithm that I had spoken about in the previous slides over here. So when it comes to bound propagation, they have experimented with 3 different bound propagation methods. Those are IBP, deep poly, and SBT. Later on, we will see why SBT was preferred. And these are just the software specifications of what the experiment was run on. So now let's come to the benchmarks of the verification. Here we use 2 main benchmarks. The first one is ACAS-XU. So this data set is something that is used to train airborne collision avoidance systems. That is the full form of ACAS. So there are 45 deep neural networks in this system, and each of them has 310 neurons. So basically, there are 5 input neurons, 5 output neurons, and 6 hidden layers. And totally, the number of hidden neurons are 300. So each hidden layer has around 50 neurons. So there are certain robustness queries that are standardized. So this ACAS-XU networks use 20 of these adversarial robustness queries, and there is a timeout of 2 hours. So the query is of the form X naught and delta. So X naught is considered the input, and delta is kind of like a threshold or a radius. So what we want is that starting from the center X naught, any point within the delta ball around X naught must produce the same classification, which means that just because there is a small change in the input by a small value, the classification category shouldn't vary too much. So delta is just like some sort of tolerance factor.
Yeah, it's called robustness property that we discussed in class. Yeah.
So this is what robustness properties are. So how the ACAS-XU networks work is that the input is some sensor info. For example, the trajectory of the airplane, its velocity, and maybe the information about other airplanes in the same area. So this input is fed into these 45 DNNs, and the output is some horizontal turning advisory, which is going to help avoid any collision. So that is the overview of the ACAS-XU network. So the second benchmark we're using is the MNIST. So if you recall, MNIST is the handwritten digit classification data set. So there are 3 networks that are used, MNIST 1, 2, and 3. So these are trained on 60,000 different images, and the testing data consists of 10,000 images. So the robustness queries are the same ones used over here, the 20 adversarial robustness queries. And these are tested on like a few valid cases. When I say valid cases, I mean that we don't do the very non-trivial query. We don't do the very trivial queries. We only use the non-trivial queries where they're actually like slightly complex. For the simple queries, we don't really require any formal verification, so we don't want to spend extra time on that. We verify only the non-trivial ones. That is what I mean by valid cases. So when it comes to delta, there are some constants that they take from this set. So MNIST has a higher complexity as compared to ACAS XU. So the timeout is actually 3 days. So an overview of how the MNIST networks work are, there are some images of handwritten digits from 0 to 9. And they will be fed into these 3 MNIST DNNs. And this output will finally be a digit label, anything ranging from 0 to 9. So now here are the properties of the data set. So about the ACAS XU, I've already discussed that there are 45 DNNs and 310 neurons in each DNN. So the MNIST 1, 2, and 3 are slightly different. They have the same number of input and output nodes, but they differ in the number of hidden layers. For example, MNIST 1 has 5 hidden layers, MNIST 2 has 6, and MNIST 3 has 15 hidden layers. So for the MNIST networks, we have a certain degree of accuracy that they have obtained. MNIST 1 is 97, approximately 97%. MNIST 2 is 97.13, and MNIST 3 is 95.5. So these verification queries are encoded as Marabou compatible constraints because the underlying verifier we're using is Marabou. We encode it to be compatible with that verifier. And those are based on the standard adversarial robustness specifications like these, the input X0 and the radius. So for both of these benchmarks, again, as I said, we're only using the non-trivial queries. So basically, we are going to filter out the very, very simple queries where formal verification is not really required. So there are 2 experiments done while evaluating. So the first one is the bound propagation techniques. So they tested the performance of 3 different bound propagation methods, which were IBP, deep poly, and SBT. So IBP is interval bound propagation. It is a very naive method of finding the bounds. Deep poly is something that we discussed in class, and SBT is something slightly new. So in the table, we can compare the propagation. So this is basically the number of finished experiments and the number of timeouts. So IBP has completed 397 experiments, but the timeouts are much greater than the number of finished experiments, which means that it is actually quite fast, but it's also very less precise. So this is not something that we prefer. SBT, on the other hand, has completed 851 experiments, but has timed out on 49 different ones. Deep Poly has completed 833 and timed out on 67.
Yeah. What is IBP and this? IBP is the original.
Interval bound propagation.
Okay.
The naive.
Default is more than interval propagation. But
Yes.
they haven't compared it with the original recount with just cigar.
No, they haven't compared. They've done the comparison for cigarette. They've run the 3 bound propagation methods for cigarette in specific.
They have not shown its performance with respect to the originals.
Yeah, cigar doesn't have bound propagation because D isn't.
Comparing how many does it do as
Okay.
opposed to this one.
I understand.
Done that, I thought they would be doing that.
No, it wasn't done. So overall, they found out that IBP has the highest number of timeouts, more spurious examples, and more refinements. So basically, this is why the timeouts are happening. Deep Poly is actually the most precise, but it's also the most computationally expensive. So it's not something that comes at a low cost. SBT, on the other hand, was able to balance precision and speed. So you can see that SBT, even in the table, it actually did perform better than Deep Poly. Maybe not too precise, but it was faster and there were lesser timeouts. So SBT gave us the best overall performance with lower timeouts, lowest timeouts and efficient execution. So in the subsequent experiments, SBT has been selected. So now the second experiment that we are doing is evaluating cigarettes efficiency, and the baseline is our standard cigar NN. So we are going to evaluate performance gains from property abstraction. So something to remember is that for uniformity, cigar and cigarette both use the same Marabou verifier and the abstraction refinement operations. The only difference is the property abstraction. So we can go through the table with the details.
Cigar and cigarette, no?
Yes, but not for the bound propagation. These are for the number of timeouts.
fine. Cigarette NN, sorry. Here the comparison is between cigar, original NN and cigarette. Okay?
Yes,
With some bound propagation being used, correct?
yes, that is true.
Yeah, with some property tightening.
Yes, they've used SBT. Only cigarette has.
So this is what I was looking for, a
Okay.
comparison between some version of cigarette with some bound propagation with cigar NN, okay?
Hello.
Okay.
Yeah,
Am I audible?
yeah.
Yeah, sorry, I was having some network issues. I mean, this is what sir was looking for, right? I mean, come with the
Yeah.
original cigar method.
Yeah.
Yeah, okay.
Yeah,
Yeah, that's what I had asked originally. You said there's no such figure.
I apologize. Maybe I misunderstood the question. But this is cigar NN and this is cigarette NN using SBT. The comparison between these two. So we can go through this one by one. In the ACAS XU network case, basically here I'll explain what the columns mean as well. In the timeout column, we have the number of experiments for which the algorithm timed out and the number of experiments that the algorithm finished. And with the columns faster verification time means that some number of cases were faster compared to the other. So they're taking, it's kind of confusing, but they're comparing cigar and cigarette. For example, over here, cigar NN has 272 cases where it completed faster than cigarette NN. So that's what this column means. Similar to that, fewer refinement steps. Over here, it means that 73 cases, cigar NN had fewer refinement steps than cigarette NN. So that seems like an inconsistency in the ACAS XU network. But overall, there were lesser timeouts. There were lesser timeouts in cigarette NN and more number of finished experiments in cigarette NN. However, somehow for cigar NN, it had faster verification time and fewer refinement steps. So this is something that is slightly inconsistent because it also depends on the data and the network, I believe.
No, I think the reason is sometimes what, maybe, or that I don't know. I mean, because that you have, I think sometimes the original cigar end, it can have fewer, fewer.
Yeah, so this is kind of counterintuitive to me as well because it might be due to some implementation details and so on. Because if we are doing the cigarette and as far as I understand it, is simply cigar and plus some extra bound tightening steps, right? And that should just give a strictly stronger and better query than cigarette NN. So perhaps, yeah, I mean, there is one thing in cigar NN, which is that cigar NN seems to often use some heuristics where they'll do a number of refinement steps as a batch together, and maybe they had not replicated that in the cigarette and maybe that is causing some issues. Maybe something weird like that is what I would suspect, but I'm not sure. This is counterintuitive to me as well.
And the technical details weren't really given, so it's like a black box. Maybe there's something internal.
Yeah, I mean, yeah, we would probably have to look at the code and maybe replicate.
Yes. So this part of the result is slightly counterintuitive and inconsistent. But in the other cases, we do see an improvement. Let's go to the MNIST1 network.
No. There is one way that maybe you can explain it, okay? Because here property tightening and this there were, maybe it is because of this, because there's so many, it depends on the spurious example that they generate, because this does fewer the same spurious examples will not be here.
Yes.
Because the original cigar NN, the splitting was counterexample guided. Okay, maybe that would have made a difference. Okay, the counterexample may not be the same thing. So maybe that led to lots of merge nodes being taken out. Okay, I mean being split, and that resulted in original network,
Yes.
some network is closer to the original network being produced by the incumbents. It's possible, huh?
Yes. So if I'm not wrong, it's
The two counter examples produced by the two versions are different, huh?
yes.
Yeah, that might have influenced also. Okay.
So this is
It's actually a
if I'm
very,
not
very
wrong.
interesting point. Yeah.
Yeah.
Yes. So it is something intrinsic to the data and the network itself. It's not specifically because of cigarette and then bringing in property abstraction.
I'm not so sure, because they're using the same data net. It must be, if I say it's there must be something. Either there's the refinement, there was some difference in the refinement implementation between the two, or whether I'm throwing this into the mix, whether the counter examples, how the way which get generated
Are different.
is different. Okay, when you do property type, visually influence what nodes you split, and so on. Yeah. So very much the splitting heuristic is influenced by the counter example. That might have resulted in more refined. Don't know. Nevertheless, the times and the certificate verification time, there is a lot of improvement. No? That
And
you can see, right?
and
Yeah.
in the finished experiments, there's an improvement, sir. The
Yeah.
verification time is also not good. That is
Some units too, there is.
yes, the verification time being slower is a result of the refinement steps. Like there are more refinement steps over here. That's why it's slower over
Yeah,
here.
and this too.
Yes, these do have improvements.
Still, despite more refinements that it is verification time is faster.
Yes, sir. So moving on to the MNIST1 network, there are lesser timeouts again, and there are more number of finished experiments as compared to CIGAR-NN. So CIGAR-NN had almost as many timeouts as the finished network. And going back to the ACAS XU, there were more timeouts compared to the finished experiments. So even though the verification time was faster and the refinement steps were fewer, there are so many experiments that weren't really completed. So in MNIST1, there were 252 cases where cigarette-NN was much faster than cigar-NN. And there were 283 cases where cigarette-NN had lesser refinement steps as compared to cigar-NN. Now, this is where the actual property abstraction gain actually sort of shows up. So in 283 different cases, cigarette-NN performed better than cigar-NN when it comes to the refinement steps. So in MNIST2 as well, there are a lot of finished experiments. CIGAR-NN, on the other hand, has more timeouts than number of finished experiments. And it has faster verification time in 134 cases and 133 cases of fewer refinement steps as compared to CIGAR-NN.
Here, even the refinement steps is slightly better than the previous thing. Yeah.
Yes, so in MNIST1 and 2, you can see the full-fledged improvements. So in all 4 columns, cigarette-NN performs much better than cigar-NN. So in MNIST3, again, there is a slight inconsistency. So the number of timeouts, there are less timeouts compared to in cigar-NN as compared to cigarette-NN. They're almost close, but cigar-NN still has lesser timeouts and more number of finished examples. And but however, the verification time for cigarette-NN is still much faster. Even the fewer number of verification steps cases are more. And overall, when you like take a sum of all of these, cigarette-NN does perform much better, like when it comes to the overall performance in both benchmarks. So cigar-NN has almost 1,506 timeouts and 1,618 finished examples. So it's almost like 50% has timed out, 50% has finished, and that's not very good performance. Cigarette, on the other hand, has a much lesser amount compared to the number of much lesser amount of timeouts as compared to the finished examples. And it is much faster in many cases. It's not, I mean, the number of faster cases when it comes to cigar-NN and cigarette-NN, there's not too much of a difference, but cigarette still outperforms cigar. But when it comes to the fewer refinement steps, there is a huge difference. Like as compared to 80, cigarette-NN has 469 cases where it had lesser refinement steps. So overall, we do see that cigarette NN outperforms cigar NN, and this is all because of introducing the property abstraction. Everything else is uniform. It's just the extra property abstraction aspect. So this is the key insight. This table just summarizes everything that we saw. So when it comes to the number of finished experiments, cigarette NN has more experiments than cigar NN which are finished. And we have a 65% improvement. And faster verifications, there is a 12.85% improvement in the verification speed. And when it comes to fewer refinement, this is where the real deal is. So there is a 586.25% improvement when it comes to reducing the number of refinements. So this is what we actually wanted. This is the crux of the cigarette's property abstraction. This is what it helps out with. So this is due to the property abstraction, which reduces these spurious examples. So we can see a graph of the runtime as well. So this is for the ACAS XU network. The x-axis is the time. So it starts from 1 minute and goes until 2 hours. If you remember, the timeout for ACAS XU was 2 hours. So the y-axis is the number of finished experiments. So if you see in the beginning, cigar and cigarette do behave somewhat similar until this particular point, which is, I believe, 15 minutes. So they do behave similar to each other. But at some point after this point where they intersect at 15 minutes, we can see that cigar just becomes a flat line. So it doesn't really improve after that. The number of finished examples just stop at around 400. Cigarette, on the other hand, there is like a steep increase you can see over here. So the number of finished examples increase by almost more than 2 times. Here it stops at 400, here it goes up to 850 or so. So we can see that it does outperform cigar in the long run. So I have just sort of written them down in points. At short run times, cigar NN and cigarette NN behave very similarly. But in longer run times, cigarette NN performs much, much better than cigar NN. And cigarette NN reaches a flat line after 1 hour. Actually, both of them do reach a flat line. But cigar NN reaches a flat line after just 5 minutes. So over here, you can see that the flat line starts. And this is just the 5-minute point. But cigarette reaches a flat line after 1 hour. So it does have a steep increase in finished experiments just before that. So that is still considered good.
That's because I guess the original thing times out more.
Yes,
That's why it
exactly.
becomes flat. I mean much earlier.
Yeah, that can be seen here as well. There are a lot of more timeouts as compared to finished experiments. So in conclusion, cigarette is more efficient. Moving on to the MNIST network. So we can see something similar over here. So the x-axis is again the time, but this time it goes from 1 minute to 3 days because the timeout is 3 days. And the y-axis is the number of finished experiments. Again, up till a certain intersection point, which is around 45 minutes, I believe, both of them behave similar to each other. So they are quite close to each other. But again, in the longer run, there is a similar behavior observed. So there is a decrease in the performance of cigar. At some point, it stops after the timeout at around 1,200. Cigarette, on the other hand, there is some amount of steep increasing that's going on, and it stops at around 1,800 at the timeout. So the trends observed again at short run times, again, cigar NN is approximately behaving like cigarette. In longer run times, cigarette is much better. So something that we can see is that minor input changes might sort of trigger drastically different paths in SMT solving. And another thing about this graph is that it's not really an ideal metric. It's not too ideal to see this because it averages the performance of all 3 MNIST networks. And if you remember, there was a difference over here. The MNIST 3 had a different performance as compared to the other 2. But overall, you can still see that cigarette NN is more efficient when averaged across all 3 networks. So this is a summary of everything that we have done so far to conclude. So cigarette is a method of enhanced verification which integrates property abstraction with the standard network abstraction in cigar to eliminate spurious counterexamples. So this results in fewer refinement steps and faster verification time. So we have seen the substantial performance gain, 65% improvement in the benchmark experiments completed, and 586% fewer refinement steps, which reduces the computational load, and a 12.85% faster verification time. So this is also has a smarter refinement strategy.
I think this 586% purely refinement steps is kind of added over all the benchmarks.
Yes,
That's what they have done, because we all already saw there were some benchmarks for which to calculate.
Yes, exactly.
Yeah,
It's
yeah.
averaged.
So that's a bit misleading, but nonetheless.
Yes. So basically, cigarette uses a smarter refinement strategy, and that uses the method of property tightening. By tightening the query bounds of the property queue, cigarette NN narrows down the search space, and it reduces the number of false positives and improves the convergence and the verification time. So it is also scalable and practical. That was a challenge that we had seen in Cigar, but it is much more scalable now because of the fewer number of refinement steps. Now, as tested out, it has been successfully applied on real-world networks, as we have seen ACAS XU and vision datasets like MNIST, with Marabou as the backend verifier. So overall, this, I hope everyone is convinced that cigarette does improve verification efficiency and scalability while still maintaining the soundness and completeness. And here is some future and related work that can be spoken about related to it. So adaptive property abstraction. So we do see that we adjust the tightness of property abstraction using D, but this is something that we are doing manually. Perhaps we could use something like feedback loops. This is an idea that maybe can be taken up in the future. And another thing is we only verify one single property, which is Q. Maybe we can extend it to handle simultaneous verification, assuming that they aren't dependent on each other. Let's say we have 3 or 4 different properties. And if we can simultaneously verify them in parallel, when they're encoded as Marabou constraints, that could also be helpful. And we can also generalize it to other domains. So if you remember, this is mainly for the DNNs. We have spoken about cigarette in the context of DNNs only. If it is, we can possibly apply the approach to other domains beyond classification. For example, we can go to regression networks, control systems, CNNs, RNNs, etc. For this, we will have to be able to encode sequential constraints as well. And integration with other verifiers. So it does work with Marabou, Reluplex, and other verifiers, but possibly incomplete verification techniques, it hasn't really gone that far yet. So maybe it can go there and sort of create a balance between the precision and the time. But overall, we did see that it was efficient in the case of cigarette. It could be efficient in many other domains is what I'm speaking about. So any questions?
Any other questions? Yeah, one comment.
Yeah.
Yeah, you had one?
Yeah. I had a question. So I mean, this is a general question, but see, I mean, one of the things that we're motivating cigarette via is saying that okay, cigarette does not look at some information from the property; it looks at only the network and so on. Whereas cigarette kind of incorporates information from the property as well, right?
Yes.
So can you clarify? I mean, what is the specific information that is ignored by cigarette but incorporated by cigarette?
Instead of not exactly ignored, but it is mainly through abstraction, most of the precision is sort of left out. When we abstract and get an over approximation, it removes some amount of precision. So that is where the spurious counterexamples sort of pass through. So it's the ignoring is happening in the abstraction process. But abstraction is something that we do need because we do want to reduce the size and complexity. So there is what cigarette is saying that we can compensate for that by tightening the property. So the property
Right, but
sort
I
of
mean,
brings back that
how are we
information.
able to do that for free? I mean, in the sense that if we are able to do something better, it's typically either because the previous algorithm was not utilizing some information that was there, or we are giving up something or somewhere. So, is that what's happening? I mean, what is there anything that the previous algorithm was not utilizing, or is the new algorithm somehow making a compromise somewhere by making this title property? Because the title property is just strictly better, right? So it can't be
Yeah.
that we are somehow, I mean, just getting something strictly better without a compromise, or maybe the previous algorithm was just somehow ignoring something or missing something.
I mean, I have one comment that I can
Okay,
make
okay.
towards that, and if you, I'll let you.
Okay, sure, sir.
No, do you have any additional comment to add to Virendra's question?
Not really, but if I understood the question correctly, cigar NN actually isn't really doing anything to the property. Property encoding can actually help out in efficiency, but
Yeah,
it kept the property the same.
So I think he's asking a more general question.
Okay.
What are the kind of information that CGAR NN does not use? Obviously, this is using some information
Yes.
right in the thing.
Yes.
Okay. So, what are some of the other kind of information that it is missing? Okay. I see. Okay, I have a more general comment. Okay, all this thing is doing, although you're right, Pranika, so that you're insisting that okay, he's tightening the property. Okay, that's how he has expressed it. Okay, but I mean, in general, to answer Diganta's question, if you can find out how does this method compute that D, it does certain analysis, bound propagation on N,
Yes.
and also does bound propagation and run.
Yes, this is the information.
So
extra
that is the additional
Okay.
information. So both those things are, as a result of doing SPT or interval or whatever, you're deriving what are invariants.
Exactly. That is
Now,
true.
there are invariants about N and about N prime. In this case, the invariant that he is giving is some constraints that are bound to hold good for the at the output
Yes. Yes.
of that network here N and N prime. So obviously, you know, that is the additional information that is being added.
Okay, so that is
Now,
the answer to the question.
yeah, I mean, along those lines, if you add anything, any additional information that you can derive by analyzing N and N prime, the original network and thing, and that is the next step of
Yes.
refinement, then it can always perform better.
That is
So,
true.
along those lines, if you're using bound propagation, I have this question, this comment as to why can't, is putting bound at various internal nodes with that, that can also be,
That can also be done
It's only obtaining at the very
at the end.
Can also help in any way by doing better refinement or better merging and so on. And does that make sense?
Yeah, I believe that can help because like at the intermediate steps also, there can be a lot of changes happening. But I feel like it depends because there could be too many neurons in the intermediate levels. So that would mean many sort of bounds
No, but I thought these depoly, etc., when they propagate, they also
propagate through
get
those.
constraints on the intermediate nodes.
They
too.
do.
So you might as well use them, no?
That is true.
That is one.
Yes.
And it is, I think that's what is happening there. What I feel, yeah. You agree?
Yeah, that is I think what my guess is as well. I was just wondering, basically, looking to some discussion.
Yes, maybe the intermediate part that you were talking about, sir. Maybe that
I
would
don't
be
think
like
it's just wondering, any additional invariants that we can add, maybe it will come into, so.
Yeah, it'll be even tighter. I think that will sort of translate to looking like a better abstract domain, is what I think.
Yeah.
Perhaps, but I'm not very sure of that. I mean, there might be other ways of doing it as well, but one way would definitely be using some better abstract domain or better bound propagation technique, because that will basically compute a stronger or a tighter invariant at each point.
yes, sir. It
Sorry,
could work.
you're saying something, fine.
Yeah, okay. So it's lunchtime, so we will assemble again at 2:30, right? That's what
I think so.
the schedule said, no? Can you check?
Yeah, but just one small thing before that. I think Parnika, you were saying something and I interrupted you. Can you maybe?
Okay,
You
I was
adding
just
something to
yes, sir.
yeah, tell.
Continuing in the same flow, I was just saying that if your idea, like doing the same thing at the intermediate level, if it has a significant amount of improvement, then it's worth looking into, because I feel like it will also it should be worth it. If it just has a meager amount of improvement as compared to using it just at the end like we do in cigarette, then maybe it's not something too good that I feel like it's not worth looking into unless it has a great amount of
Yeah,
improvement.
certainly true. I mean,
Yeah, and there's also the computational overhead question.
Yes.
yeah, but if the intermediate nodes computation, there is no overhead because at least 3 point incident, they do compute. Even to propagate all the way to the output, you'll have to compute the bounds at the intermediate nodes. no?
Yeah.
Yeah.
Yes.
So that doesn't add any extra overhead. But how exactly we use that information
That is true.
is the question. Okay, you can add all of them as invariants and then see if it helps verify the network faster. I don't know.
Perhaps,
But
but
certainly here the idea is
Yeah.
reduce the counter example and refine that is the idea.
yeah, this is more of an iterative thing. Like one by one, if we see a counter example, for that specific counter example, we add a certain constant to eliminate that one. And it's just iterative. As counter examples pop up, we eliminate them with this refinement. So if we add it all at once, like all of them together, as you said, I feel like it might be much too precise. Like it would almost come close to the original network N. So this is like a step-by-step sort of thing. And once there are 0 counterexamples, we just stop there because it's good enough for us.
Yeah.
Yes, that's all. Any other questions?
Okay, thank you. And we assemble again at 2:30, correct?
I think so.
Yes.
Okay, thank you.
Thanks everyone. Bye. Great presentation, by the way.
Yeah.
Can I leave, sir?
Yeah, you can certainly.
Okay,
Yes,
thank you.
yes. Stupid. Huh? Happening what? Yes. No. They are. This is just like you guys presented. I'm having. Yeah. That is using LLM. There's a broad topic of using LLM to help do here. One of them is to do invariant generation. One of them is looking at that. There people are using LLM for deriving inductive invariance. Okay. So they're using LLM as a learner. Okay. Learner teacher model. So in that, the LLM. So that is what that thing is. Yeah. Correct. Okay. LLM guesses what it could be, which may be approximate. So that there are 2 papers under that topic of using LLM, leveraging LLM to help verification. The other one is there is this L star method of learning automata. Okay, but here there is a methodology by which they use LLM to help that L star methodology to do a better job of reducing the number of queries. Okay, to learn automata for recognizing language. That's what that is.
While I was looking at the reward machine citation, so two other papers came up with some same author. So one paper was that how to choose a model, I mean, efficient reward machine. He made one paper on that.
Okay, like reducing the size. Huh?
No, so there are lots of reward machine as we discussed. So we were saying that as detailed as you go, the more defined you will get the. So there he has some ability to, choose a optimal reward machine for that.
Yeah, but how he defines optimality is interesting, because at least in our case, if you add more information, I'm assuming that you will get a better. I mean, you will converge to optimal policy better. Okay.
But that is the future reaction, the next step of the paper.
Yeah, no, but so just because you have smaller machine doesn't mean that that the thing is. So yeah. Anyway, that's what this thing is. Let me send I stopped sharing this one. This one I'll have to do. Yeah. Okay. So I know I have to go have lunch and then come at 2:00. If you want to, I mean, there is a possibility that, see, it's 2 days. I'm kind of continuous. Okay. So I'm not sure if we can discuss, since he has asked to do it on Friday, we can, this is Tuesday, Wednesday, Thursday, I'm completely free. Okay.
Thursday and Friday, that's what I have said.
Yeah. Okay. No. He said Friday is better, no? I think so. Let me go have lunch.
Yeah.
You want
We
to?
can discuss.
Yeah.
Because I ordered something already, it's going online. I mean, I looked into the history of that, and how that cardinality one came. From that paper, you will definitely not get the idea of why the
Let me see. You said that they also have cardinality one and has a sufficient condition. What is not here?
So from that paper, there were current studies for individual Australian. Yeah, they have not.
ஹலோ ஜோதி, இது கொஞ்சம் வரீங்களா இங்க? அது ஏதோ வேற, நான் லேப்டாப் க்ளோஸ் பண்ணிட்டு போனேன். இது மறுபடியும் வேற மோடுக்கு வந்திருக்கு. கொஞ்சம் வரீங்களா? ஆ சரி. ஆ ஹலோ.
Hello.
ஹாய் ஞானஸ்ரீ, are you there?
Yes, sir.
Okay, I think, yeah, we'll wait for Diganta. Diganta has to be there for sure. Yeah.
Yeah.
I see Bijian is there. That's good.
Yeah, yeah,
Hi Bijian, how are you?
yeah. Actually, in the morning I couldn't join for first few hours, but later
And
I
I
joined.
understand. I guess you were also traveling. Ila vanduchi.
No. Yesterday I was traveling, so yeah. Today I just overslept a bit. So,
Yeah, okay. We'll have to wait for Diganta and let's see how many other people will join. Yeah. Yeah, as long as you guys are learning through this process, I'll be satisfied. I hope you're enjoying and learning.
Yeah, it's been a fulfilling process. So, is my voice clear?
I think it's a little bit feeble. If
Okay.
you could, for example, Bijian was very loud. You were a bit feeble.
I'll try to speak louder.
அந்த பக்கத்துல இருந்தான். So Bijian, can you speak?
yeah.
Yeah, you're very loud. Lucky, can you
Yeah.
speak?
Yes, sir. Hello, sir.
Yeah, you're also quite good. Jnanashri, you have to speak up a bit, then that's all.
Yeah, sure.
I think it's okay, but it could be better.
Okay.
Hi, Diganta. No, no, yeah, okay. No. I also wanted to Yeah, hello. Yeah, Diganta will be here momentarily. As soon as here, we will start. Okay? Yeah, yeah. I'll make you co-host. You can start sharing the thing. And, as soon as Diganta joins. Work ஆகுது.
ஓகே இது ஆன் பண்ணும் சார் நீங்க
okay.
லாஸ்ட் தள்ளனா தான் ஆன்
ஆஃப் ஆயிருந்ததா?
ஆஃப்ல இருந்து
சரி. Yeah, you can share. Yeah, you can share. Yeah, share. Hmm.
Is my screen visible?
Yeah, it is. நானும் ஷேர் இல்ல அவங்க ஷேர் பண்ணாலும் பரவாயில்லையே இப்போ அவங்க ஷேர் பண்ணிருப்பாங்க. Yeah. தெரியும். Okay. People can see Gyanashree's slides.
Yes.
Yeah.
Yes.
Diganta is here. Okay.
Yeah.
Yeah, let me just start recording. Oh, the live stream has never been stopped. Okay, so fine. Yeah, so you can start.
Okay. Good afternoon, everyone. Today I'll be presenting the paper Leveraging LLMs for Program Verification, which explores how large language models can be integrated with formal methods, particularly in verifying program correctness. So, in overview,
Can everyone hear Gyanashri well enough?
It's okay for me.
Okay, Gyanashri, try to speak a bit closer to the mic and louder. That's all. Yeah, but you're okay though. Yeah. Okay.
yeah. Okay. So, in introduction and motivation, is this better?
Yeah, it's okay.
Um, so, in introduction and motivation,
Yeah, much better now. Thank you.
So, in introduction and motivation, I'll introduce what program verification is, what challenges the paper tackles, traditional machine learning models that have been used, and an overview of paper's contribution. In background, I'll discuss what loop invariants are, what ranking functions are. I'll give an overview of Loopy, which is a tool that has been developed in the paper, and FramaC. And verification task, I'll talk about algorithms in detail. In evaluation and results, we'll show the data of how Loopy performs over various categories of data sets. And we'll analyze and draw conclusions from the performance of Loopy in discussion and analysis. And in conclusion, we'll conclude with final remarks. So, program verification. Sorry? Is there a question?
No, I don't think there's a question, but there's some background noise. People, you can unmute yourself and then unmute only if you want to ask a question. Some background noise.
I did not really hear that. It was muffled.
No, you're coming through loudly. Go ahead.
Okay. Okay, so program verification is the process of mathematically proving that a program satisfies a given specification or a property It involves establishing a proof of correctness of programs with respect to a given property. And there are two main steps in program verification. One is proof construction, where you generate proof artifacts such as loop invariants or ranking functions. And in proof checking, you mechanically validate those artifacts using tools like SMT solvers. And there are two main important proof elements that are discussed in the paper. One is loop invariants for proving safety. For example, we say that assertion always holds. And ranking functions for proof termination. Example like loops eventually, we show that loops eventually exit. And what is the challenge that this paper is trying to tackle is, so proof construction is hard. So it requires a deep understanding of program behavior and some creativity. So this makes proof construction hard to scale or generalize, and it is also hard to automate proof construction. However, proof checking can be automated using tools like FrameRC SAT solvers. And in this paper, they have adopted the guess and check paradigm as a general approach to automate proof construction. So they guess what the the candidate proof could be. So the key idea is you let a ML-based system guess the potential proof, and then you use formal checkers like FrameRC with SMT solvers to verify those guesses. And then what it does is it separates creativity, which is handled by the ML model, and soundness, which is obviously guaranteed by symbolic tools. And in this paper, we use LLMs as a general purpose guesser. So machine learning for program verification. So guess and check methodology has made it accessible for machine learning models to be used in proof construction. And the trend has been to train models using individual tasks that require independent data set. It means that the authors, they can train. So what it means is that previously they had not trained did not train a single model to do everything. Instead, they train different models or use different kinds of prompt setup for each verification task. And some of the traditional machine learning models that have been referenced in the paper are some like one is data-driven verification, and in this paper they have used a tool called PIE, and then they understand the program behavior, especially during while testing the program. Another paper has developed a tool called Locust that uses machine learning to predict memory safety invariants for heap manipulating proofs, and then they use these predictions through a feedback loop with a verifier. And then there's something called continuous logical functions, where they learn precise formulas in SMT for invariants, and something called active learning over decision trees, where it is a teacher-learner paradigm, where teacher provides feedback, where teacher is the program verifier and it gives feedback to the learner. So they classify programs as correct, incorrect, or it needs further explanation. And based on that, learner, it builds a decision tree that can predict program behavior. Another custom trained ML models per task, they have used reinforcement learning to find loop invariants. Now, leveraging LLMs. So large language models, they are a machine learning model designed for natural language processing tasks such as language generation, and they are capable of performing code reasoning with natural language instructions. And they are trained on with self-supervised learning on vast amount of data. And these are some of the examples of LLMs, GPT-4, Lemma 2, and they are trained on vast diverse data. And this particular paper, we have used GPT-4 for most of the experiments. And with LLM, you can infer candidate proofs, the potential proofs, and they are a natural fit for our guess and check approach. And LLMs, they're already in use. They assist programmers, for example, in GitHub Copilot. So what is the paper's contribution? So they have built and evaluated a tool called Loopy, which is an LLM-based toolchain for program verification. They have curated a data set of C programs for multiple different program verification tasks. We'll look at this data set later. And they have evaluation with multiple LLMs. They have compared these LLMs. And there is also a comparison, compare the performance of Loopy with symbolic tool called Ultimate. So Ultimate is a symbolic tool which has won many awards in SVCom. And moving on to background, so we'll talk about loop invariance. So we have also learned in class something called hold logic, which shows program correctness. So program correctness is based on hold logic. So there is so if precondition P holds, then after statement S, post condition Q must also hold. And a loop invariant is a logical statement that, so here I is the loop invariant, P is the precondition, Q is the post condition, and LC is the loop condition. So a loop invariant, it says that it must hold before the loop starts, and it is preserved after every iteration, and it implies the post condition when the loop exists. And loop invariants, they are crucial for proving correctness of loops, and they also ensure that assertions are always satisfied. And ranking functions. So ranking functions are used to prove that a loop always terminates. Ranking function must be a non-negative. They must be non-negative at the start of each iteration, and they must strictly decrease with each loop iteration. And there are more complex ranking functions like lexicographic, where there is a tuple of decreasing values. And a lexicographic ranking function is useful when one value doesn't always decrease, but a secondary value can decrease and back it up, sort of. And there is something called multi-phase ranking function as well. So here one value decreases after the previous one becomes non-positive. And we'll look at overview of Loopy. So it has following components. The input is the C program, and we have an LLM which generates the candidate proofs, and we have Oracle. So in Oracle, we use FramaC as the Oracle, and it verifies the proof. And Loopy has these key aspects that make better use of LLM. So which are prompt engineering, which is just giving prompts to the LLMs, nudging, as in like you give more information to the prompts, and interplay between LLM and symbolic tool, where we make use of Houdini algorithm and repair algorithm, which we'll talk about later. So FramaC is a verification tool for C programs, and it uses ACSL, which is a C specification language, and it writes specification as comments in C code, and it supports invariance, assertions, and pre and post conditions. So now we move to verification of tasks. So here we discuss all of the algorithms. So verification task has an input, a C program, along with the property of interest that must be established. So we have used C language. So we have chosen C language based on availability of benchmarks and formal checkers, because FramaC uses C language. And the annotation, they are written in ACSL as comments in C programs. And there are two kinds of verification tasks: safety verification, where the goal is to come up with ACSL annotations that help FramaC in proving the assertions, and termination checking to infer a ranking function for a loop that proves its termination. So first we look at safety verification. As we said, the goal is to prove that assertions in the program always hold. So here the benchmarks have been curated from SVCom, Diffie, etc. And the programs have been filtered so that they are safe, that is the assertions hold, and they are small enough to fit in an LLM prompt, that is they are less than or equal to 500 lines of code. So this is the basic outline of how Loopy works. So as we go along, we build on top of this, but this is just the basic outline. So there is program P, and then you feed the program P along with prompts that we'll talk about later to LLM, and then LLM generates the loop invariant. And then this loop invariant, so Oracle over FramaC verifies this loop invariant for the program P, and if it is valid, then it is accepted. If it is not valid, then we'll see what happens, because so there are various algorithms that does different things when it is invalid. So we'll see later. So data sets for safety verification, they have been classified into three types. One is scalar loops. There are 469 benchmarks for these. So scalar loops, they only have integer variables. There's one main method and one loop, and they only use simple arithmetic reasoning. There's recursion, where there are 31 benchmarks, and they use recursive functions. And there are scalar types variables, and there are no loops in recursion. And in array or pointer programs, there are 169 of those, and they include arrays or pointers, and they are limited by FrameAC's handling of memory, because FrameAC does not support dynamic memory allocation. And so techniques to augment LLMs for safety verification. Now we'll start looking at the various algorithms. So first technique is providing domain specific instruction to the LLMs. We'll discuss the basic algorithm, and later we'll talk about the kind of prompts that are being used. So the input is program P, prompt template is M, and NC is the sorry, is there
I just want
yes.
to just pause here to
Yes.
see if people have any questions regarding the problem definition, the problems statement, and what it is, what the paper is trying to do. Is there any questions about the motivation and the problem definition? Okay, so if it's not, then I have a simple question. Basically, now here the LLM is being used to do the hard task, correct? In the verification, the MRC is already checking
Yep.
all the assertions. But of course, the
Sorry, sir.
MRC cannot, let me finish, cannot, invent,
Um,
do invent. So this LLM is really, I mean, this flow, which includes LLM as a big box, is helping you to.
Sir, your voice is not very clear. I couldn't really get the question. Your voice is not clear.
I will feel. I don't see why it should not. Okay. Can you hear me at all, or can you?
Yeah,
Can you
I
hear me
can
now?
hear you. I can hear you, but the voice is breaking in between.
Yeah, so I first asked if people had any questions about the
Right.
problem definition. And so I wanted to pause here if the audience had Alitra. Okay. So Alitra says, Alitra, you have a question? Why don't you, can you speak up? No. Okay, no questions. Yeah, I had a question. Is it here primarily LLM is being used? Can you hear me now, Ganesh? Yeah.
Is it, sorry, what?
Can you hear me now?
Yes, I can hear you now.
Okay, I'll speak slowly. Oh, I don't know why.
There is some echo on your voice.
Okay. Better now?
Can you say something more?
I think he's probably figuring something out.
Is it better now? Can you hear me?
Yeah. Yes.
Is it better now?
Only not much.
Okay.
At least not for me. I don't know. What about Ganeshri?
Yeah.
No, then I'm gonna, yeah, just hang on.
Yeah, now it seems to be better.
Is it better now?
Yes, I guess.
Yeah, it's much better now.
Are you sure it's better now?
Yes.
Yeah, it sounds much better to me at least. Yeah. There's not the echo is gone.
Okay. Yeah, I just wanted, I was going to ask. So, in short, this mainly you're trying to use LLM to do the hard part of the verification task, which in this case is to derive loop invariance and ranking functions to be able to do. So most of the rest of the easy task is being done by pharmacy. That a good way to
Yes.
summarize what the problem definition is?
So from what I've understood, yeah. So Framacy does the task where like automation is required. So LLM handles all of the creative task of like generating the proof artifacts.
Yeah, I ask you again. LLM does the loop invariant synthesis. All the rest of the check is being done by pharmacy, isn't it?
Yes.
Is that
Yes,
correct?
correct.
Huh?
Yes. Yes, it is
Okay.
correct.
Okay, thank you.
Yeah. Can I continue?
Yeah, please go ahead.
Okay. So the first technique that Loopy adopts is providing domain-specific instructions to the LLMs. But before that, let us see the basic algorithm. So there is input, where input has program P, prompt template M, and number of completions NC. So by number of completions, what we mean is for a particular prompt template, NC number of times the loop invariants are generated, and output. So output is success I, where I is the set of propositions which are strong enough to prove the assertions in P, or it returns a failure when strong loop invariants cannot be found. So I'll show the flow of the algorithm. So we have, okay, yeah, actually, okay. So we have a prompt template which is either M0 or M1. So we will talk about what M0 and M1 are later. So the prompt templates could be either M0 or M1, and we have a program P, and the prompt template is instantiated with program P, and then the instantiated prompt template is passed to the LLM, and this LLM generates the loop invariant I, and then this is fed into Oracle O, which is Framacy in our case, along with the program P. And then Oracle, if it returns true, then it is valid, the loop invariant is valid and it is accepted. If it is not valid, and if our number of completions have not been exhausted, that is, if it is greater than 0, then you run the loop again. Then you again reinstantiate the prompt template with the program and run the loop again. Otherwise, if we have exhausted our number of completions, then we return failure. Okay, and I also wanted to talk a little bit about the oracle. So the oracle that has
Yeah,
been
I
used
think,
to
can I stop you here? Yeah,
yes,
you can hear me now, correct?
yeah, yes, I can.
Yeah. Is there any questions from the class about this overall flow? Please ask, okay? If you have any questions. Okay. So I was in my previous comment, I was kind of wrong. I have one comment or a kind of question, Janashri. So the
Yes,
oracle, which is really from a C, is being used to check the validity of the loop invariant, whether it is correct loop invariant that is adequate to prove all the
yes,
aspects in the program. Correct? Yeah.
yes.
Okay. Yeah. Okay. Fine.
Okay. Yeah. So I wanted to talk a bit about Oracle. So in the paper, we have used it as a black box. So given the program P and set I, the invariant as input, it returns as output triple. So the output that it returns is one is B, small b, which is a Boolean value. So it returns true if P verifies with the loop invariant I, or it returns false. So here the small I, so these are the propositions, and loop invariant is actually a conjunction of all of these propositions. And so the other thing that it returns is IS, which is a subset of I, and it is a set of invariants that exhibit parsing error. So when B is true, obviously IS is empty, and INI is another subset of I, which is a set of invariants for which the oracle cannot establish the inductiveness property. And this can happen for two reasons: when the invariant does not hold at the beginning of the loop, and when the loop body does not maintain the invariant. So when B is true or when IS is not empty, INI is empty. And we assume that the oracle is sound, and the basic algorithm, so the basic algorithm that we have discussed here, this does not use INI or IS. Those will be used in the later algorithms that we will discuss. So here it only uses B. So if
Yeah,
B is true, then
I have one question here on the next slide.
this
Yeah,
this slide,
so the next slide.
this one.
Yeah, this one. Okay.
Yep.
So there is another outcome that is possible as well, where the set of invariants are syntactically correct, that there's no parsing errors.
Yes.
And set of invariants, every invariant in I is also inductive. But it may not be, the invariants put together may not be adequate to prove the property, the assertion after the loop. How is that handled?
So they've not dealt with this. So the oracle does not handle
Are
that
you
kind
sure
of.
about that? Are you sure that it does not do,
Yes.
and then program is not verified, no? The invariants are not sufficient to do. I'm not so sure if your answer is correct.
So can you please repeat the question once?
No, there is an other outcome. Is my voice coming out clearly?
Yeah, now it's good.
Okay, sorry. There's some technical issues now. I pulled all the plugs and I'm just talking into my laptop. Okay, so using my the microphone. So I will speak slowly. There is an other outcome. So you see, go to the previous slide.
This one.
Yes. Now, obviously, I thought that this would, if the invariant, either the invariant could be, there could be some parsing errors where it is very bad, okay, or some of them may not be inductive, which you showed, and there was an exit condition which you also showed for logic, that if upon exit the loop invariant must be strong enough to prove the post property, okay, the post assertion, correct? So that is doesn't seem to, at least in your next slide, that possibility is not addressed. So my
So
question is, if it is a loop invariant, is only if you get a loop invariant that is inductive but not able to prove the property, what good is it? So then, is that not addressed in the paper?
so they have given these two, the syntactically incorrect invariant and the non-inductive invariant, because they have some use cases in the later algorithms. So that is why the oracle outputs those. Um,
Right, but the question still sort of stands, right? So in the sense, of course, we can send to the oracle a set I, where let's say that some invariants are inductive, some invariants are not inductive, but in general, the conjunction of the all of the invariants in I is not
okay.
sufficient to prove the property.
Okay, so this set I, so by set I do not mean a set of invariants. So set I here is a single invariant. Um, so yeah, this could be an incorrect use like of set here, but Yeah, so by set, I mean the set of propositions, not set of, but conjunction of propositions, they form a single loop invariant. So here I is a single loop
I think,
invariant.
why don't you go ahead? I think
Sure,
either you're not explaining it properly, or I think from what I had briefly read the paper and even spoken to you earlier, that there is,
Yeah.
you can modify the prompt, and then
Yeah.
the oracle obviously will tell you whether it is the invariant that it generates is strong enough to prove the post property. If not, the oracle will tell you that. And I think there is a way that you can then go back and then instantiate. Okay, that is what my understanding is. But if you're saying that this methodology doesn't guarantee that the invariant it produces is adequate to prove the property, I have my own doubts about the utility of this method, and I don't think that that's what this thing does. But let's see. Go ahead. Yeah, continue.
Okay, so I'd like to explain this one more time. So here, so the LLM generates loop invariant I, which is a single loop invariant, and then Oracle takes this loop invariant along with program P, and then it generates. So, okay, okay, I see the point actually here. Okay, yeah. So this Oracle, okay. So this is the wrong placement of the slides here, but in this particular case, for this particular algorithm, the basic algorithm. So here, as you can see in line number 4, the IS and INI part, they are empty. They do not return anything because this particular I that you have passed is just a single invariant. It's just a single loop invariant. So there's no use case of IS and INI. I think it will become clearer when I explain some other algorithm.
Okay,
Um,
No,
I'll
I
wait.
think you should not deviate. Yeah, yeah.
Yeah,
Just
please.
go ahead with your existing.
yeah. Yes. Okay, so so as we said that there are two kinds of prompt templates, M0 and M1. So here M0 is the basic prompt template where the LLM is only told what loop invariant. So they're not told what loop invariants are, or any detailed instructions are not given. They only say they will only ask the output to be generated in ACSL syntax so that FrameRC can verify them. And this is an example of the prompt template, the basic prompt template. So here it is only asking LLM to generate the prompt in this particular syntax, like the code block that has been given here. And then another kind of prompt template is M1, which is domain specific prompt template. And here they provide more instructions to the LLM. For example, like how the loop, what the loop invariant is, or yeah. So there's more nudging happening here. And then as you can see, there are, so you have given rules here, and you have asked them to use implications. So also all those sort of things. So basically, you're giving more instructions and you're setting up rules for LLM um, to generate the loop invariants. And then comparison between M0 and M1. So this is the program, and uh, the text that have been highlighted in green, they are the loop invariants, and the top two invariants, the first two are generated by using the basic prompt M0, and the last two are generated by domain specific prompts M1. And as you can see, so we have to assert that I is equals to J, and the top two invariants, even though they are correct loop invariants, however, they do not satisfy the assert statement. However, the bottom two loop invariants, no, they do.
Okay. I
Okay.
think that this slide answered my question. So the basic prompt thing can only generate invariance. It doesn't guarantee that it is strong enough to prove. But the more advanced version of the prompt M1 will generate the other two invariants, correct? Yeah.
Yes.
Oh, okay.
So the other technique that Loopy uses is something called Houdini algorithm. And Houdini algorithm, they're analysis tools. They are used for discovering which invariants are sufficient to prove a program correct. Um, and LLMs, the output could be syntactically invalid, or it could not be a valid invariant, or the correct invariant could be spread over multiple completions, as in multiple loop invariants that were generated for a single prompt template. And in such cases, Houdini algorithm is augmented with the basic algorithm that we saw earlier to prune the incorrect outputs. And okay, so here is an example where Houdini algorithm could be used. So the candidate, so here we have to assert that x is equals to n, and the candidate loop invariant is this, like x is greater than equals to 0 and x is less than n. And uh, okay, so this is also another, okay, sorry, I've made a mistake here, but then this is also another possible LLM output. Uh, the top thing, the candidate loop invariant for LLM is this, along with all of these. So there are 1, 2, 3, 5 possible candidate loop invariants. I've placed them in separate points. So yeah, so all the completions together have the correct components, but no single completion is correct in itself. So this is where you can use Houdini algorithm. So this is the flow showing how Houdini algorithm can be integrated into our basic algorithm that we had discussed earlier. So up until this point, it is just the same. So the prompt template, either M0 or M1, is passed to is given
Yeah,
to be
I want,
instantiated.
Ganeshni, I want to stop here. Go to the previous slide.
Yes.
Yeah, what I didn't quite get what exactly Houdini does. You know, what does it generate? Does it fix a thing? Does it generate a new prompt, or does it fix? What does it do?
So I'll be discussing the algorithm here, the
No,
Houdini
no, no,
algorithm.
no. I know you'll be discussing the Houdini algorithm. I want to understand, as a
Yes.
black box, what does it do? It takes a program and then outputs something. What? I mean, I know how you're going to be describing later on. I want you to answer, what does it do? What is the
So
problem that it is trying to solve or fix?
okay, so Houdini algorithm, what it basically does is, given a set of invariants that could not satisfy the property, so you take these set of invariants and then you conjunct them, and then you see. So in this conjunction, you see what are the subsets that are syntactically incorrect. You prune them out of the set, and you also see what are the non-inductive invariants, and you also prune them out of the set.
Ah, okay. But it doesn't address the third thing, where the invariance might be correct but not sufficient to prove the property. That it does not. That
Yes, that
problem.
it does.
Okay.
Yes, that it does. Okay.
And
So
how is this Houdini algorithm used in the previous flow? Because you didn't show the
yeah,
Houdini box in the previous. You're showing
yeah,
it here. Okay.
yes.
Okay, fine.
Okay.
Thank you.
Yeah. Okay, so what we do is, so this is similar to the basic algorithm, the initial part where you have the prompt template and program P, and then you instantiate it, and then the instantiated prompt template, you pass it to the LLM, and then you generate a loop invariant I, and then if Oracle O can verify this loop invariant, then it is valid, the loop invariant is valid, so you accept it. Otherwise, you get a record of all of these loop invariants which are failing. So you keep a collection of those, and then you run this loop NC many times, which is NC is the number of completions that we discussed earlier. And then if NC becomes 0, then you call the Houdini algorithm with the program P, and IU is the collection of all of the loop invariants that have failed here. Uh, okay. So now I'll show the.
No. Go back to the slide. But okay, so there is kind of an arrow going into it, into Houdini, but nothing is coming out of it. Now, what comes out of it will be the fixed invariance. That's it. So Houdini, okay, Houdini, does it use LLM or does it not use LLM?
Yes, Houdini does. I'll be explaining.
Okay, I got it.
Does not. Houdini actually uses Oracle to prune out the.
Oh, that's what it does. So the LLM, yeah. So Houdini somehow has its own bag of tricks,
Yes.
and that does not involve the use of LLM, and it just fixes it. Huh?
Yes, fixes
Okay.
the set of loop invariants.
Yeah.
Okay. So this is the flow of Houdini algorithm. So you take as the input the set of invariants, as we discussed here. IU becomes IU. So we take the set of invariants and program P, and we first check whether these set of invariants is empty. So if it is empty, then you return failure, and if it is not empty, then you pass this program P along with the set of invariants to the oracle. And if the oracle, so recall that P becomes true when for this set of invariants the program P is verified. So if P returns true, then you return success along with the invariant I. And if it returns false, then you first check whether there are any syntactically incorrect invariants. So if there are, then IS is not empty, and then you prune out IS from I. And if it is empty, if IS is empty, then we check whether the non-inductive invariants are are there or not. If there are, if I and I is not empty, then you prune out I and I also from I. And then if I and I is also empty, then return failure. Uh, you say that. So because even though the loop invariants are correct, but they are not enough to satisfy the given property for the program. So that is why return failure. So yeah, this is just the algorithm here, where you have, so this is the inference, the basic algorithm, where you keep a collection of all of the invariants that loop invariants that do not satisfy the program, and then when the number of completions have been exhausted, you call Houdini along with the collection, and in Houdini you call the oracle and you get the set of IS, I, and I, and if B is true, then you return success with I. If it is false, then you check whether IS is empty, and if it is not empty, then you prune out IS. Else, you check whether INI is empty, and if it is not empty, then you prune out. So here there is a error, but it is supposed to be INI, and you prune out INI. And if INI is empty, then you return failure. You do not do anything about it when there is no syntax error or when there is no non-inductive invariance. So yeah, so this is just basically explaining the same thing. So properties of Houdini. So it is sound. So only returns success if Oracle verifies the program. That is when P is equals to true. Only then it returns success. And it is efficient. At most linear number of Oracle calls. Linear number in terms of the number of loop invariants. And it guarantees that you find the largest inductive subset because you keep on pruning out the invariants as long as you don't get a set of invariants that satisfies the program property. Um, So next is so the next technique is using LLMs to repair incorrect invariants. Now, so
Yeah, but
LLM generated.
what do you mean by incorrect invariance? Houdini already has guaranteed that it gives the largest subset among that of that are inductive, correct? Huh?
Yes.
Yeah, but here repairing incorrect means, will you explain? I mean, what is an
Yeah.
incorrect in something that is not sufficient to prove the property? Is that what you mean by incorrect?
So by incorrect, I mean, okay, I'll give you an example.
Okay.
So in one of the benchmarks, so the what the program does is it loop iterates from 1 to n, um, from index 1 to n, but then loopy infers the invariance where the index variable ranges from 0 to n. So this gives a syntax error. So so using repair, you kind of fix these syntax error. Instead of discarding the set is and ini, you try to fix the invariance if possible.
Okay, this is another mechanism. I thought Houdini also does that. No?
No, Houdini
I,
rejects this.
I,
Huh?
yeah, go
Sorry.
ahead.
No, you were.
No, go
Yeah,
ahead,
go
go
ahead.
ahead.
Yeah.
No, so I had a couple of questions about the previous slide in the flowchart. I can just go back to the one. One before when you're introducing Houdini as a high level flowchart, not this one, the one, yeah. So okay, so now that we've talked about the Houdini algorithm, just to understand a bit about what's going on here. So what we're doing is we're passing a program, adding some prompts, sending it to the LLM, and asking it to generate some invariants, and it's going to generate a bunch of these invariants. So this is the set of
Yes.
invariants that you keep talking about, right? Now,
Yes.
so if this, so when this set of invariants gets sent to the oracle, right?
Yes.
If the conjunction of all of them is
Yeah.
itself a valid loop invariant, in the sense that the conjunction is inductive and the conjunction is strong enough to prove the property, then we say valid and accept, right?
Yes.
Okay, so now if the conjunction is not valid, then either the conjunction is failing to induct or the conjunction is not strong enough to prove the, or I mean, the either the conjunction is failing to induct or the conjunction inducts and it's just not strong enough to prove the property, right?
Yes.
So what happens in that case? So when it fails, there's two cases, right? So either the conjunction of invariants in this set I
Yeah.
is not strong enough to prove the property, or this conjunction. I mean, either the conjunction in the set I in fails to induct, or it is inductive but is not strong enough to prove the property, right?
So
So
that
these are
was
the
my
case one
original
and case two,
question
let's
too.
say.
Yeah, yeah.
Yeah, yeah. So can you just explain what's happening in those two cases in within the Houdini algorithm once?
Okay. So the first case is when the conjunction, they are correct but they fail to prove the this thing, right? When they fail to prove the property.
The first
So
case, let's say, is that the conjunctions do not induct. Let's take that case first, maybe.
okay, so then so for the conjunction you pass it to the oracle, and then you prune out, you get all of the uh, INIs, non-inductive invariants for that particular subset, for that particular
Mm-hmm.
conjunction. You
Mm-hmm.
get all of the
So
invariants.
will INI be empty or non-empty in this case?
uh, when it is non-inductive, when the
Yeah,
entire I is non-inductive. So then,
yeah.
so that, but probably depends on whether the IS. So here in the algorithm, what is the algorithm? Okay, so we first look at whether in line number 5, we first look at whether IS is empty or not. So if the
Mm-hmm.
if there are syntactically incorrect invariants, then you first remove them
Mm-hmm.
and then you run the oracle again. So you don't
Sure,
go to
sure, sure.
the
Let's just assume that all the just for simplicity, let's assume everything is syntactically correct.
okay. So if the conjunction of the invariants, they are non-inductive, um,
Mm-hmm.
then the oracle, then you run it through the oracle. Then so sorry, what was the question?
I mean, no. So we're looking at the case in this algorithm when the conjunction of the invariants is not inductive, right? And we have assumed that IS is empty, as in everything is syntactically correct, right? So of course B will be false, and then we are in the branch where IS is empty, and now we'll either go down the INI is empty or the INI is non-empty, right? So I was just asking,
Right, right.
do we know anything about INI at this point, given the fact that we are assuming that this conjunction of invariants does not induct? Do we know whether INI is empty or not?
Um, so I don't think we know, but because if okay, so if the conjunction of invariance is non-inductive, and so INI is empty when the conjunction of invariance is non-inductive, and the oracle returns an INI which contains non-inductive uh, invariance.
So wait, so INI will always contain non-inductive invariants, right?
No, possibly not, because if the conjunction of invariance is valid, if it is a valid loop invariant, but if it does not satisfy the given assertion, then
Right. So
INI will be
when you say
No, but
valid, what do you mean? Do you mean inductive?
yes, inductive.
Right. So let's say the conjunction of invariance is not inductive. Let's just look at that case. What will
Yeah,
happen then?
yeah. Then INI will be non-empty.
Okay. Why is that?
Um, because in the conjunction, if there is some non-empty, uh, okay, I can't think of an example right now. Um, So if there is a conjunction, so if there is a set of loop invariants whose conjunction is giving you a non-inductive, yeah, let me think.
Okay, sure. Maybe you can take this offline. It's
Yeah, I somehow think, I mean, I believe Houdini gives the largest subset of those in set of invariants which are inductive, presumably. Okay, that's
yeah,
what
I think that's also what's happening, right? So I
yeah,
think what the
that's what is
oracle will
happening.
do.
Yes.
Right. So I think what if the conjunction of invariance in I is non-inductive, then what the oracle can do is, see, I mean, if the conjunction is non-inductive, at least one of the component conjuncts has to also be non-inductive, right? So if each
Correct.
of
That's
my
right.
small I is in capital I is inductive, then a conjunction of them will be inductive, right? So I think what the oracle will do in INI is that it will give me those small i's which are non-inductive, right?
Non-inductive, so
So
it will
if
separate that, and
it'll
then
separate those, right? So
yeah,
now
it'll
we have
separate.
we have another set which will hopefully now be inductive. We'll repeat the checks. Suppose some of them still are non-inductive, it will get separated again and so on,
Yeah,
right?
but what is not clear, I think that's what. Otherwise, what is the use of Houdini? Okay,
Correct,
Houdini
correct, correct. So
has
it's
to
it's
do
just it's just
something.
kind of, yeah. If the LLM has generated a bunch of inductive invariants, I mean bunch of candidate invariants, right?
Yeah,
And let's say that somehow some conjunction of them is inductive, but it's not clear what conjunction. Then Houdini will be able to find that conjunction basically.
that is one. But what is not clear to me from what Jnanashri is describing is if this Houdini also does something for the second case. Okay, the first case we have
Right. I
some,
don't
but the
think
second
it.
case it doesn't do anything, or does it? What Jnanashri?
Right. I don't think it
For the
does
It does
second,
not.
because.
It,
it does
it does
not do
not
anything.
do anything for the second
It
case.
does not do anything. It doesn't
Yeah.
even suggest anything or not. I mean, of course,
Correct.
you
Because.
already
No,
know
that
that from the oracle that it is not sufficient, but Houdini is not
Right.
doing anything. Okay.
Right. So I think what will happen is, see, the oracle will say b equal to false, right? But then it is the case. In the second case, the invariant is actually inductive, right?
yeah,
So all of the components will end up being inductive, which means INI is actually empty, right? IS is also empty. So we end up
yeah,
following this path: b equal to false, IS is empty, INI is empty, and the Houdini ends up returning failure. So basically, if the invariant is inductive, but it's still not strong enough to prove the property, there's no way to get rid of any conjuncts to make it be able to prove the property anymore, right?
Then it
yeah.
returns success, I think so.
So no, then
Yeah.
it returns failure. I
In
mean,
the
yeah, it returns failure. So basically, Houdini starts with this conjunction and it keeps weakening the conjunction as long as there are some counterexamples to induction. And then once it's inductive, then it just sees if its now resulting thing is strong enough, right? But if it's not strong enough, it cannot strengthen it back again. So it cannot go both ways. It's just doing this one sort of monotonic thing.
Yeah,
It just
but
drops
it
things from the
doesn't,
conjunction and
yeah,
weakens
it
it.
doesn't strengthen it, but it just returns something which is inductive, at least a subset.
It is inductive. Yeah, it is at least inductive.
Yes.
Yeah, yeah.
When does it return success then?
Oh, I think it only returns success. The oracle returns success. That's yeah. So if somehow it's while it's doing this weakening, we get to a point where the conjunction itself is strong enough to prove the property as well, then it'll return success.
Ah, okay. So then there is nothing to be done. I mean, we don't need to do any repair. Okay. And the
Right. We don't need to do
The
anything.
the repair happens in another technique that I'll discuss now.
No. It happens in
Correct.
another
So
technique. I understand that. But the question is, in the overall scheme of things, when does repair kick in? That is the question that we are discussing. Maybe, because to give a big picture, okay, when do you need to use repair? That is the question that we are addressing after Houdini, okay? Houdini
And just to
may,
again,
yeah.
sorry, go on.
No, that's what I'm repeating. Houdini may or may not. When it returns a success, you're done. There's no need to repair. Otherwise, the Houdini just returns the largest subset, which is inductive, and then says, do whatever you want, right? Yeah. Am I right?
Yeah. So
Yeah.
I think that makes sense to me. Ganesh, what do you think?
yes, that is correct.
Let's see. So if she continues, then we can. Yeah.
So yeah, and just one clarification I want to understand at this point. I mean, is it so? If this Houdini algorithm is failing, then basically what do we have is we have this set INI of things which we know. I mean, components of the invariant which we know failed to be inductive, right? We have this set is of components which were syntactically incorrect even, and we have this set I which is we know that it is inductive but it's not strong enough to prove the property, right? So we have got these three different sets which are weak in three, I mean not good enough in three different ways. One is is which is not syntactically correct, one is INI which doesn't even induct, and one is I which is inducting but doesn't isn't strong enough to prove the property, right? Does is that what we have at the end of Houdini if it fails?
Yeah. Yes, that's correct. Or I could also be empty. Even then, it.
I could also be empty. Okay. I being empty means that nothing is inductive. Yeah, sure. Yeah, makes sense. Yeah, I think I mean any
That's
of these
okay.
sets can be empty.
Yeah, but that is a special case. No, I being empty is a special case of this thing. Yeah. Okay. That's when you go in to do repair. Okay, for doing it. I understand. Correct. Yeah. Yanashri?
Yeah, when the Houdini algorithm returns failure, then you.
Okay. Good. Now we understand. I hope.
Yeah.
the
Now
rest of you
this picture is
understand
clear. Yeah. Okay. Please go ahead.
Can I continue? Okay. So. Yeah. So this is the.
Yeah, now I can understand, okay, what incorrect invariance means. It is just those three cases that we just now identified. Okay, yeah, go ahead. Please. Yeah.
So,
what happened?
Yeah. So So okay. So instead of discarding them, will I get extra time or should I?
We started
Yeah,
only
I mean,
30, so you still have half an hour. Okay, and half an hour. You still have half an hour. Your regulation time. Okay. But if you want more, we can use, because I think the idea is, to let you, let all of us, including us, the two of us, also get to understand the content of the paper, which you have done, invested a lot of time. And also the 4 o'clock talk by Maya is cancelled. Okay. So you have extra time. Yeah.
So just a point of logistics. I mean, will the other presentation after 4 o'clock be pulled forward, or is it the
I
case that
don't mind
we'll?
doing it. I will send Shai Shashank a note. Who's not here? Is he here?
Right.
Lucky, can you do me a favor? Lucky?
Yes, sir. Yes, sir.
can you get in touch with Sai Sasank and ask
Okay,
him to join? He's supposed to, he took your spot, okay?
yeah, yeah. Yes, sir.
Yeah, and ask him to see if he can show up earlier,
Okay, sir. I'll
so
get in
that
touch
as
with him.
soon as Jnanashri finishes, he can go ahead. Yeah, if you can do
Okay,
that.
sir.
Yeah. Okay,
Yeah.
thank you.
Can I
Yeah,
continue?
go ahead now, Jnanashri. This is quite interesting. Now I think, sorry for all the interruptions and for your patience.
Yeah. Sorry for this logistics interruption between of your presentation. Yeah. Sorry about that.
Completely fine. Yeah, I'm sorry if I'm not able to explain it correctly or properly. Um, yeah,
Great job.
so yeah, so yeah, LLMs. So the Houdini algorithm. So it could fail due to like minor errors like syntax or non-inductiveness. So instead of discarding those subsets, we will repair them using LLM, guided by Oracle error messages. And we'll first see the flow because I think that will make it easier to explain. Um, so yeah, this is a build on top of the basic algorithm. So here the only change is that when Houdini algorithm returns failure, then you call the repair algorithm.
Yeah. Now everything is very clear, Jnanashri. This is a very good incremental enhancement to your flow, okay? Which makes it clear. Yeah. Okay. When after Houdini fails, you will use repair. Okay, good.
So okay, so repair is called using P, which is the program, IU, which is the collection of set of invariants that we generated in the basic algorithm, and NR is the number of completions. So in these two, so NC and NR, there are two number of completions that have been used here. NC runs for, so NC is for
But
the base.
here, I have a question. I don't know what you meant by number of completions, NR. I didn't quite get that. Did I miss something? What is a
Yes.
completion?
Okay. So yeah, I explained it in the beginning. So number of
Can you
completion
remind?
means for, sorry, yeah. So the for the okay. So number of completions is for a particular prompt template. So
The
you
number of times you have
generate the,
iterated. The number of
yeah.
times you have
So
iterated.
yeah,
Okay,
for
okay.
example,
That's
here
all.
NC is the number of completion.
Yeah. NR is the number of iterations for repair. Is what?
Yeah, for repair. Yes.
Okay, got it.
So
Sorry
yeah.
for
So
the.
it's okay. So so in the other algorithms we had used NC 15 times. We had set NC to 15, but in these two algorithms for NC we have given it we have given the number 8, and for NR we have given the number 7, so that NC and NR together they are equal to 15. So which means that NC runs 8 times and NR, so they'll seven loops using NR. 7 times the loop runs. Okay, so
Yeah, but in
yeah,
this
so
in this picture, the NR loop is not shown. There
yeah,
is.
the NR is in the repair algorithm.
Oh,
NR is
inside it.
used in the,
Oh, okay.
yeah,
Okay, got it.
yes. So NR is used in the repair.
Okay. Yeah.
Okay, so here the goal is to infer loop invariants using LLM, and then you verify or repair them if needed. And so IU is the so it is the collection of all the candidate invariants that we have generated. And then yeah, NC is like you repeat NC many times using the prompt template to get the candidate invariance I. And then you try Houdini, and then if it returns success, then obviously it is success. You don't need to use repair algorithm. But then if it returns failure, then you call repair with so you call repair with program P. I is the set of invariants from this inference algorithm, and NR is the number of completions that we'll use in repair algorithm. Okay, so now we'll look at the repair algorithm. So first, what it does is it queries the oracle O with program P and the loop invariant I from the inference algorithm, and then the oracle generates. So since using this loop
So
invariance,
sorry, just sorry to interrupt, but just to clarify again, so this I that you're talking about, it is
yeah,
the I coming out of Houdini, which is all of those, it's a conjunction of those invariants that were inductive but not strong enough to prove the property, is it?
no, so it is all of the invariants.
Oh,
I
okay,
use
all of the
this,
invariant. Okay, okay,
yeah,
okay, sure. So
not the
it's
one
it's
coming from Houdini. Yeah.
correct, correct. So it's basically, if I think of the one coming from Houdini as IS, INI, and I left, it's the union of all three of them.
Yes.
Okay, okay,
Yeah.
okay,
Correct.
sure, sure. So it was
Yeah.
what we are passing into Houdini in some sense, yeah.
Yes. The same set of invariants.
Correct, correct. Okay, sure, 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 sure.
Yeah. Okay. So yeah. So since the Houdini returned failures, obviously Oracle will also fail for these set of invariants. So then, uh, so obviously B will be false, and then you will also get IS and INI. So either IS will be non-empty or INI will be non-empty, and then using this is ini and then program p and also the loop invariant, the set of loop invariants that we discussed just now. So using this you instantiate the prompt template mr. So mr is a specialized kind of prompt template that we'll see later. So for now we'll just look at the flow, and then we'll instantiate the prompt template, and then this prompt template is passed into an llm. And here I'm sorry, but then I've used the same I for this as well as the above one, the one
Sure,
that
but
we
it's
got in
actually a
the
different
inference
I, right?
algorithm. Yeah, but it's a different I. So
Yeah.
the loop invariants are generated, and then you pass the loop invariants through an oracle, and then if it's valid, then you return and accept, and if it fails, then you call the Houdini again using these new set of loop
Yeah,
invariants
so
that have
here
been
I have a
generated.
couple of questions or clarifications. Okay, so it is interesting. So what you now have is earlier the basic prompt was just MP, but now you are passing it to additional information, ISI, etc. Correct? And that's
Yes.
yeah, and that is additional. I mean, the prompting now has additional information to LLM to be able to generate some additional invariants. Correct? Yeah.
Yes, that's correct.
Good,
Yes,
good.
that's
Yeah,
correct.
now I understand. Everything is falling. Thank you.
Um,
Yeah.
yes. So if the oracle fails, then you call Houdini, and if Houdini, given the program and the invariant, if it is able to generate a successful result, then you will accept the loop invariance that has been generated from Houdini. If it fails, and if the this is the number of completions for the repair algorithm, and if the number of completion, if you still have not exhausted the number of completions, then you will go back to the instantiation process again, where using the prompt template you will again reinstantiate the prompt template and call the llm again, and you repeat that. Otherwise, if you have exhausted the number of completions, then you return failure. um, is there any question for this?
Yeah, I think the rest of you folks should ask questions too. I know that you guys have not read the paper that we have at least have been interacting with. I think, and Diganta has read the paper. I have only skimmed the paper, so we are asking pointed questions. But you guys can ask basic questions too. I mean, like I said, if there is something that you're completely missing or you want to find out, okay, so I think you should. And the earlier during the talk that you ask, the better it is. So that's the thing. But no, and no point. Your questions will be, uh, will be not helpful. Okay. So, uh, fine. Okay. Good. Only one question I had was, see, in all these things, now Houdini is once again there inside the repair loop as well, because new invariants are being generated, correct? So
Yes,
they
correct.
need to be fixed as well, like those syntax errors and then non-inductiveness, etc., etc. Correct? So
Yes.
that's all. So, but the whether whatever is generated and fixed is sufficient to prove the property, that is done only using Oracle. Correct? Yeah.
Yes.
Yeah. Okay. Okay, Gyansh. Yeah, I got it. At least I was able to do. So, does the rest of the folk have any questions? Okay. Yeah.
Um, so we'll talk about the prompt that has been used in the repair algorithm. That is this prompt, MR. Um, so the prompt, it has been instantiated using the we have the program P and the invariant, the original invariant that we got from the basic algorithm I, and ISNII that generated through this running this oracle initially. So we'll talk a bit about what the prompt looks like for the repair algorithm. So here is an example. So if the error message indicates a syntax error, so if is is not empty, right, in a loop annotation for fix the line with the syntax error, and then to fix the non-inductive invariance, you try the following. So if an invariant is preserved but not established, so what do we mean by preserved? Preserved means if the invariant is true at the beginning of the loop iteration, then it remains true after executing the loop body as well. And established means that the invariant is true at the beginning of the loop. So if an invariant is preserved but not established, means the invariant is not it is not guaranteed to be true before the loop starts. That is at the loop entry. So if that is the case, then you add a clause to the invariant to make it established. A clause that makes the invariant hold before the loop begins. And if an invariant is established but not preserved, that is, it is true at the beginning of the loop, but in the iteration it becomes false, then you add a clause to the invariant to make it preserved, a clause that makes the invariant hold after the loop ends, assuming that it holds before the loop begins. And if none of these are the cases, if an invariant is neither established nor preserved, so you remove it or replace it with a different inductive invariant. If none of the above is possible, you add a new loop invariant to strengthen the existing invariants. So this is what the prompt is. And so, yeah. So this is just explanation of whatever we saw.
I go back to the previous line. So what you show on the right is the prompt.
Yes.
Okay.
The image is the prompt.
Oh, I see. So you include the error message sent by pharmacy also in the prompt, huh? Okay.
Yes, this.
Okay, and then you explain in English these things, huh? Okay.
So this is just the description of inference algorithm. Like, so it is same as this, but then in try Houdini, if Houdini is successful, then you return success. Else you call the repair using program P, IU, and NR is the number of completions for the repair algorithm. And this is the repair algorithm. It's just a description again. So you call the oracle, and then you identify what syntactically invalid invariants are and what non-inductive invariants are, and then you try NR many times. So you use repair prompt MR with program P. The I here is the set of invariants that we generated in the inference algorithm, and IS and INI that we generated from the oracle. And you generate new candidate invariants using LLM. Then you query the oracle again, and if it is valid, you return success. Else, then you run Houdini again on the updated set I. Updated set as in like the one that you got from the LLM here. And so if Houdini succeeds, you return success. Else, you reduce, retry, and then you count and repeat. And if all the attempts fail, then you return failure. Okay. So here the soundness is guaranteed by the oracle and Houdini as well. So recall that Houdini also uses oracle. So yeah, it is just guaranteed by soundness of the oracle. And efficiency, only a few retries, NR, so it avoids redoing full inference. And success rate helps salvage and refine partially correct LLM outputs. And yeah, it bridges LLM intuition with symbolic tools efficiency. Um, and now we'll talk about the second kind of verification that is done, which is termination checking. And then, so here the goal is to prove that loops terminate, and it requires finding ranking function, which is a value that decreases after every iteration, and also a supporting loop invariant. So the invariant, they ensure that conditions are always true during the loop. And so without, if you don't use the invariant, the ranking function might be invalid, or it could also be safe. It could also be unsafe. And the types of ranking function that we used are simple, lexicographic, and multiphrase that we discussed earlier. And the benchmarks are generated from, we get the benchmarks from termination, competitions, and other OSS bug study. And data set filtering and preparation. So we only include programs with one loop, and there are no assertions for termination, and we only use scalar variables. And comments are removed to prevent giving hints to LLMs. And so the benchmark size there are 281 programs. So this is the flow of the termination algorithm. So, uh, so there is a prompt template M, and then there is, you instantiate it using the program P, and then you pass this instantiated prompt template to the LLM, yeah, and then you generate, V is the ranking function. So you generate the ranking function here, and then there's another prompt template, MI. So you instantiate this particular prompt template using the ranking function V and the program P, and then you send it to an LLM and you generate loop invariant, and then you keep a record of it, and then you do this, that is instantiating the prompt template M1 with V and P NI many times. So then, yeah, and then once that is done, you run Houdini on these set of loop invariants that have been generated. And if the Houdini is successful, okay, so if the Houdini fails, then you go and reinstantiate and then generate new ranking function again. But if Houdini is successful, then you call the oracle with program P. V is the ranking function, and I is the set of loop invariants that we have generated here. And if it is valid, then you return success along with the ranking function and loop invariant. And if it is if it fails, then if NV is another number of completions here, and if NV has been exhausted, then you return failure. Otherwise, you go back and reinstantiate to generate new ranking function again. Uh, so is there any question? We'll also look at the algorithm now.
Oh, you can go ahead.
Yeah, okay. So this is the algorithm. So you instantiate prompt template M with P, and you query the LLML to infer a ranking function V, and then you instantiate prompt template, another prompt template there is. So MI with P and candidate ranking function that you just generated V to query LLML, and you do this NI many times to infer set of loop invariants I. And then you invoke Houdini algorithm with program P and invariant I. If Houdini succeeds, then invoke the oracle O with P, the ranking function B and the loop invariant I. And if the oracle returns true, then it's a success, and you return success with B and I. Else you repeat the algorithm until it succeeds, or it exhausts the maximum number of tries, that is NV times. So yeah, so that is the termination algorithm. And so now we'll look at evaluation and results. So tool that we evaluate on in this paper is Loopy, obviously. And benchmarks are, there are 469 scalar loop programs, 100, sorry, I'll drink some water. Okay, so there are benchmarks which contains 469 scalar loop programs, 169 array-based programs. There are 31 recursive programs, and for termination we have 221 programs. And then these are the LLMs used, and verifier we have used from us, but mostly they have used GPT-4. And this is an overview of comparison. We'll look at it in detail. And so the first data set consists of 469 programs of scalar type, and there is one main procedure and then one main loop here. And the second one is an array loop, so programs with array loop, and there are 169 of those. And there is a single method with at least one array or pointer. So the third data set consists of 31 programs with recursion, and there is only scalar types and there are no loops. And these benchmarks, they have minimum of 1 and maximum of 4, and they average about 1.4 non-main methods. And so yeah, and then there's termination, which has about one single method and one loop. So here these are the features that I just talked about, that is the number of loops and number of main methods that have been used. These are the total number of benchmarks, and here is the performance using vanilla LLMs, and here is the performance using Loopy, and this is Ultimate, which is the symbolic tool that we talked about before, and this is using Loopy plus Ultimate. And here, as you can see in the scalar loop,
So what does
Ultimate,
using Loopy plus Ultimate means? How is Ultimate used in this Loopy frame?
that I'm not aware of.
Or is it simply that they tried with Loopy? If it doesn't succeed, then they use Ultimate, or you don't know? Huh? Okay, that's good.
That has not been mentioned, and I did not look it up.
Yeah, okay.
Okay, so Ultimate has a higher success rate in the scalar loop. So out of 400 and out of 469 programs, Ultimate they validate 430, whereas Loopy validates 398. So, however, we find that there are 31 benchmarks that Ultimate does not solve, but Loopy can solve, and there are 63 benchmarks that Ultimate solves, but Loopy does not. So Ultimate and Loopy combined, so I don't know how the combination happens. I'm sorry, I have to look that up. Ultimate and Loopy combined can solve 461 out of 469 benchmarks. Yeah, and so prompt engineering impact. Prompt engineering, like remember what? So M0 is the basic prompt, and M1 is prompt which are domain specific. And with M0 and 15 completions, so GPT-4 solved 236 out of 469 safety benchmarks, and with M1 and 15 completions, it solved 293 out of 469 benchmarks. And effective Houdini. So Houdini filters non-inductive or syntactically incorrect guesses. And with M1 plus Houdini, there were ChatGPT-4 could solve 383 out of 469 benchmarks, and plus 90 benchmarks over using M1 alone. And so there, like, only linear number of calls were made to Frame-RC, linear number in terms of number of loop invariants. And effective repair, when Houdini fails, Loopy applies the repair prompts, and so you get like information from the oracle, the error messages, and then additional 15 benchmarks are verified when repair was used. Uh, so final count 398 out of 469 with GPT-4. And now if you compare LLMs with M1 plus Houdini, where number of completion was 15, GPT-4 could solve 383 out of 469, GPT 3.5 could solve 370 out of 469, and Code Llama could solve 289 out of 469. So LLMs were different subset of benchmarks, verified different subset of benchmarks, suggesting if you combine the LLMs, then you can get better coverage. And results on termination benchmarks, the termination algorithm that we discussed. So here prompt M2 means the basic ranking function. So 133 out of 281 were verified, and with lexicographic ranking function, 171 out of 281 were verified, and with multi-phase ranking function, M4, 181 out of 281. And ultimate could solve 236 out of 281, and if you combine loopy and ultimate, you could get 255 out of 281. Now results on array and recursive programs. So array benchmarks, so there were 169 programs with Houdini but no repair, where the number of completion was set to 8. So M0, so with the basic prompt, 60 were solved out of 169. With M1, 102 were solved, and with M1 plus arrays, when array specific hints were added to the prompt, we could solve 127. And so out of the 42 cases that were not solved in this M1 plus array specific hints, there were about 9 benchmarks for which Loopy infers the correct and sufficient loop invariant, but Frame-RC fails to verify. So here we can see the drawback of Frame-RC as well. And yeah, so recursive benchmark, there are 31 benchmarks, and Loopy solved 16 of those, ultimate 20, and combined they could solve 23. And runtime comparisons, average time per benchmark. So Loopy took 186 seconds, whereas Ultimate took 23 seconds. And Loopy runtime includes LLM inference, which took about 119 seconds out of 186 seconds. So key takeaways from evaluation. LLMs, especially ChatGPT-4, are effective at generating useful proof candidates. And if you use prompt engineering plus Houdini, results there were huge performance boost compared to just using prompt engineering. And Loopy outperforms or complements symbolic baselines in many cases, as we saw the performance with Loopy with symbolic baseline was comparatively better. And discussion and analysis. So strengths of the approach. So leveraging natural strengths of LLM, so you can recognize patterns, and there's like flexible code understanding. So this combines LLMs with sound symbolic checking, that is Frame-RC. And there are 3 techniques used, that is prompting with simple prompts as well as domain specific prompts. So for filtering we used Houdini algorithm, and repair, and which is competitive with state-of-the-art symbolic tools like Ultimate. And limitations. LLM generated annotations are often, so we saw that there could be so many syntactically incorrect invariants or non-inductive invariants, and there could be sometimes invalid in ACSL format. And So they are prompt sensitive. So success, it highly depends on the wording of the prompts, and Loopy's verification strength is only as strong as the oracle. So Fremacy doesn't always provide informative feedback. So, and we also saw that Fremacy has limitations in terms of allowing dynamic memory allocation, and also supporting recursive specs. And so results depend on specific SMT solvers also. So the computational cost, so Loopy runtime was
Can you go to
8
the previous?
times.
Can you go to the previous slide?
Yes.
I just want success. Okay, this prompt sensitivity. Success highly depends on the wording. So I guess it's not that robust. So if you change small wordings, it may get confused and it may not do as good. Is that what it means?
Yes.
Ah,
So yeah.
yeah. So that's a little bit of a disadvantage. Huh? So your prompt, the way that you word the prompt is quite important. Huh?
Yeah. Yes. Correct.
Mm.
Okay. So future directions. So improve generalization beyond simple programs. So we have only used programs which are less than or equal to 500 lines of code, and we have also restricted the kind of programs that we use. So we could go beyond that. So tighter integration between language models and formal methods, um, better feedback, oracle feedback, and debugging. So so right now, if the program is non-inductive, the oracle just rejects it, as we saw in like in case of Houdini. Am I audible? There's no
Yeah,
electricity.
you're audible.
Okay, yeah. Um, I might be disconnected because there's no electricity right now. Okay. Yeah.
You're, I know that the power went off here as well. I'm in lecture hall 202. Where are you joining from?
From my hostel.
So you're in the hostel, okay. No, but you are audible. But you cannot see anything?
No, I do see. I just wanted to check.
So yeah,
Yeah.
it's all audible and visible on this end as well.
Okay. Yeah. I
Yeah.
think
Okay.
that,
So
okay. Yeah.
okay. Yeah. So we can use symbolic tools other than Fremacy, and then we can also develop tighter feedback loops between verifier and LLM. Yeah, in conclusion, what did we learn? LLMs are surprisingly effective for generating partial formal proofs. Partial formal proofs, as in like we can use Houdini and the repair algorithms to generate like proper proofs. Prompt quality and symbolic filtering are crucial for success. Loopy verified hundreds of real benchmarks, which were competitive with ultimate state of the art tools. And hybrid methods can outperform purely symbolic approaches as well. So, yeah, that's it. Thank you.
Yeah. Any questions? Very good presentation, Gyanashri. Okay.
Thank you
Thank
so
Yeah,
you.
much.
yeah, great presentation.
Yeah.
So I had a one question. So this oracle is supposed to represent some tool like pharmacy, right? Now they have considered the cases when pharmacy succeeds and when pharmacy fails and so on. But what can often happen with these tools is that they can simply time out, right? So they just get stuck. Do they have any discussion about what they're doing in that case?
No, they do not. So the
No, no,
only
no.
limitation of
Go ahead. Then I have, and I see, no, go ahead, Gyanashri. You answer, then I will have my comment.
yeah, so they have not discussed anything about the timer. The only limitation of pharmacy that they have mentioned is that so in dynamic memory allocation they do not support that, and also recursive functions they do not support.
Yeah, and the comment that I had, Diganta, the
Mhm.
pharmacy in the mode that they're using, it's pretty much uh, you can add as much assertions, like, intermediate assertions you want. Okay. It's not like they are
Yeah.
using their abstract interpretation or model checking PMC-like
Right.
thing. What they are doing is, I think they have some kind of a SMT backend to which they ship these formulas. So what I'm saying is, for
Right.
these
So
kinds of things, as long as you put lots of intermediate assertions, enough intermediate assertions, so that there are the block of code between two intermediate assertions is small, the number of statements, then I think it will work okay. I think that's
yeah, so I have two follow-up questions then. I mean, what plugin of pharmacy do they mention that they're using in the paper? Because
that I know.
I
Yeah,
I mean,
you have
Ganesh, you
used
can
it a
answer
few
that.
times. You know better. No, okay. Yeah.
Yeah, so they have said Z3, Alt, Ergo, and CV, C4 as the
No, no. So those
external
are the solver
libraries.
backends, but what pharmacy plugin are they using?
So
Uh,
they have said something called
uh,
we use WP plugin to use Z3.
right, WP, right. So see, this is my personal experience with WP. It does seem to time out sometimes, and what you're saying, sir, is right. I mean, if you add intermediate assertions, then if with enough assertions, WP will go through. But there's are they doing that? Because if I understand
So
correctly, all that they're doing is annotating the program with one invariant. They're not doing anything
so
more in the annotation, right?
so they have said something like the timeout to be set to be 3 seconds.
Right.
Wow.
So, okay. So then it is probably the case that the timeout is being sort of implicitly reported as one of the failure cases of the Oracle. But which failure case is it is then the question, right? I mean, if the timeout happens, then what does it return in terms of IS and INI and so on, right?
So does it output like uh, partial result, or does it not output anything?
Right. I mean, what does it even mean to output a partial result, right?
Yeah, yeah.
I mean, how do you even interpret a partial result? So, yeah, so this is a question that it's not clear to me. And my personal experience with WP is that if you just do this kind of annotation with, so again, this is another question. When they're sending this program to Frama C, they're just simply doing an ACL annotation of the invariant. They're not doing any other intermediate statements kind of annotation that sir was mentioning, right?
Yeah, no, they do not.
Right. So I think in that case, there are situations where for some programs in SVComp with some invariants that I mean manually is readily visible that that invariant should hold. When I tried WP, it seemed to get stuck.
Mm.
Uh,
Mm.
so I had some 10-second timeout, and even if if it doesn't come out in 10 seconds, it was not coming out in anything bigger. To be fair, I
Mm.
was not using AlterGo or CVC. I was using Z3 as a backend, and maybe some of that will matter. And yeah, but anyway, without getting into all of those details, is timeout how they're handling is not very clear. They seem
Yeah,
to be
yeah.
handling it somehow if they're setting a timeout of 3 seconds, but it's not clear what they interpret IS and INI to be and which path they take in the algorithm if a timeout happens. It may not matter, but yeah.
Yeah, another question that I had, Jnanashri, in terms of experiments was how many times did they in and maybe I missed it, but how many times did they need how many of the examples they were able to generate and then solve successfully with the basic prompt? How many of them required the repair loop?
Yeah. So I had slides for that. I'm not sure if you're referring to those, but yeah. So with just the basic prompt, they were able to solve 236 out of 469 safety benchmarks.
Mm, mm, mm.
And I also have with the repair, effective repair, uh, they were able to solve 398 out of 469.
So that's additional 15 benchmarks that they were able to repair out of
Mm.
496. Okay.
Interesting. Okay. I mean, what is your Jnanashri, your thing? I mean, is it? I mean, I have mixed feeling about this. I mean, in terms of is, for all the things that ChatGPT, etc., that you hear about these AI LLM models that they're going to take over the world, but they're not doing that well, isn't it? Huh? That is how I was
I
thinking that
think,
yes, to solve it, okay, they need a lot of help. It seems like for these kinds of applications. Huh? What is your
yeah,
thought?
yeah, because just using Loopy alone, they were slower also, and they were not as effective as compared to other symbolic tools. um, but then like using Loopy, so if it supplemented the other symbolic tool like Ultimate, so they were able to solve more problems, not like
Mm,
like
mm,
comparatively a lot more, but then they were still able to solve more problems
mm,
compared to using just Ultimate alone.
mm,
So yeah, so right now I think they could just be used as a supplement to whatever is
mm.
available.
Yeah,
The
so
rest of it, yeah, go ahead. I mean, yeah, Megan, go ahead.
no, I mean, I was just going to make a comment about this thing. I mean, generally, what seems to happen is with these LLM-based things is that the using an LLM is kind of approaching the problem in a fundamentally different way. Like we're trying to do some pattern matching, and we're doing it at the level of text even, right? So what tends to happen is so for example, if you have things like linear loops and or some very simple control flow structure but with some complicated predicate, right? Something like ultimate will be able to handle it very well because there's a lot of techniques for the loop invariant synthesis for linear loops. If you have like a simple predicates complicated control flow structure or complicated predicate simple structure, ultimate will be able to do it, right? If we have something like a bunch of different for loops which are all very shallow but all of them are happening one after another and so on, but they're doing something very simple, just changing a few bits here and there in some data structure, right? Something like CBMC will be able to probably handle it very well. Just set an unwind tree and unwind assertion. So in all of these cases, these tools work better than LLM because a lot of engineering and a lot of research has gone into making these tools work very well, right? um, for example, if you have a very long piece of code, LLM will simply run out of the context length. Like you can't even send it to the LLM in most cases. And then there's this question of time. Of course, it takes. So this is using ChatGPT and all of these things, which are online API calls. And this is not a software we have access to locally. So the whole API call time gets factored in, and this LLMs being generated on, like the text being generated on the server, the response being generated on the server takes some time. Even if you host it locally, that's a huge amount of hardware and time cost. And then there's actual cost, like in terms of this API are not free typically, and you have to pay a lot to run these experiments. So all of these things is very big downsides. But what is very interesting is some typical programs which have been used as hard cases for all of these other tools, right? Like things like GCD and some long division and things like these, for which things like invariance, the typical algorithms or techniques are not able to synthesize. For these kinds of programs, LLM is able to do very well because GCD is something that it's probably has seen a lot in the training data, right? So I guess the argument for LLM could be that a lot of the code that one would want to verify will be very similar to a lot of the code that is already out there in the internet. And since the LLM is essentially learning how to do some kind of a pattern matching by training it on that online code, it'll simply uh, just work on those kinds of cases where it's similar to something that is already there online, right? Um,
Yeah, but that's what I
but
don't
yeah, I
understand.
mean,
No, but they were able to solve 50%. Of course, they used Houdini uh,
right.
plus this one. And what caught my attention was in the array category, they did better than the symbolic tools.
Yeah, theoretically they will do better, right? Because I mean, again, so
Mm,
if you think about arrays, to come up with the invariant, it's kind of very hard for symbolic tools, right?
logically,
Whereas
because of
whatever array program that they have, that's probably something somebody has written a blog post about or something like that somewhere in the
yeah,
internet,
that
right?
is
I mean,
what.
or
So
something similar.
yeah, so then the true test will
So
be in trying to find the right kind of benchmarks which are not
exactly.
unusual, I mean,
Yeah,
on new
yeah, yeah.
algorithms and those kinds of things.
Yeah. And there is a lot of very interesting research happening in that direction, not for specifically something like program verification, but you know, regarding this question of how good are LLMs at reasoning, both from a theoretical and like an empirical point of view. There's a lot of interesting benchmarks people are developing to kind of test
Yeah, it
whether
seems
LLMs will
like
truly be able to do some novel
yeah,
reasoning.
doing SVCOM benchmarks may not be a good thing. I mean, they have to find different.
It's not a great idea at all. Yeah, I mean, It's the thing is, it's hard because even on open source benchmarks or things like that, right? I mean, they're all available on the internet. Even if you use some kind of a proprietary benchmark that is not available on the internet or some synthetic thing that you've made on your own, typically they will follow some kind of a pattern that is already out there, right? Or it'll just feel very contrived. So
Yeah, but
yeah, I
anyway,
mean, it's
yeah. Anyway, I want to give this opportunity for others to ask. This is a general topic of LLM, how good it is and so on. So this would be a nice time for you to give your free floating thoughts. It doesn't have to be about any technical thing. What do you think about this line of work? If guys are still hanging around, what do you think of using LLM as a black box to assist in doing these verifications? On you have had some insight into how difficult it is to come up with loop invariants and so on. So what are your thoughts? Anybody want to add anything? Let your thought flow.
or is it too late in the day for?
Could be, but there is another one. At least you have Shah Shashank is going. He has he only can go at 5:30 because I think maybe too many comments after the last review and therefore
Right. Makes sense. Yeah.
Whatever. No comments. But I hope some of you will show up for Sai Shashank to just give him some moral support. That's it, 5:30.
So one more thing I wanted to ask, a favor I wanted to ask you guys. I mean, so I've been trying to get in touch with Kathakali and see if she is available right now. I don't know if this is too much to ask, or if she's busy with something, then it's fine. But if any of you know that it's okay to call, or has some kind of number that if anyone, if you can get in touch with her and sort of see if it's possible, then it will be good, because I think
Do you have her number, Jnanashri?
Yes, I do.
so even I have a number, but I don't know if I should call directly, right? So yeah, I mean, that's what I
I
basically
think if
wanted.
Jnanashri calls, it's okay.
Perhaps, I mean, that is up to Ganeshri and Kathakali, so I don't know.
Of course.
Yeah, I can call her.
Yeah. Sure. Thanks.
Yeah, so if there are no questions, then we will reassemble again at 5:30.
Yeah, perhaps we can use this meeting itself, sir,
Yeah,
for meeting with
that's what
Kathakali.
I'm thinking. Yes, that's why I say other
Correct.
people can drop off and while we discuss with Kathakali. Yeah. Then hopefully you'll come back at 5:30 to support Sai Shashank. I mean, what he's doing is also quite interesting. So on backdoor attacks.
Yeah.
There's a good set of slides. I went through that. So be there.
Can I stop sharing?
Yeah, please. Sure. What are your opinions, Ganeshri, on this LLM based thing?
What is your thought? Yeah.
So LLM based thing, as in my opinion on
On
being
whether
used in program.
LLMs will take over, or LLMs are a scam, or
So why did you? I mean, Jnanashri, I mean, you chose this thing. Are you done? Have you had some encounters with LLM for other things, and that's why you wanted to do this, or just out of curiosity?
So it's basically out of curiosity. So I didn't know much about LLM. So through this paper, I wanted to learn a bit.
I think you should try that. I mean, now that I've been wanting to, but I've never been somehow, frankly, I never used any of these. Okay. I've not even
Mhm.
typed. I think that maybe I did once, but I was trying to uh, throw abusive words at them. That's what it
Yeah.
is. And it was quite polite when it came back. But as I do
Yeah.
more abusive words, it was getting more abusive. Okay. Uh, uh, but
So
I've never.
I have a very funny anecdote about this kind of a thing. I think this was the Google Gemini some version early last year. Uh, they came up with a fairly interesting model, but somebody posted and said that so this person who was interacting with the LLM was under 15 years of age, right? And the LLM knows this because Google will take that data and simply pass it to the LLM. And this person now asked for some C++ code for some project that he was doing. So the LLM said that, look, C++ code is unsafe, and I cannot show unsafe things to a minor, and refused to help. So
See, so it meant, yeah, it used unsafe in a very sensitive way.
yeah, yeah.
I, oh, okay. But see, Chat GPT, I don't know. I mean, no one can sue Chat GPT. It was probably thinking in legal ways or.
Yeah, I think that is indeed. I mean, I think OpenAI and Google, Meta, all of these spend significant resources to kind
Oh,
of do,
to be
yeah,
sensitive
to make
to
sure
these
that,
things,
yeah,
sexism and
correct,
those
correct,
kinds
yeah,
of things, huh?
yeah, yeah. I mean, there
Maybe that's why it
was a
was.
very, very funny thing again out of Google where that somebody, yeah.
So I
So this
guess,
is a very similar kind of, yeah.
yeah, so
Sorry, go
the
on.
LLM model developers would be held responsible nowadays, I think. I mean, because these things have become such ubiquitous things. If it does certain things and then that can be construed as having psychological effect on kids, then they'll be held responsible in some ways. No? So they'll have to put certain guardrails.
Yeah, I mean, it's definitely possible, and I mean, see, I don't know if what the legality is, but given that these are big companies, there's a PR damage aspect that, and people will definitely try to sue, even if whether or not the case holds or not, right? And once they sue and make a huge media deal out of it, then Google and Facebook and all of these people will probably find it better to settle, and then there will be opportunistic people who will want to sue just for, you know, suing sake. And of course, there's an actual damage that you can do by, like, if the LLM, for example, is very readily giving recipes to make dangerous chemicals to miners, right? I mean, of course, this is not something that is too difficult to obtain from a simple Google search, and so far nobody has held Google responsible for the search results they provide. But there, it's a bit more clear. With the LLM, it's not very clear, like, whose responsibility it will be, and since there's only one party involved, it'll be Google who will be on the hook for it, right? Or whoever, I mean, serving up the LLM. But yeah, I mean, I think we asked Ganesh and then we didn't let her sort of. So, what is your opinion on after reading this paper and so on, like on the capabilities of LLM for things like programming and stuff?
Um, I think uh, for more like, I think right now the data sets they have been like really tailored for the LLM. So
Hmm.
in those tailored data sets it performs well. But
Right.
yeah, even if like we say that LLM is a like general purpose guesser, even then like I think for it to become really general purpose, it needs more work.
Yeah. Yeah, that is pretty much what I feel as well. There's this interesting benchmark called the ARC AGI Challenge by Francois Cholet. It's very interesting. It's a set of these reasoning tasks which seems that it's extremely easy for humans to perform, but LLMs cannot do anything there. On the other hand, apparently there are things like very difficult code challenges and Olympiad problems that humans find difficult, but an LLM-based reasoning system is able to solve. So it is, I think, the case that the data set is somehow helping the LLM, but it's not very clear what kind of, I mean, how to sort of separate it out and show that, right? Because if it is the case that you could train an LLM on a bunch of Olympiad problems and it's now able to solve an Olympiad problem which was not seen before, that is a bit surprising. Uh, whether that means that the LLM is somehow has some magical reasoning capability, or that whoever is coming up with Olympiad problem is a limited an unexpectedly limited imagination, then therefore it is the problems are sort of similar in unexpected ways. Who knows? Both of those two cases are, I think, very interesting if one understands exactly what's going on.
This ARC challenge is also probably being hosted on Kaggle, right? Like,
yeah, ARC is on Kaggle. So I think version 1 definitely is. There's now a version 2 out. Version 1 has been solved by some modern LLM based techniques, but I think version 2 is LLMs are not able to solve.
I think it's like
I
8
don't know
months.
if the version 2 is.
Yeah, I think that.
That's also on Kaggle, right?
Yeah.
Yeah. Okay, so I mean, I don't know how we'll get in touch with Kathakali. I don't.
I tried calling her. She did not receive my call. Sent her a message which has not been delivered.
Right. Yeah, sure. So I think we'll just figure out some other time and place to meet. Yeah, we can have a more open-ended discussion now if people are interested, because anyway, or we can just meet at 5:30, whichever.
Yeah, there are a bunch of people still there, so they're not speaking.
Yeah, I mean, and of course, I mean, if people want to leave, you can leave this. I don't know if it's anybody is forcing.
And I tried to get Shai Shashank to start immediately, but he said no.
No, I saw that. Yeah, I saw that he's not available. Yeah, that makes sense.
Would anyone be speaking now? Like till 5:30?
No. Oh, I thought
5:30 blank spot.
5:30. We tried to get Maya was a scheduled speaker. She is not well, and therefore we decided to move Shai Shashank earlier, but he preferred he was not available until 5:30. So if nobody, I mean, then we'll. I'm keeping the meeting on. I'm going to go get probably some coffee and then come back. But people are free to chat. Diganta, I don't know what you want to do.
Yeah, I mean, if anybody is willing, wishes to chat, I'm here. Otherwise, I'll. If everybody leaves,
but since Deepro and Aritra are here, are you guys here?
Or are you guys AFK?
Yes, sir. Actually, I was planning to get some coffee as well and join by 5:30. So,
sure.
Am I needed here for something?
No. I thought since we brought up that the point that Aritra was saying, okay, and I think maybe I mixed it up and got you guys confused, okay. We could discuss and then get clarity on what he was trying to say. I thought first, so if you're willing to let me go willing to come back, we can discuss that, I thought.
Sure. I can do it. Is Aritra there?
He's there on the
he might be AFK.
No, he's logged in. Whether he is stepped out or not.
Yeah, I think he might have stepped out while letting the meeting be running it.
No, but
nonetheless, maybe.
No, Deepro, if you want to go get some coffee,
yeah, I was planning.
Yeah, okay, I'll also go get some coffee. If we are back and before 5:30, and then I'll, we can just chat. Yeah.
Sure,
Yeah.
sure, sure.
Hello. Um, Ikanta, are you there?
Yeah,
I wanted
yeah,
to
yeah.
ask.
Hi, I'm there.
Yeah. So, are there any like works that have been done using like LLM in program verification, like something that I could read up on?
Yeah, so there's Loopy, and I think basically Loopy is one of the better ones out there. Then there is so look at leveraging. This paper called leveraging. I think it's something like leveraging LLMs for program invariance or something like that. Uh, right. So I'll send you some links, but basically Loopy is a good point to start. And if you look at references of Loopy and papers referencing Loopy, you'll get a good sort of point to do a DFS from.
And
Yeah,
so for this paper, mostly I've considered LLM as a black box in some sense.
that's what most papers do. That's what most papers do. See, that's the thing. I mean, the even people who are researching on LLMs, they kind of look at it as a black box, right? I mean, so of course they understand what the architecture is. So if you want to understand the architecture and all of that, a good point to read would be the original Google paper called "Attention is All You Need" and such. But then, see, even if you understand the architecture and then you train it and you see that it's giving you good performance, you don't necessarily know what's going on inside the model at a level where you are able to interpret it or explain it in any way, right? So it is by the design of things kind of a black box situation. Even people who are working with LLM, developing or training these LLMs don't really know necessarily what's going on here. They have some heuristic ideas like if it's not converging, let's tweak this parameter here, let's change the temperature there, and so on. But at a very granular level, it's not very clear. And I mean, there are works that are trying to get some idea. There is this person called Neil Nanda who's doing some interesting work. He's at Anthropic. They have some interesting work from mechanistic interpretability and things like that. But yeah, I mean, mostly it's a black box. Almost everybody is treating it as a black box, and this is not really much else you can do. I mean, it's a kind of black box by design. There is a flavor to it, though. I mean, in the sense that, so for example, Google typically they train their thing to be very very safe in the sense of the uh, calling unsafe C++ to unsafe for minors kind of a way, right? Um, and so it's almost like there's a certain amount of like flavor or personality that each one of them has. Mostly Meta and OpenAI's models are fairly like balanced and so on. Yeah.
So have like so for like programs where for safety critical programs,
Hmm.
so have like LLMs been integrated into program verification?
No, 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 no. Not yet, not yet. It's there, it's still in research stage. I don't, yeah, it's not been. And then the real issue, see, at an industry point of view, the real issue is more logistical in the sense that with LLMs, these are all typically online APIs, right? So there's a privacy issue. Like you don't want to send the code to the online APIs, right?
Oh, right. Right.
Yeah. And then there is a cost issue. So all of these issues are also there, right?
Yeah.
But at the same time, yeah, people are interested in LLMs, but they don't want the privacy aspect of it. They don't want to pay as much as they're being asked to pay for it. And yeah, so the logistics, the cost, the privacy issues, these become kind of important there as well. Because typically these safety critical codes are also like very proprietary things, like actual industrial safety critical codes.
Can I leave the meeting?
Yeah, sure.
Thank you. Thank you so much.
Yeah. See you later.
Yeah, thank you.
Thanks. Bye.
Hello?
Hello, sir. Hello, everyone.
Hello. I don't know
Yeah.
if. Yeah. Okay. Yeah. So I think people is there. Yeah. Yeah.
People are coming in. What I've done is I've disconnected everything. So how are you going to disconnect? I've disconnected everything.
Oh, you have to yeah.
What have you disconnected?
Okay, it's fine, it's fine. Actually, in my room, like, you got very bad kind of it automatically turns on mic when I regional kind of thing.
What you can do is you can just sit around here. Oh, sit here. You can also talk and so on. Yeah,
Yeah,
just
like
pull a
I-
chair and sit here.
Okay.
Or you can sit there.
Yeah.
But whenever you want to say something, I'll mute and you say. Yeah. Like sit close. Sit close by right here. Yeah, we'll give a few more minutes to see if anybody else is joining. Otherwise, give me 5 minutes. Yeah, we'll start in 5 minutes.
Sure, sir.
Yeah. Yeah, I mean, I disconnected all the audio and everything. Okay. So if you want, you can pull up a chair and then just sit here. That's why I said pull up a chair and sit here. Okay. Because you don't have a laptop either, no? You didn't understand what I said. I'm not projecting anything. Yeah, so if you want to see the slides, you have to pull up the chair here and then sit. What do you want to do? You want to just sit and listen to the audio?
No,
But I'm
saying that you can sit.
But you don't want to sit next to here?
So that you can sit.
You do what you want. Yeah. Yeah, but what else can you do? I mean, either you should have brought your laptop. I know that didn't do because I didn't know you were going to show up here or a thing and so on. So tomorrow it'll all be online. This is it's not worth the effort. So tomorrow everything will be online.
Pretty unstable, so you get disconnected from the gate and.
Yeah. Okay. I'll make you. You can see, no? Yeah, Shashank, you can share the slides.
Okay, sir. Thank you. Please let me know if you can see.
Yeah, can you see?
Yes. I can see.
Okay, thank you. Yeah, and so I'm Sai Shashank, and I'll be presenting the paper Verifying Neural Networks Against Backdoor Attacks. So general overview of the contents I plan to cover. So I'll just informally introduce the problem and then briefly talk about the motivation behind solving this problem. And then more formally, I will define things we care about and define the problem itself formally. And we'll see what the technical challenges are. And we'll walk through for a single example what verifying backdoor absence looks like. And then I will look at the technical approach, that is the solution, the method that's proposed by the paper, then look at the correctness and soundness proofs, and finally look at the experiments they have done and the results they got. And I'll just summarize and look at the future work informed by the limitations of this method. Okay, so the problem is about backdoor attacks. So a backdoor attack involves embedding a trigger inside an input to a neural network. The idea is that we want to produce a specific target output that we as an attacker choose, regardless of what's actually in the input. For example, if you see on the right, so here we are feeding an image of MNIST digit 7. And as expected, it outputs 7 for this image. But the attacker can put a specific trigger that he knows, and he places it in a particular position with a particular pattern in the input image. And as you can see, there is a distinct pattern in the bottom right. But the input image is still overall 7. So if you don't know anything about the backdoor attack, you would expect the network to still predict 7. But with such a trigger embedded in the input, the network consistently predicts output 8, let's say, that is chosen by the attacker. Yeah, so one way to do this, one way to get these backdoored neural networks is through training data poisoning, where on the left, you can see we have the MNIST dataset, where you choose a certain fraction of the training data. And what you do is you modify the input image to have a specific trigger. In this case, it's a small patch on the bottom right of the image. And you change the label for that sample to a specific target label that you as an attacker choose. In this case, that's 8. So once you have a backdoor network, the problem is to verify, given a neural network, if it's free of backdoors. And we look at backdoors with a certain level of success rate, because in practice, these backdoor attacks are not 100% successful. So the motivation behind looking at this problem is that we see that the neural networks are becoming more and more capable, and are therefore being used in a wide variety of applications, which include safety and safety critical systems, like face recognition and medical diagnosis and so on. And the existing approaches to detect and mitigate backdoor attacks are limited. And most of them seem to focus on empirically checking if backdoors exist for a given neural network. And they're not concerned about providing a formal guarantee. So the paper claims that the only known approach that is relevant to certifying absence of backdoors is based on randomized smoothing, but it seems to have a limitation that it degrades the neural network's accuracy. So it provides certain robustness guarantee, but it degrades the accuracy of the neural network. So the main contributions of this paper is that they propose an approach to verify.
One question, Sasank. Go
Yes,
to the
sir.
previous slide. So I know this is not the main topic of the paper. You say that it degrades the randomized smoothing, degrades the performance. So that technique, it actually modifies the original net. Is it? Yeah.
Yes, sir.
Okay.
They call it a smoothed classifier. And although it's more robust, but it seems to perform worse. Yeah.
I see. Okay. Yeah. Okay.
Yeah. So like I was saying, this paper proposes a novel approach to formally verify absence of backdoor attacks with a specific success rate. And it assumes certain constraints like the trigger is of so size. Yeah. So the proposed method is composed of two main ideas. One is statistical sampling or hypothesis testing. And the other one is the formal verification method of abstract interpretation. It also includes a gradient descent-based optimization. In the case that the method decides that there is no backdoor, decides that there might be a backdoor, it tries to generate a concrete backdoor trigger using a gradient descent-based approach. So a few notations.
Any questions from the audience about this motivation and informal introduction? Okay. If there is no question, please go ahead. Yeah.
Yeah. Thank you. So briefly, we'll review some notation. So we'll use n to determine to refer to a neural network. It's a pre-trained neural network classifier that's given to us. We have m-dimensional input and we have n-dimensional outputs. In the case of MNIST, M would be 784 because we have a 28 by 28 image, and N would be 10 because we have 10 classes. And we have the labeling function. It takes the logits that are output by the neural network. In this case, in MNIST case, it's a vector of 10 elements, and it outputs a label corresponding to the prediction by simply taking the maximum argmax over the vector. And we'll use I to refer to an input image for the neural network. And we call S a potential backdoor trigger. This is typically unknown to us unless we're doing certain experiments where we are planting the backdoor. The method itself does not know what S is. So it's an image patch in the case of MNIST, let's say MNIST classifier. And we also assume a certain shape associated with the image patch. And we also denote a top left position for the trigger to determine where exactly in the input image is the trigger stamped on. So given the image I and given the backdoor trigger S, we can define IS as the resulting stamped image, where we replace the pixels of the original image with the pixels from the backdoor trigger at the specific position HP, WP. As an attacker, we also target a particular label that we want the backdoor trigger to generate. Let's call that TS. And let's call theta the minimum desired success rate of the backdoor attack. If I say theta is 0.8, what I mean is you can expect an average sample from the distribution has an 80% chance of generating the backdoor target label.
So what is CS?
There's a question. I mean, there's a question.
In the shape, right?
Yeah, like CS from ICS. What is CS?
So if you consider images, you also have channels
Okay.
for the image. I'm sorry, I glossed over this because MNIST is grayscale, so we only have one channel. But yeah, typically if it's a RGB image, we have 3 channels. Okay.
Yeah, can proceed.
So,
Yeah.
so now we can define the notion of a backdoor attack being successful at a certain rate. So a backdoor trigger S is considered to have a success rate of theta if there is some position HPWP such that if you pass the stamped image into the neural network, the probability of assigning the target label to that input is at least theta. Okay, so now with this definition, the problem that we want to solve is given a neural network and the shape of the trigger and a target label that we are looking backdoor attacks for and a success rate theta, we want to verify that there is no trigger S of the given shape and at any position in the input such that the backdoor attack achieves a success rate of at least theta.
So I have a question here.
Yeah.
So when you say that the success probability needs to be at least theta, so what is the distribution you're defining this probability against? Like as in, how do we calculate or how do we model this probability of L of this whole expression being TS being theta or not? Is it based on the output logic in softmax or something?
Yeah, it's based on that. For example, in the experiments, they take 10,000 samples of MNIST test set. And if theta is 80.8, then we look if at least 80% of the 10,000 are generating the target label, given that they are backed out.
Oh, okay. So they estimate the probability by doing some statistical sampling.
When doing the experiments, yes.
Okay, sure, sir. And maybe I'll let you continue and I'll come back to this.
Yeah. I think there's a little bit more detail, correct, Shashank? I mean, the probability is calculated not as simply as this with theta. I mean, there is some hypothesis. They use this SPRT algorithm. I think let's wait until he. I'm sure Shashank you will show a little bit more detail as to how exactly the probability is computed and what the distribution over which it is done, etc. Yeah.
Yeah, we can definitely revisit that. Yeah. So before we address the solution, let's look at the challenges. So the trigger search space is very large because S could be any pattern. That is, the contents of S could be anything, and it could be at any position in the input image. And like we have seen throughout the course, exact verification techniques are hard. They don't scale well. And if you're going with over approximation methods, if you're not careful, it can lead to a lot of false alarms and inconclusive results. And there's also certain statistical nature to this problem. Like, I guess it's a bit ahead of the content. So basically, when you have certain hyperparameters, it's not very clear how you want to, how it affects the solvability of the problem. Like, what theta value should you choose, or if you're using a statistical method, what sample size should you be considering? So we'll try to walk through the solution now, actually, but we'll just look for a very single toy example and see how we can verify that whether it has no factor. So consider a tiny network with just 2 input features, like let's say 2 pixels, and a few hidden layers with relu activations, and just 2 output classes labeled 0 and 1. And yeah, so the input image would be a 2-pixel input. Let's call it 0, x1. And let's say the trigger is just 1 pixel trigger. That's affecting the first pixel, let's say x0. And its value can range from, let's say, 0 to 1. Because, yeah, this is reasonable because a normalized image would have a value in between 0 and 1. The second pixel is fixed because we are given the input image. So we just take x1, and let's say x1 is 0.5. So the constraint that you can start off with is pre-I, which is x00 lies between 1 and 0, because this comes from the trigger and we don't know what it is. And x01 is exactly 0.5 because this is from the input image. And let's say the target label is 0. So now the goal is, is there some trigger value for x00 in this interval that makes the network output the target label 0? So, so what the paper uses is a deep Pauli abstract interpretation. So we start with this pre-I constraint, and we propagate these through each layer. And if you recall deep Pauli, we calculate an over approximation, and we keep track of the concrete and linear bounds at each layer. And this will give you the behavior, the constraint for the network behavior. Let's call it AI. And we can now define a success condition for the backdoor attack. So the attack is successful if the output neuron for the target label is greater than the output neuron for the other label. In other words, the logit that you predict for the target label should be greater than the logit for the other label. If you have multiple classes, then we should have the logit for the target label to be greater than all other logits. And this will give us the post condition, post I, x out 0 greater than x out 1. So now we combine the constraints that we got so far, the input constraints, the network behavior constraint, and the constraint on the attack success. So yeah, so you notice that the trigger variable is the thing that we don't know. And what we do is we use a SAT solver to check if this constraint is satisfied. If it returns unsat, since it's an over approximation that we get, that is phi is an over approximation, we know that no trigger value can make the network output the target label 0 for the given input I. So we can say that the network is safe for the specific input. Yeah, if SAT, the solver will return a model, a specific trigger value for x00. But since it's an over approximation that we used, so we need to check if this is an actual trigger against the real network. And we can do this in a single forward pass. Yeah, if that confirms that the trigger succeeded, then we found an actual backdoor trigger for this input. So this is for one single example, one single input image to verify absence across a set, let's say X, consisting of K input images. So what we do is we get a constraint phi, that is a conjunction of all the constraints phi I for each image I. Yeah, so this kind of hints at what the overall solution is going to look like. So the high-level idea is to apply hypothesis testing using the sequential probability ratio test algorithm. So yeah, so we get the inputs. If you recall, we get the network that we want to verify the absence of backdoors for. We get the required success rate theta for the backdoors. We need to decide on some sample size k that this algorithm need to use. And we also, like I said, we assume the shape of the trigger. So we need to provide that to the method. And we also tell the target label that we are looking the backdoor attacks. There are certain parameters that are required for this hypothesis testing algorithm, like how much of type 1 error and type 2 error are you tolerant for? And we indicate them using alpha and beta. And there's also this notion of indifference region delta. Yeah, I don't want to go into detail, but it's about specifying some buffer zone around the boundary of the two hypotheses. So the two hypotheses are the null and alternative hypothesis, and these are mutually exclusive. And the null hypothesis H0 says that the probability of not having an attack on a set of k sampled images is more than 1 minus theta to the power k. Okay, so theta is a success rate. So theta gives you the probability of a successful attack on one backdoored image. So the probability of having an attack on k images would be theta to the power k. And the probability of not having an attack on a set of k randomly sampled images would be the complement of that, so 1 minus theta to the power k. And in other words, if null hypothesis is true, it means that the network is safe.
With the network is safe with probability less than or equal to 1 minus theta k, correct? No, greater than, I'm sorry. Yeah, the probability of the absence of not having an attack. Huh?
Yeah, it's in other words, it's likely that there is no backdoor attack on the network with success rate at least theta. With respect to these error thresholds. And we also have, the mutually exclusive alternative hypothesis, H1, that says exactly the opposite thing. The probability of not having an attack on k randomly selected images is no more than 1 minus theta to the power k. So we can see how this probability is the one separating H0 and H1. So if you think of it as a boundary, it's an exact boundary, but with the indifference region, we take plus delta and minus delta to create a buffer zone. So if you are in that zone, where we don't stop sampling and testing again, we continue to sample for evidence, either to conclude H0 is true or to conclude H1 is true.
Yeah, Diganta,
So-
I mean, I think the algorithm has some more detail. But Diganta, I mean, you want to ask any question here? So this
No, I think I'll
I'll
wait until some more details are presented.
Yeah, I think so. I think there will be questions. I also have questions. And when he gives more detail as to what exactly, at a high level, kind of people understand this now. Theta is, so the success rate being small means this assurance will be high, correct?
So if
Theta,
theta is low,
yeah.
then it just means we're looking for weak attacks also. We want guarantees against weak attacks as well. Theta is low. Theta to the power k is
Very small.
also low. And
And
1
so
minus that will be very close to 1.
it'll go to
And
1.
H0 and H1, the probabilities will be very high and they'll
So
be
you
very
have
close.
high confidence that there's no probability of attack when theta is small, correct? Yeah.
Yeah, it'll need like a lot of trials to conclude.
Yeah.
Yeah, to
So
conclude.
that will be a
acceleration.
harder problem. So basically, we're trying to show that even a weak attack with low success rate is going to not be able to. Yeah.
Because I guess if you take small enough data, you could just find adversarial examples, I guess. And that would technically count as a backdoor attack.
Right.
Because theta is so small.
Sorry, so if theta is very small, why would adversarial examples count as a backdoor attack? Because it has to be uniform adversarial example across all images, right? Or
yeah, but the theta
oh
is so
no, so
small.
if theta is small, yeah, so basically, even if it's across just one image, then it still sort of aligns with okay, I see. Yeah. So if I have basically if I have 1,000 images and I have just an adversarial attack on one of those images, that then I can interpret that
0.001.
situation as being basically something like a backdoor attack with this much. Yeah, sure, makes sense.
Okay. Yeah, so there are 3 components to this to the solution. So the first algorithm, the overall algorithm, it repeatedly samples k random images from the data set that you have and calls verify X. That is the algorithm 2 on them. And this algorithm 2 returns either that the network is safe on this set X or unsafe, or it's unknown. And based on what verify X returns, we use the SPRT algorithm where we keep track of how many times verify X has written safe, how many times we have called verify X. And we use that information to statistically accept either H0 or H1.
Yeah. At this point, I know that you will define verify. Okay, that's right. The verify X is actually defined here in your second bullet. Okay.
Yes, sir. Yeah.
So what exactly verified means when it returns safe, unsafe, etc., is described in the second bullet. Okay, go ahead, please. Yeah.
So algorithm 2 is verify X. We are somewhat familiar with this because we walked through an example where X has just one image. So for a given set of K images in the set X, we need to check every possible trigger position because we don't know where the trigger might have been placed. We just assume we know the size. So what we do is
possible trigger position for every possible images you have to check. Yeah.
So what we do is for each position in the input image, we use abstract interpretation like we did in the example to create constraints representing what a successful trigger attack looks like for each image in X. And if that is unsat, that is, if no such trigger can exist at any position, verify X returns safe. There are other cases. I'll go through them exhaustively when I go through the exact algorithm. But we can see how.
Yeah. Okay. So I just a small doubt. so when you say repeatedly sample k random images, I mean, are you so do you have a while loop that samples k where calls verify x and then samples k again and calls verify x and so on, or are you just sampling k things and then calling verify x on that whole set, and then based on that just estimating your probability with respect to SPRT?
It's the former. We sample a
Right.
newly every iteration, every try.
Okay. Yeah. Okay, yeah, that makes sense. Yeah.
Thank you. Yeah, and then in the case that algorithm 2 finds that a trigger might exist, that is a verifies determines it's unsafe, we try to use a gradient descent based approach to generate a trigger that works on the images in the input set X. And if that trigger works, then we return the trigger. Otherwise, we return null from this OP trigger method. Now, I will go into the details of each of these algorithms. So first we have algorithm 1, the overall algorithm, verify PR. So the inputs, if you recall, we have the neural network N. We have the attack success rate for the trigger theta. We have a sample size K. Sorry, yeah, we also are given the shape of the trigger. We are given the target label that we want to check attacks for, and we are given certain error thresholds and indifference region widths that's required for the SPRT algorithm. So we keep track of the number of times we call verify X using this N variable, and we keep track of the number of times it returned safe using Z. You can think of them as, from a statistical testing point of view, you can think of them as number of trials and number of times we got evidence for the null hypothesis. So we defined the probability boundaries. We saw how 1 minus theta to the power k was the probability separating H0 and H1. And we add plus delta and minus delta to create the buffer zone. The idea is, if we are in between these two, we do not want to accept, because we're not certain enough. So we create that buffer zone and we only conclude that is accept H0 or H1 only when we are in either side of this buffer zone. So yeah, this is the repeatedly sampling part. So while true, we increment n. We're going to sample now set of images X of size K. And we call verify X. We pass the network, we pass the input set, we pass the shape and the target label. This is an abstraction now. We have not seen the full details of this algorithm, but we have said that it returns either safe, unsafe, or unknown. So let's say it returns safe. Then this trial resulted in as evidence towards the network being safe. So we increment Z. And in other case, if verify X returns unsafe, then it's possible that the algorithm generated a trigger using OP trigger. So we take the trigger and we run it on the full data set that you have at hand. It might be a set of 10,000 images. And if running so actually gets you the required success rate or higher, that is theta, then we can return unsafe from here and we can just terminate. Otherwise, we fall through, and this 4 lines correspond to basically checking likelihood ratios of the data we have seen so far. So
I want to point out here, I mean, in terms of asking a question. So firstly, it is, verify X returns unsafe, which means that it returns a model, but you're doing something to make sure that that generated trigger is something more comprehensive, right now? That it
Yeah.
works for all X's or something like that, for every
Yeah.
yeah. But the case where it falls through is when it is verifies detected, it is unsafe, but you cannot even get the trigger. That is the unknown case. That is the unknown case, I presume.
Yeah.
Right?
Yeah.
Okay. Yeah, well, of course you can get an unknown case out of verify also, isn't it? Yeah, if it's since it's an over
Yeah.
approx
Yeah, if
unknown.
it's unknown, we don't do any of this.
Yeah. Okay. Yes.
So just to understand this likelihood ratios a bit, so H1 is the hypothesis that says that there is it is not the case that there are no backdoor attacks, right? So there may be
Yeah.
some backdoor attack with
There
less
might
than
be
such and
backdoor
such amount of.
attacks. Yeah.
There
Yeah.
might be some backdoor attacks with such and such probabilities.
Yeah.
Okay. And so then every time we sort of so every time n increases but z does not increase, every time we get something in the like every time n minus z increases, that basically is one point that is evidence for H1, right?
Yeah. Yeah.
Okay. Okay. Yeah. Okay. And so then the lower one is saying that, okay, suppose let's assume that H naught is true, then what is the likelihood, the lower term in this ratio in line 12? The denominator term is basically what is the likelihood of H naught, right?
Yeah.
And the numerator term is saying, what is the numerator term saying exactly?
It would be for H1, right? P1
Right.
corresponds to
So
the
but why is P1 corresponding to, so I mean H1 is okay. Okay, so what are we saying in H1? You're saying that there's no there's no it is
there might
like
be
there is no
backdoor
back.
attacks.
There
H1
might,
saying
it's
there
not the
might
case
be.
that there is no, right.
Yeah.
There might be backdoor attacks.
We can be
with,
sure.
Yeah.
I think the
With
H. Yeah, go ahead. You finish. Okay. 12 and.
No. I'm just thinking out loud. Sorry. Yeah, go ahead.
I have a few appendix slides on this detailing how we
But
get
at
this.
the-
Okay, sure. So maybe we can then discuss that
But
at
at
the
the
end.
high level, it is useful to understand. So when can be, so
Right.
if 12 and 13 passes, so this is the case when you earlier said that you can be sure that it is safe, that there is absence of backdoor attack with high probability threshold that you had, correct?
Yeah,
Isn't
with
it?
respect to this type 1 and type 2 errors.
Huh?
Yeah.
So with
Yeah.
respect to this alpha and beta.
Yeah.
With respect to the alpha beta. And the else if case is when you don't know. I mean, you're not sure what the that it you know that it they could be, or you don't know, right?
Yeah.
So that is that's what going on at the high level. Yeah.
At the high level, but I have lots of questions here. Why exactly that should be is what is not clear to me yet, and that is kind of the
Yeah.
I don't know. I mean, maybe Shashank later on, if you could shed some light as to
Yeah.
So I think
I dug into why like these bounds should be as they are, and I can talk about that either now or later. I have a few slides on them.
Yeah, sure.
Yeah, maybe later is a good. I think that's details of the SPRT algorithm itself, which is I mean something that I don't recall very well at this moment, at least. So maybe we can have the discussion sometime later on. Yeah.
That's sometime later, and then if you have the time in the appendix, but I don't know if I think certainly as a follow up, I would love okay, Shashank, since you're there, to see what exactly is happening there with the SPRT algorithm, if indeed as you can help us
I
understand.
would also, that would be nice.
Yeah, definitely.
So any
Okay.
questions here by
Yeah.
people in the audience? Huh? Yeah, okay, good. So there is one part here which is pure FV kind of a part using the verify X.
Yes.
But the result of verify X over several iterations is the success or the lack of success is used to compute some probability of overall safety. And correct? That's the overall
Yes,
thing.
sir. Yeah.
Yeah.
That's the idea. Yeah. Okay. So, yeah.
The algorithm, like how long does the algorithm run? Like it's
Who's
just
this?
while
Identify your name.
Bijay Andrak.
MGN. Okay. Yeah.
Yeah. So this is a while true block. So here, how long does this run? Like, is there?
Yeah, it can time out if you're not careful. I mean, it can run forever if you're not careful with your hyperparameters. Yeah, the authors use a timeout to stop it if the network is too complex or if the
I see.
hyperparameters are not
Okay.
good. Yeah.
So like there's no proof it will stop or something.
No, it need not stop.
Okay.
So
Okay.
are there statistical guarantees for termination? I mean, do we know that, okay, with some certain amount of probability, it will stop after this many number of things or something like that?
Actually, I'm not aware of such
Sure.
result.
Yeah. Okay.
Yeah.
Yeah, but there is one observation that I think the paper makes. Correct me if I'm wrong, if I'm Mr. See, okay, that's a good question. Yes, it can converge into one of these two things. That's one way of terminating, or it never converges into either of them. You've run very long, and that can happen. Okay. Now there are two extremes. You can have k is equal to 1. Your sample size could be 1, or you can have very large k. Okay. I think they make an observation that neither of them is a good thing, okay? Because, I mean, yeah, because if k is equal to 1, almost every time it's likely that there'll be a backdoor attack, okay?
Yeah. Verifax can return unsafe by just finding an adversarial example.
Yeah, at the thing, and then you never have safe kind of a thing, okay? This will not. The first hypothesis will not happen. If you have very big K, then verify is too expensive. It can just not return anything. Like authentication and all these formal methods, they can never return a result. Then there is too many unknowns, okay?
Yeah.
Or something like that. In either case, it may not. Okay, now how whether those are the cases where it may not terminate, correct? Because you never converge.
Yeah.
So if k is 1, then really where it shows up in the algorithm, the low k case where it shows up is the P0 and P1 will have values that are unfavorable for termination for SPRT, right? Or something.
Yeah, it'll be hard
P0
to
and P1 will be
distinguish. Yeah.
P0 and P1 will be hard to distinguish. Okay. So basically, if k is 1, then I see. Okay. So by the way, there's a capital K and a small k. I'm assuming those are the same things in P0 and P1.
Yeah.
Or
I'm sorry. Yeah. It's the same thing. Yeah. Sorry.
Correct. Yeah. Okay.
Yeah,
I
this
see.
is
So let's
certainly
say that it is
that they make in the paper. I'm not confident as to why exactly that should happen. For that, you need to get into the details of n minus z, 1 minus theta k. It also depends what the value of theta is, okay? And then k and so on. So I don't know. It's let's yeah. Okay.
Yeah.
Okay. Yeah, thanks. So this is the next part of the next level of detail.
Yeah, any other questions on algorithm 1, the high level one? Okay, by others? Okay, go ahead. Yep.
Sure. Yeah. So like I said, the next level of detail is the verifax algorithm. It receives the network along with the subset we want to verify for. And in this case, we're not concerned with theta because we want to see if it's safe or unsafe for all the images in the input set X. Like I said, it returns either safe or unsafe or unknown. Yeah, so we have a Boolean flag that keeps track of whether we are we're not able to verify it was safe or unsafe for any particular trigger position. So we initialize it to false, and we look through all trigger positions because we don't know where the trigger would be. And what we do is we try every possible top left starting position. For each position, we initialize the constraint phi. This constraint is set to phi pre, which is a preliminary constraint on the pixels of the input image. For example, if it's a normalized input, you set that each pixel is between 0 and 1.
Yeah, and that plus superposed by the trigger, okay, at that position. I think that is also done there. I think the image superposed by the trigger position, huh? Yeah. And that's what the pre.
Yes. But we have not touched the image yet, so they're all variables at this point.
Oh.
And then we go through for each image I, and then we generate the constraint that talks about the successful backdoor attack on that image. This is the function that uses abstract interpretation using deep poly. It starts with phi pre. It takes the input image. It knows the shape. It knows the position because we're going through all possible positions. It knows the target level. So we walked through an example, seeing how we can generate the network behavior constraint along with the backdoor attack success constraint. And we get this overall constraint for this image. Let's call it phi I. And if we call a SAT solver, and if we find it to be unsatisfiable, it means no trigger at the current position can make the network misclassify this image with the target level. So if this image can be backdoored, so we can set the whole feed to be false, and we can break out of the loop. Okay, so if it's satisfiable, we accumulate the constraint into phi. And this phi will now represent a condition trigger must satisfy to backdoor all the images processed so far in the set X. So after the inner loop, we have phi that's representing a constraint for all the images in the set X for it to be successfully backdoored. If solving phi, if it was not unsat anywhere, solving phi if it results in sat, then we are given a particular trigger input that caused the satisfiability of phi. We can check if this is an actual trigger because it's an over approximation using deep poly. We need to actually check if it's an actual trigger. That is why we have unknown. So what we do is we call OP trigger that checks if the solution, if the model returned by the SAT solver is an actual trigger, or if it's not, then we actually try to use gradient descent to generate. So if OP trigger successfully generates a trigger, then we can return unsafe because we've generated a trigger for the full set X. Otherwise, we set the unknown as unknown.
They can, I mean, if you do it, there is, yeah, I mean, I know you'll go through OP trigger, but I just wanted to have a question. So whatever trigger that it generates has to work for all the images in X. correct?
Yeah,
So
yeah.
whereas the constraints that you have accumulated so far will only say, oh, you found a trigger at some position, okay,
Yeah,
at one
yeah.
or more positions. So this is doing more work, not only to check if it is spurious or not, but also to generate, to see if you can find a trigger that can trigger all the images, right? A common trigger that
Yes,
triggers
yes.
all the images. Yeah.
Yes. So yeah, so if this method returns a trigger, we can return unsafe. Otherwise, at this position, HPWP, we could not verify that there is no backdoor. So we have to set as unknown to true, which will be later used once you have run out of all positions. And you could not return unsafe at any position. So if as unknown is true, we return unknown. Otherwise, we can return safe. Okay. And
just please go back one slide.
Any questions? Any questions?
Yeah.
Yeah, go ahead.
No, I just want to say, like, okay. No, yeah, it's continue.
Okay. Thank you.
So I have one question
Yeah.
here. I mean, so I understand that they're getting these 5 from some deep poly, but is there something special about using abstract interpretation? I mean, if it would have scaled, would using some other solver also work? Because all that one needs to do is to solve the simultaneous sort of k safety thing where you have k different images, and for all of them we want there to not be any backdoor, right?
Yeah.
So that is
In
kind
my
of a case safety
understanding-
query, and we can.
Yeah.
Sorry.
No, yeah. In my understanding, yeah, I think scale is the main problem.
Correct.
That's why we're using, I think, abstract interpretation.
Right. Okay. But yeah. So I mean, if it wasn't the case, one could have used any. Yeah. Sure.
Yeah. Yeah.
Yeah, I mean, I know that people don't know, I mean, about K-safety. So this question may not be. So maybe I'll take it offline. I'm not sure. Okay, simple thing is, I don't even think it's K-safety. Okay, but I don't want to get into the details. Maybe you're right.
I see.
Yeah, I think it is a simple
Okay.
SAT. Okay, because it's all fully universally quantified. You have to check if there is, for all positions, for all X's, there is no trigger. Okay, that's how. So it was.
Yeah, but I think you would need copies of the network to probably encode it for.
Really? Okay. I mean, yeah. Okay. Maybe, may not. I'll think
Maybe
about
I
it.
don't know. I don't know. Yeah, maybe we'll discuss this later.
Maybe more complicated than yeah. Yeah. Okay.
Okay. Yeah. So the next level of detail is the algorithm OP trigger, which receives, as we've seen, the network, the set X, the constraint phi, the shape of the trigger, the position at which we are checking, and the target label for which we are checking. And it returns a trigger that's successful on the set X, or it returns nothing. So yeah, so like we said, if phi was satisfiable, we have generated a model of our phi, the trigger SM. We check if it works for all the images in the set X. If it does, then we can just return this trigger. If not, we set up a loss function for each image like this. So what we do is, yeah, so in the case of, we take the image I, we have some S that we don't know that we'll optimize for. We'll see, we'll initialize it, let's say randomly. And we compute the loss function of this trigger on the input image as follows. So basically, if ns greater than no, what ns and no are, basically ns is the logit corresponding to the target label ts, and no is the logit, is the maximum logit that is not corresponding to ts. That is, if ns is the maximum logit of all, then the loss is 0, because well, the attack succeeded. If it's not, we take the difference between NO minus NS and we add some epsilon. I guess in the case this difference is too small, we want to boost the gradient signal. So yeah, so we set up this loss function otherwise to encourage prediction of TS. And we get the total loss by taking this loss for each image, and we take the sum. And yeah, we try to minimize this loss by optimizing S using gradient descent, and we obtain a candidate trigger. That's some minima S star. And if this works for all the images in the set X, which we can check by doing a forward pass by stamping each input with this S star.
But here, you just run it. Here, just run it. Yeah.
Yeah, which is cheap. If it works, then you can return S star, and if it doesn't, we return null. So there's
basically what you're doing is it like, why do you, I mean, the gradient descent, you're running it, why do you need, I guess you run gradient descent to see, minimize that so that it is as close to your that original model, is it? I mean, you're getting all things.
Yeah, so you're optimizing the loss, which encourages predicting the target label on the stamped images. So you minimize that, and the parameters you're minimizing are the contents of the trigger S.
Yeah.
Is that okay, sir?
Yeah, I think so. So here you're doing it for all kinds of but capital S is a trigger, but are you varying the content of the trigger here as well? And if so, it should be done. There should be further sampling of that. No, that's what I was confused about. Okay.
So what I understand is S is initialized randomly, and we optimize the loss with respect to S.
Oh, I see. Okay. Okay. Yeah. I know. I can't say that I understand all the details, but I get the idea. Yeah. Okay. Any questions? Yeah. Okay. Please go ahead.
Yeah. So we want to prove the correctness using this lemma. So what we want to prove is, given a network N, a set of images X, a trigger shape, and a target label, we want to claim that verify X returns safe only if there is no backdoor attack, successful on all images in X, with the provided shape and the target label. And this is for all the positions. There should not be a backdoor attack at any position that is successful on all images. And it returns unsafe only if there is a backdoor attack, which is successful in all images with the shape and the target label at some position in the input. So the proof is basically, attack condition is what we use, which is based on deep poly. So if you assume the soundness of deep poly, it always returns a constraint, which is an over approximation of the constraint that must be satisfied, such that the trigger is successful on the image. And verify X returns safe only if constraints that are satisfied, that need to be satisfied to attack on all images at each certain position are unset. So combined with the soundness of attack condition, we can see how the first part of the lemma is true. And second also holds because we only return unsafe when we're able to generate a trigger that is successful on all of X. So this is the easier part of the lemma that we can. And now I want to prove the soundness of the verified PR algorithm. That is, given given the inputs, the neural network and the success rate theta, the target label TS, the trigger shape, and the type 1, type 2 errors, and the buffer, half width of the buffer region. Verify PR returns safe only if there is sufficient evidence. Yeah, by sufficient evidence, we mean subject to the error tolerances you have specified, that there is no backdoor attack with a success rate at least theta for the given shape and the target label. Okay.
What is the significance level? What is the significance level in that statement?
So type 1 error and type 2 error are telling you basically the probability that you fail to reject the null hypothesis in the case that the null hypothesis is actually true. So at what significance are you willing to accept the result determines what values you set for alpha and beta.
I think that, yeah, that's kind of determined based on this delta, alpha, beta, and so on.
Yeah. Yeah. So we assume the correctness of the SPRT algorithm, and we can say that verify PR return safe only if there is sufficient evidence that H0 is true. The notorious 4 lines that we discussed at the bottom of the algorithm. So we'll just say we know SPRT is true. We know the bounds are correct according to the SPRT algorithm. So we assume it returns safe only if there is sufficient evidence that H0 is true. So we get that the probability of not having an attack on a set of k randomly selected images is at least this. This is basically H0. So if verify PR returns safe, we're accepting H0, the null hypothesis, which is stating this, the point number 2. But we know by probability theory that if there is a backdoor attack with success rate at least theta, then for a set of k images, the probability of having an attack on all of them is theta to the power k. And if we take the contrapositive of statement 3, and if you do mode exponents with the statement 2, we can conclude that there is no backdoor attack with success rate at least theta. Okay. So now I look at the experiments. They've basically tried to answer 4 research questions empirically. So the first question is that if the realization of the verify-X algorithm is effective. What they mean is the verify-X algorithm that checks for a trigger that's successful against a specific set work effectively. Basically, will it return safe reliably when the networks given to it are actually safe? So what they do is they take 51 pre-trained networks, safe networks without backdoors, and they try different architectures, mostly fully connected and some convolutional, and they try 3 different activation functions, and they test each of them against all possible target labels from 0 to 9. And they set k equals 100 for this experiment. And if there are any images in this set that are already matching the target label, or misclassified by the network as with the target label, they're filtered out.
Yeah, but here I mean, once again, I asked you when we reviewed also, what does effectively mean? Verify X, whenever it returns safe, it is fully sound on that, on a particular X, it'll never, because it is using, after all, abstract interpretation, and then at worst, whenever it returns safe, effectively by means, if it is returning mostly unknown, then it is not working effectively. You're not checking the soundness, it's efficacy in terms of whether how
It's the other way. Yeah. If the
Yes.
network is clean, will it return safe?
Okay, and not unknown. Yeah. Okay,
Yeah.
that is yeah.
So on the x-axis we have network types. ReLU indicates the activation function. _3 represents the number of hidden layers. Yeah, they take 5 of them into 5. That's what into 5 means. And on the y-axis you have frequencies of how many times it was actually classified as safe and how many times it was classified as not safe. So the algorithm was able to prove safety of the clean networks in 89% of the cases. So we had 51 networks, 10 target labels. So there are 510 total.
But what was the size
instances.
of the sample that they used here?
They used k equals 100.
No, there were 100 images. Just they checked it on 100 images. Huh?
Yes, sir. Yeah. Yeah, so the bottom line is that it worked in 89% of the test cases. They were also able to see that it worked even in case of more complex networks like convolution networks. And the problem seems to be with the networks having tanh activations. Yeah, so networks with those tanh activation functions were less likely to be verified, and they attribute the hypothesize that this might be because of much lower precision that's obtained in doing abstract interpretation involving tanh. But they also say it could be due to actual vulnerabilities in the method.
So what is the difference between the 3 tanh networks, tanh3, tanh4, tanh5?
Oh, it's the number of layers, 3, 4, and 5.
3, 4, and 5. And what does X5 mean?
Oh, the total
There are
number
five
of
such
networks.
networks.
Yeah, 5 such networks.
Okay.
Yeah.
Okay. Yeah, I mean, if it's just growing with the number of layers, then it's probably the former, right? I mean, it's probably imprecision.
Yeah.
Yeah.
Yeah. So now they look at the question: does the complete approach, the algorithm 1, the verify PR algorithm, does it successfully verify that the networks are free from backdoors that achieve a certain minimum success rate theta? So what they do is they run the full algorithm, verify PR, on a subset of 6 networks. We look at what the varying characteristics are. And they also include all the 10 target labels for each network. And they vary the sample size k and the target success rate theta, but not too much. They just see 2 possible values for each. And they use the test set, Fulham test set, as the population for validating the trigger success rates. And they also employed timeouts. Yeah, they also employed timeouts because, yeah, the SPRT process was taking quite a lot of time in certain complex cases. Yeah, so here ReLU _3_10 means a network with ReLU activations, 3 layers, and in each layer there are 10 neurons. So the good news is that it verified many of them as safe. Especially it worked very well in the case of ReLU. And yeah, configuration of k equals 5, the small k, and high theta resulted in the highest number of successful verifications. So you can see the contrapositive is that increasing k or
How many
decreasing.
iterations that took k is equal to 5 is fine. So it did converge in those cases. Go to the previous slide. So yeah, the fact that it was able to successfully verify in those cases itself is an indication that it converged and terminated for these values of k and theta.
Yes.
Yeah.
Okay. Did they talk about how many iterations of SPRT they needed?
I think they did, but in terms of time it took.
Okay.
Yeah, but I might be
Um,
missing a detail.
Sure. The other question is, of course, I mean, changing k while keeping theta the same. That doesn't change the actual confidence we get of the no backdoor attacks not existing, right? So we still know that there is going to be no backdoor attacks that exists with success rate greater than theta for the given level of significance, no matter what k we choose, right? Because I think that is compensated for with the SPRT.
Yeah, but that is true. But the question is if it converges faster. Obviously, I mean, when it converges, it definitely has to satisfy one of those hypotheses. Okay,
correct.
Then it converges. But yeah.
And again, tanh performs really badly.
Yeah, it has timed out in all the cases. Yeah.
Yeah, but then there's also the thing is the probability is 1 minus theta to the k. So for the same theta, if you keep increasing the k, then if you keep increasing the k, then that will be even it gets it closer and closer to 1, no? So that might have an impact on the convergence and maybe on the result also, no? I don't know. Yeah, that's what the SPRT where it comes. Okay, so because theta to the k will be even smaller and smaller, and with high k, then you will be required the longer to converge could be, and then result also could be better. That's a question that I'm raising. That's all. I don't know.
Yeah. So yeah, I think in my intuition, high theta and low k works. And if you have a high k, then like you said, it'll be very close to 1 and it'll be harder for SPRT to separate those two. And if theta is low, again, the probability will be close to 1. Yeah, and so in all other 3 cases, except when theta is high and k is low, we can run into
problems.
Yeah.
Okay, go ahead. I think you're getting close to the deadline.
Yeah.
And it's been a long day, and there's one more day. I hope people will show up to support them. Yeah.
Yeah. So like I just said, increasing k or decreasing theta led to timeouts because they required more rounds of SPRT. One anomalous result was that they were able to generate triggers for TANH3_10 networks for a couple of target labels. They suggest that it might be because of universal adversarial perturbations or the low threshold, which 80, I don't think is a low threshold, and 80%. And I don't know what, I'm not entirely sure what universal adversarial perturbations are.
You say it's an
So-
anomalous situation, which means that although was it a correct outcome or not?
No, the
Sound-
networks were clean, but the method
Ah.
generated a trigger that worked
Hmm.
80% of the time.
Okay, because the trigger is also kind of subject to, it's not a precise, no, but it's checked, no? Everything,
It's
whatever
checked on a subset.
Mhm. No. Okay. Okay, go ahead,
Yeah.
please. It's getting.
Yeah. So, and they analyze the time efficiency of the approach. And the way they do it is they measure the wall clock time for the previous two experiments. And so for the first research question one, where we checked verify X on K equals 100. So the times seem to have varied widely from seconds to hours. If you notice, the y-axis is on a logarithmic scale. And yeah, TANH networks seem to have been significantly slower than the ReLU and sigmoid versions. And yeah, possibly due to more complex verification. That was
So I have a
Yeah,
question
they'll-
here. I mean,
yeah.
you're saying that it's due to more complex verification cases, but if one is using abstract interpretation, the complexity of the constraints coming from sigmoid versus TANH versus ReLU should be similar, especially with deep poly, right? Because you're only going to give, I mean, no matter what your activation function is, you're only going to give a linear upper and lower bound at the end of the day, right?
It's a good point. I think, I'm not sure, I might be wrong. I think the cases where the imprecision comes into play is, and like in the case of ReLU, is when the input to ReLU is crossing zero, right? I wonder if that's more common for TANH.
I
But
know, I mean, I would imagine that it would be common in all three cases. I mean,
Okay.
yeah, I mean, that is at least my intuition from experience, at least, because
Okay.
it's very rare to find ReLUs, unless you do some branching, it's very rare to find ReLUs that are stuck positive or stuck negative. Because, I mean, people train networks typically to avoid such situations, because that is precisely where you say that your gradient has saturated, right?
I guess I would have to check more on that.
Yeah.
Yeah.
I mean, again, if they were reporting the number of iterations, this could be answered very directly, right? I mean, if we could just compare the number of SPIT iterations, and that might, and understand
it
how
could be
that.
because of large number of iterations.
Yeah.
than
Correct. But yeah,
verify
that, I don't know if
taking
they're
longer.
reporting that data. Yeah.
Yeah, Shashank, I see
Yes,
you
sir.
have still 9 more slides and you only have
Uh,
5.
Yeah. Some of them are appendix. So yeah.
Okay,
just a one
appendix, I
word.
think we can take offline if there is, I don't know if
Yeah.
there is any,
Yeah.
to discuss.
So how much time do we have? We
Till
don't have
7.
much time.
7 is a hard stop. Okay.
Yeah.
Yeah, go ahead.
No problem. Yeah. There are not many remaining. Yeah. So they also look at the wall clock times for the full verification. Oh, actually, yeah. This is for verify X only and not verify PR. So I guess the question you asked still remains.
Oh.
And yeah.
Oh, okay. That is very confusing then. Yeah. Okay, sure.
Yeah.
Yeah.
Yeah. Thank you. So yeah, they look at full SPRT verification, and times still varied a lot depending on K and theta. And yeah, as expected, increasing K increased the duration, and also decreasing theta also increased the wall clock duration, because the SPRT, as you expect, would require a lot of trials. And finally, they look At the question if the approach can actually generate backdoor triggers in the case that you actually give a backdoor network. So they take a new set of 45 networks. They use the data poisoning technique that we briefly discussed to insert a backdoor. Yeah, and they filter the test set to only have images that are susceptible to this backdoor that we have inserted. And they call OP trigger on these networks. And they're susceptible image sets that we have filtered. So they were able to generate the correct trigger for 33 out of the 45 backdoor networks. And for the remaining 12 networks, the generation didn't succeed because, well, either the initial data poisoning attack itself was not effective, or the trigger generation process. Yeah, it's mostly because the data poisoning attack itself had not succeeded. Yeah, and yeah, the trigger generation process itself did not take a lot of time, less than a minute on average per network. Yeah. Do we have time, right, to conclude?
I have a
summary?
few questions. Maybe if
I think,
so,
yeah.
I mean, I'm suggesting maybe if we can take questions instead of the
Yeah,
summary,
please.
unless.
Yes.
Yeah.
Let's take questions. Yes.
Yeah. So one question that I have. So when so in the whole algorithm flow, when they're coming out of OP trigger, what they have done is basically they found a backdoor attack that works on a particular set of K images, right?
Yeah.
But we don't know anything about the success rate of this trigger in any kind of statistical guarantees of the success rate of this trigger at that point, right? So when we do return unsafe.
Why do you say that, Diganta? And because I thought when they ran gradient descent, I mean, they could, I don't know, is it true that the operation trigger only selects one? Because usually when you run gradient descent, you kind of have all these episodes, you can have multiple set of samplings and then keep doing, no? I don't know if they do that or not. Is it?
No, so I mean, so I don't know if I don't see any of that here, but
Yeah,
I mean,
because
let's even
eventually
forget
they're
about
checking on capital X. You're right. You're right. Because eventually they're only
right.
they're checking on particular
Right.
X. Yeah.
Yeah, and I mean, even if let's assume that instead of gradient descent, they have some kind of magical perfect optimization step in six, this question still remains, right? In the sense that, I mean, of course, it's just this X is just some X that has appeared in some iteration of algorithm 2. And if OP trigger just happens to find an event, especially if the K is very small, we don't really know if, trigger, if the K is very small, we don't really know if that is a trigger for the global test set for with 80%, right?
Yeah, which is why we check if the generated trigger satisfies the success rate again.
I see. So
Yeah.
that is again some kind of statistical test if they're doing,
Yeah,
is it?
you run it on the full test set and you see if you
Okay.
get the data of them are being factored on it.
Okay. So that makes sense. Right. So then,
although the optimization is run on capital X, then they check on a much larger thing. Is it? That's what you're saying?
Yeah, that makes sense.
Okay.
Yeah. So can you go to slide 27 once?
Is
27.
Yeah.
Yeah. So here, when they're saying that they're surprisingly generated triggers, they did do this check, I guess, right? Yeah. So then it is indeed surprising. I mean, I was wondering if this was simply because of this kind of small K, but I guess not.
Yeah.
Yeah. What is the K that they used in this experiments that you talked about in slide 21, 22?
Let's see. It was 100.
Okay. No, I'm not talking about verify X. I'm talking about they have this op triggered experiments in 31, 32. I mean, yeah. Yeah, do they mention the K here?
I am not sure actually.
Yeah, okay.
Wait, oh, let's see. So the test set is 10,000 images, and they keep the images that
Right, no,
that
but like I mean, they could still choose some K5 or 50 and optimize on just some, right?
yeah. I don't remember that detail. Yeah.
Okay. One last question that I have was that, see, they're generating these triggers, but they've also introduced some triggers via data poisoning, which seems like they're using some white square, right?
Yeah.
Do they mention whether the generated trigger and the actual poison trigger matches?
Yeah, yeah. It actually did.
It
It
actually
generated
did.
the
Oh,
correct
that's
trigger.
actually
Yeah. Yeah.
wow. That's amazing. Yeah. So it's not like it just found some universal adversarial perturbation or something
Yeah.
like that. Yeah.
Yeah.
Yeah. Okay, that's actually very interesting. Yeah. Yeah. Okay, sure. So that was all the questions I had on my end.
Thank you.
Yeah. Sorry for interrupting. Maybe you can, if yeah, or others can ask, or you can conclude.
Yeah.
No, I think I'll prefer taking questions. If there are any questions. Everybody's tired. Go. Okay, I mean, I think I have some dry runs to do after this for
I
tomorrow.
see. Yeah. Yeah. So
I mean, we couldn't because we pushed it to the end, and there are a few that we'll have to do.
So is any of those dry runs, do I have to be there, or
No, yeah, I
I
don't
don't
even excused.
Okay.
You want to be there?
No,
You
no,
want
no.
to
I
be
mean,
there? You're glad to be there. I go home, you'll be
no,
there.
no.
No,
I'll
this
take a
one.
rain check on this.
Yeah,
Yeah.
I've roped in Arpan. Okay, it's Vardhan's dry run.
Okay.
And it's up
Yeah.
Arpan Bag's alley. This one.
Yeah.
I may even say, Arpan, you take care of it and I'll go home. I don't know. No. Anyway, that's at 7 because then I'm still here at CMI. I'll have to find my way home. Okay. No. That's okay. If there are any things, we can take 5 minutes. Okay. If people want to stay, they can stay. I mean, no. Since I'm giving 5 minutes, I can't say people go home. Okay. You have to stay if you yeah. So you want to finish up? 5 minutes you have, Shashank.
I pretty
You're
much
also
done. Maybe I will do limitations. Yeah.
Oh, okay.
Because this would be the last slide. Yeah, I think we've discussed this. I came up with the questions. Yeah, we've discussed over approximation. We've discussed the scalability challenges. Yeah, so one thing that the paper doesn't consider is the input-based triggers. Yeah, we're looking at a universal trigger for all networks and all inputs. But backdoor attacks where the trigger is input specific could also be realistic, but it seems to be significantly harder, and it's not considered. And the trigger shape is also something the algorithm assumes, but this again doesn't seem very realistic. And considering all trigger shapes, we can see it makes it very hard to scale.
Right.
Yeah.
So do they actually, in the experiments, all the trigger shapes were held constant, right? They don't have any data showing how much worse they get if you make the trigger shape much bigger or something.
Yeah, and they use a constant shape of 3,3 for their experiments.
Okay.
Yeah. Thank you, everyone.
Okay. Thanks.
Thanks a lot. This was amazing. Yeah, this is a great presentation. Yeah.
Okay.
Thank you so much.
Yeah. So far, so thank all you for the good work. I think it's been good. Yeah. Put in some good effort. So tomorrow at 8:30, I mean, I'll send an email.
Yeah, I might not be able to join at 8:30, but I'll definitely be there by 9.
Okay.
Yeah.
Maybe I'll start at 9, so you won't miss my talk.
Yeah, that would be great actually. Yeah.
No,
I mean,
I'm not.
but I think
I'm not
that'll.
very great. It's the others who expect to do so. Maybe I'll also start at 9 o'clock. So maybe I'll announce at 9 o'clock. What, half an hour anyway, going to the lunch. Okay, I can take it out of the lunchtime.
Yeah, that's
9,
what I was
because
asking. I
it's
mean, I
been
don't know if
late.
that's okay with everyone. But yeah.
Yeah.